Just a moment.
Sure.
So, a very hearty good morning to you all the participants. We are on the second day of the conference, second day of the International Conference Multifunctional Electronic Materials and Processing, MEMP 2021. And today we are going to start the day with a lecture by Professor Anuruddha Suman from Aragon National Lab. And he's going to talk about towards developing energy efficient electronics based on diamond. So let me briefly introduce you the speaker of the speaker. Professor Anuruddha Suman is the group leader, Nanofabrication and Devices Group, and material scientist at the Center for Nanoscale Materials, Aragon National Lab, USA. Dr. Anuruddha Suman is the leading scientist in the research of nanocarbon materials, including CVD diamond, carbon nanotubes, graphene, as well as other 2D materials. He is the leading expert on energy efficient systems based on nanocarbon materials. His recent work on demonstrating super lubricity, near zero friction at engineering scale opened a new era of solid lubrication technology. He has more than 25 years of research experience in synthesis, characterization, and developing applications of CVD diamonds. His main research interests include super lubricity, nucleation, and growth mechanism of diamond and other carbon materials, novel synthesis routes, surface chemistry, nanoelectronics, micro and nanoscale cryobiology, and micro nanofabrication. He is the author and co-author of 130 peer-reviewed journal proceedings, publications to book chapters, and has 29 granted patents, 17 in pending. The list of his awards include 4 R&D, 100 awards, NASA Tech Brief Magazine Award, and the 3 Tech Connect National Innovation Awards. He co-developed a nanotechnology educational kit, Next Gen STEM kit for high school students in collaboration with United Scientific Supplies, which is now available to high school students across the United States that gives students first-hand nanofabrication experience right in their classroom. He was recognized by Pinnacle of Education Award from Board of Governors, University of Chicago and Aragon for his achievement. He has presented his research via numerous invited and keynote address talks as well as through TED Talks. His research in diamond and graphene materials helped in the formation of several startup companies. He is advisory board member of Applied Physics Letters and a member of MRS, STLE, and ABS. So you can visit his Scholar Google page, LinkedIn profile, research highlights and portfolio at A&M, and his webpage on the Aragon website. So over to you, Professor Anuruddha.
Well, thank you, Ranjit, for a nice introduction, and good morning, everybody. First of all, I would like to thank Ranjit and Dr. College to really invite me for the presentation here. It's really an honor to be here celebrating the CMET's Foundation Day. I think I have a old connection as I did my MSc and PhD in Pune during 91 to 1998. And I think that was a time period when CMET was in construction and then in operation. So I feel, really it's a great occasion to be here and an honor to really celebrate CMET's Foundation Day. And, looking back, I think 30 years now seems like yesterday, but I think CMET came a long way. And today, I think recognized as one of the prime institutions, in India and abroad. So it's my honor to be here and talking about some of the work that I have been doing here on the diamond electronics. So let me go to the next slide. Okay, looks like the slides are not going. So maybe I'll stop share and start again. Something happens here.
Maybe you can stop sharing the video, I think then.
Okay, let me start sharing the screen because it worked perfectly before. It should work. And let me go to the presentation mode here. Okay. So let me first introduce the Center for Nanoscale Material at Argonne National Lab. This is one of the user facility of the DOE. And we work on various research areas which are mentioned here, starting from synthesis, nanofabrication, advanced microscopy, nanophotonics to theory and modeling. And as I said, this is a user facility, which means anyone from the world can really apply through a simple two-page proposal. And once they get accepted, they can come and do the work with free of charge. And you don't have to be US citizen. People all over the world, come to the CNM, as well as there is the advanced photon source, which is adjacent to the CNM. So it's a really nice facility, and I'll encourage you to, look at the web page, which is mentioned here down below. And if you see any interesting facility there, feel free to write to me, apply for your user time, and you can really use all the great resources here. A little bit about my group. We have been doing a lot of work on the carbon-based materials for many years. So we work basically on diamond, graphene, historically, a little bit on the carbon nanotubes, but bulk of my research activities is on diamond and graphene nowadays. And one of the part is goes really to the electronic properties, and another on the tribological properties. But today I'll be focusing on mostly, diamond and its electronic properties. So the capabilities in our group, we oversee 18,000 square foot of clean room, which has all the state-of-the-art facility that you need to fabricate a device. Some of the systems are mentioned here. We have one of the large area diamond CVD synthesis system, as well as we have a newly developed quantum matters and devices lab with a millikelvin cryogenic facility, and then also super lubricity lab, where we study various nanomaterials as a lubricant and look at the wear friction properties, as well as the fundamental science behind this nanomaterial and how they work as a solid lubricant. So let me talk about the diamond, which is the major topic of my talk today. As you very well know, that two forms of carbon are very distinct. One is a diamond, which is a tetrahedrally bonded carbon, and another is graphite, which is sp2 bonded with the AB stacking, with a very weak bonding between the layers, van der Waals, and then it has a completely distinct properties between these two forms of carbon. We always say that diamonds are forever, but if you look at scientifically speaking, diamond is a metastable phase of carbon. So if you keep it diamond, outside, for a million years, you will see that the top layer of the diamond may convert into some, graphitic layer. So, even though it takes a lot of energy and, a lot of time to convert into graphite, it's a metastable phase. And really speaking, scientifically, diamonds are not forever. But, considering human lifespan, you can always say that diamonds are forever. If you look at the free energy diagram of the carbon, you always see that you can convert easily diamond into graphite with some energy, but converting graphite into diamond, you have to barrier this big potential energy barrier, and so that's why it's a very high activation energy needed. You may have listened to yesterday's talk from Rod Ruoff, and there are some interesting work going on in converting this bilayer graphene, into some kind of diamond-like layer. And I think that's a really interesting scenario, but a lot of things I think still needs to happen to really see how we can meaningfully convert this few layer graphene into really what we call as a diamond. So let me talk about the phase diagram of carbon. It should be very familiar to any material scientist here. But there are various ways that you can synthesize diamond. First is a shock wave synthesis, which is also called as a detonation method. And then it requires very high pressure and very high temperature. This generally happens when you wrap some of the graphite with TNT explosives, and then because the explosion, there is a shock wave produced and the temperature produced. In that cases, you convert graphite into nano diamond. That's called the detonation method. The other well-known method is, of course, high pressure and high temperature method, which is started in 1950s by General Electric, where they use the tetrahedral press, and this is how the nature creates diamond. Very high pressure and high temperature, in the mantle region of the Earth's core, where the carbon, because of very high pressure and temperature, converts into diamond. Now, there is another interesting region at a relatively low temperature, which is accessible to us, can be produced easily in any lab, about 800 to 900 degrees Celsius, and then also pressure less than atmospheric pressure. You can create, or you can synthesize diamond, which is called as a chemical vapor deposition synthesis. So these are different ways you can synthesize diamond, and I just wanted to remind you that in 1955, this team of scientists led by Tracy Hall at General Electric synthesized first time diamond by squeezing graphite at very high temperature and a mechanical press. And then, they use about 1.5 million pounds per square inch and the temperature of the order of 5,000 degrees Fahrenheit. And, it's later on, we also realized that just by introducing just few atoms, of nitrogen or boron, you can change the optical properties of this diamond. And, that leads to a different fluorescence. So you will have a kind of yellow-like diamond if you have nitrogen impurities, and you will have nice, blue color diamond if you have some boron impurities. Now, let me talk a little bit about the historical, background in the gas phase synthesis, because that was the real, exciting area when people saw that it is possible to synthesize diamond. And it was in 1962, Eversole from Union Carbide in the US first demonstrated the growth of diamond particles on a diamond substrate using hydrocarbon pyrolysis. And it was until 1972 when Russian scientists really introduced the concept of gas activation, by using hydrogen, where they show first time with the hot filament activation process that they can etch the non-diamond component, and then produce, a growth rate of diamonds at a reasonable rate, which is micron per hour. And then there was a lot of explosion of research activity. Similarly, the efforts in the US by John Angus at Case Western Reserve University also, did the first successful demonstration of this diamond thin film onto the non-diamond substrate. And then, there was worldwide interest in this, interesting material. 1992, there was a first demonstration of phase pure nanocrystalline diamond at, hydrogen poor plasma by Dieter Gruen and co-workers at Argonne National Laboratory. That's where I, did my first postdoctoral fellowship. And, interestingly, I should mention that I did my PhD in Pune University in 1998. And, there was a very active research area in the diamond. Dr. Godbole and Dr. Ogley, started this research activity at University of Pune. And I think this was probably the first time in India our group, showed the synthesis of diamond, and that was really exciting time there. And it's great to be talking about diamond again, at this CMET conference. So at Argonne, our group have been, very active in utilizing diamond as well as different forms of, carbon like graphene. and really utilizing this material for various applications. In the market, there is a lot of collaboration and few spin-off company that I have mentioned here. And as you can see from the list of R&D 100 top R&D 100 awards that the lab has received through the research done at Argonne, as well as in my group at CNM. So let me remind you a little bit about the nucleation and growth process. As I mentioned, this is a gas activation process. So it could be micro, plasma or hot filament CVD, and then you have hydrocarbon gases like methane. Because of the activation or the energy which is supplied, to these gas molecules, there is a dissociation of this methane into the methyl and acetylene radicals. And then, these radicals then condense on the substrate surface, which is relatively, at a lower temperature, like 800 or 900 degrees Celsius. And then there is a diffusion of these species that happens on the substrate surface. Traditionally, any carbide formation material, which has a less incubation time and favors diamond growth readily because, they form this diamond nuclei much earlier than the other ferrous material, which has very high diffusion rate for carbon, and that's why long incubation time. It requires too much longer time and sometimes hinders also the diamond growth to form this critical diamond nuclei. And then once the critical diamond nuclei is formed, then there is a coalescence and decollation growth of diamond crystals. So traditionally, it's well known that the main principal growth species for the hydrogen-rich chemistry is a methyl radical. And the activation energy, for this methyl radical to insert in the diamond lattice is about 20 to 30 kilocalorie per mole. That gives a very low nucleation density and of course gives larger time to grow. That's why larger grain size and also the higher surface roughness. So generally, to increase the nucleation density and reduce the incubation time, you generally provide a natural, diamond particle as a nuclei. So this is a diamond nano powder you sprinkle on the surface by ultrasonication or abrading on the surface. And then once you put it into the CVD system, either hot filament or plasma, you can start growing this film in a columnar fashion like this. So if you look at the cross section of this film, you'll see the very high columnar growth morphology with the large grain size that increases with the film thickness, generally 10% of the film thickness. Now, if you go to the hydrogen pure, poor UNCD growth, we call it as an ultra nanocrystalline diamond, and that was a interesting growth process where we started at Argonne with completely with a non-hydrogen process, either C60 or with a little bit hydrogen, which comes with the CH4. And in this case, the growth mechanism is a little bit different. Instead of a methyl radical, we see that a C2 dimer, is the main growth species. And if you look at the insertion energy for the C2 dimer is very, very low, 6 kilocalorie per mole, and very high renucleation density, about 10 to the 12, nuclei per centimeter square. So as a result, there is no time for the crystal to grow. And that's why you get a very small grain size, 2 to 5 nanometers, and also very low surface roughness, which is 4 to 5 nanometers. So if you look at a plasma, you have characteristic green plasma that comes because of the C2 radical, intensity, that emission that's produces. And then once the CH4 converts into C2H2, there is a C2 that basically inserts into the diamond lattice. And then if you look at the TEM image, you will see the characteristic grain size about 2 to 5 nanometers. Since the insertion energy is very, very low activation energy here, we found that you can even grow diamond film at 400 degrees Celsius, with a similar kind of a grain size. And then I think this was a major breakthrough where we can clearly show that, you can grow diamond film at 400 degrees Celsius at a wafer level, and that is compatible with CMOS. So if you look at again the cross section here, it looks very different from the microcrystalline diamond. Here the grain size remain same from bottom to top. The grain size do not increase with the film thickness, and the very low RMS roughness, of the order of 4 to 5, or maximum it can go to the 11 nanometer. So at CNM, we have this 915 megahertz microplasma CVD. And then just by changing the ratio of the hydrogen, argon ratio, we can go from microcrystalline diamond, nanocrystalline diamond to ultra nanocrystalline diamond. And then we can also change the temperature to really make CMOS compatible film. I'll be talking about that how we can utilize in various applications. So I mean, there has been a lot of growth happen in the diamonds area in last 20 years, but there are still, some challenges. They are still remaining there, and some of those was mentioned in the DOE's microelectronics basic research need report, and those thrust areas, as remain the, some of those are still there, which is a large area growth of a single crystal diamond, and also producing a very efficient N-type doping, ability to integrate with other wide bandgap semiconductor materials. Also, how you can develop materials and architecture for thermal management. So I'll address some of those in my talk here. So let's talk about diamond for MEMS. This was the paper published sometime back in 2007. And this was a part of a DARPA project on harsh environment, robust micromechanical technology, where the objective really was to develop a high frequency, low insertion loss, CMOS compatible resonators and RF MEMS devices, for radar communications. So the interesting problem was, if you see here on the right-hand side, this is a RF MEMS switch. So you have typically a metal membrane that touches to the dielectric here, which is traditionally silicon nitride. And then when you apply the voltage, this membrane touch the dielectric, and then it acts as an on and off switch. But what happens with time is that this is metal, and then this is a dielectric. So after a certain time, there is a dielectric accumulation of charges, and at certain point, the charge is so much that it basically explodes this metal membrane, and then this device is no longer in use. So what was needed there is to really engineering of this dielectric layer, and to really see how we can achieve very fast switching. So we worked on replacing some of the things here mentioned here, and most of the important part here is really engineering the dielectric layer to make it a leaky dielectric by utilizing UNCD as one of the leaky dielectric material. So the first thing was really to establish the CMOS compatibility, because all that RF MEMS switch has to be operated by the CMOS operated circuit. And some of the interesting way of switching to the CMOS on Sapphire was because this ultra CMOS eliminates the parasitic capacitance due to the insulating nature, also achieves extremely fast switching due to the lack of capacitance, and also no nonlinear voltage dependent capacitance, and really reduction of crosstalk. So that really enables the excellent speed, linearity, and isolation, which is needed for this RF MEMS circuitry. So the first thing that we did is really to establish working CMOS, and then the way you can do that is really depositing UNCD at a 400 degrees Celsius, and then making sure that the CMOS is remain intact. So these are the steps that we use, and these are the IV curves before and after the UNCD deposition, and then we clearly see that there is not much deviation after the deposition, demonstrating that all the CMOS circuitry, even going through this 400 deposition cycle, was stable. So this was a real large efforts consisting of at least 5 different institutions, including Argonne, Peregrine Semiconductors, who developed basically CMOS and Sapphire, MEMP-Tronics, which actually designed the switch, and then innovative microtechnology, which actually fabricated, in a foundry, this 6-inch wafer. And all the diamond related, technologies were developed at CNN. So this is the, the result of the fabricated switch. And if you compare with the silicon nitride RF switch here, you can clearly see that, these perform much better than the silicon nitride switch, and then lasted for about 1.2 billion cycles with a very, very good performance at 10 gigahertz, insertion loss about 0.17 dB with these S parameters. And one of the fundamental change here in the operation was, in this case, the diamond used as a leaky dielectric. And then, it recovers very, really fast. And then, even though, the operation here is a little bit different from the silicon nitride, uh, in this case, we clearly show that, it recovers very quickly and then can last for 1.2 billion cycles. So this was a real, interesting result. And this is the video that I can show you for the switch in operation. You can clearly see the metal membrane, which is touching the underlying dielectric layer here. And this is integrated MEMS device with the CMOS on a chip. Right now you can clearly see here. So this was a first demonstration of a UNCD-based monolithically integrated, fully functional RF MEMS switch driven by CMOS. This technology is also useful for various cell phone communication, including 5G and others. And we already have, 4 different US patents granted on this fabrication. So let me move on to the now next topic, which is on the thermal management. And this is how we can do. So what I showed previously was the active electronics, and now I will show you about the passive electronics, which is utilizing diamond as a thermal dissipation for gallium nitride based devices. If you just see the comparison here from the GoPro labs, now I think it's changed to it has been acquired by I think the general sorry the there's a diamond company which acquired this, and now Element 6. And but nevertheless, if you see here the comparison with gallium nitride on sapphire, silicon carbide, and gallium nitride on diamond with the temperature of the transistor here and the separation between the transistor here, you can clearly see the gallium on diamond has a specific advantages here at 80 degrees centigrade. In this case, gallium nitride on diamond arrays can be packed nearly 100 times more densely than the gallium nitride on silicon carbide. So this is still old technology now, because this was from at least I think 7 to 8 years back now. And in this case, what they have done is depositing a diamond, polycrystalline diamond, releasing it, and then physically bonding the gallium nitride onto the diamond surface. Now, the integration of the diamond gallium nitride is really challenging. And you can clearly see here the problem that they have seen is the adhesion failure after repeated thermal cycling. And because this is just a physical bonding that happens, there is also thermal resistance between the barrier, between the diamond and the gallium nitride they use. And the other thing is you have to use very thick diamond, in some cases about 400 microns. So that's where also the cost is an issue here. So the question is, can you grow directly diamond on gallium nitride? And people have tried. The problem is if you use hydrogen-rich chemistry, then there is a decomposition of the gallium nitride that happens because of the hydrogen diffusion into the gallium nitride, which releases, the nitrogen. And then, you have either very poor quality of the diamond being deposited at lower temperature, or, you have diamond film that you can deposit, but then the adhesion is very, very poor. So the question is, can you grow a diamond, at a lower temperature with, less percentage of hydrogen? And that's where I think the low temperature UNCD comes in handy, because in this case, we have demonstrated you can grow a reasonable, quality of the nanocrystalline diamond, because here we really need a diamond with a little, a bigger grain size in order to have very good thermal conductivity. So in this case, what we have done is deposited very thin layer, 10 nanometer tungsten layer on gallium nitride, and then deposited nanocrystalline diamond. This is A5 cross section, and we can clearly see that a very nice nanocrystalline diamond deposited. This is actually the photograph of a gallium nitride wafer, and adhesion is excellent. Even with the Scotch tape, we cannot remove this nano diamond film from the gallium nitride. So we deposited two different thickness, about 150 and 300 nanometer. And then you can clearly see a very good quality, well adherent diamond film on the gallium nitride at 450 degrees Celsius. And, the use of this tungsten layer is really nice because it prevents the out diffusion of, nitrogen from the gallium nitride lattice. So if you do the Raman before and after nanocrystalline diamond deposition, you can clearly see the high quality gallium nitride peak here, demonstrating that the gallium nitride lattice is intact, and this is an XF spectrum, clearly showing very high quality diamond being deposited. And if you look at the now the effective thermal conductivity, of this layer, because this is now a sandwich layer between consisting of gallium nitride and nanocrystalline diamond. So if you look at the gallium nitride, you'll clearly see that the thermal conductivity decreases with the temperature. But if you look at the nanocrystalline diamond, which is a green here with 150, and then with a 300 nanometer thick, which is brown triangles, you can clearly see that there's a crossover that takes place here, and you can clearly see the thermal conductivity is increasing, with the increasing temperature, which is great because as the device temperature is increasing, the diamond is much more efficient in extracting the heat. And if you calculate the thermal conductivity here for the 300 nanometer thick nanocrystalline diamond, is about 833 watt per meter Kelvin, which is pretty good. Is about 6 times higher than the gallium nitride. So, in this case, we have shown that just the 300 nanometer thick nanocrystalline diamond really outperforms gallium nitride at elevated temperature. And then that means, this layer could be inserted into the, layer, into the device, layer near the junction where the heat source is produced, and can really efficient in extracting the heat to form, this nice thermal management here. Let me jump on to another topic, which is a graphene diamond. In this case, again, we demonstrate how the integration of the 2D material with 3D, which is a diamond, is interesting in in fabricating devices, which are showing very high performance in terms of very high thermal conductivity and high mobility. So if you look at the graphene on SiO2, about 77% of the heat dissipates into the bulk silicon through SiO2, and then the remainder of the heat is carried to the graphene region, which extend beyond the device to the metallic contact. And here the mobility decreases, with the temperature rise. So in this case, there is a 10-degree rise, in the operating temperature. It will add about delay of 5%. So that's kind of significant. So we thought of replacing SiO2 with the diamond and see how the graphene devices perform. Now the question you may ask, why diamond? Because of course diamond is chemically inert, has a lower trap density for charges, which is very good for reduction in noise and better signal to noise ratio. Also the energy of optical phonon in diamond is pretty high, which reduces surface electron phonon scattering and improves the saturation velocity. Also diamond has almost 5 times higher higher thermal conductivity than copper, which means better heat dissipation. And of course, the CVD diamond technology for producing diamond is well matured. So really it's economically feasible, to produce diamond wafers, at a wafer scale. Now, the question is how this graphene on diamond devices perform. So in this case, we did two experiments. In one case, we use UNCD, which is really not very good from thermal conductivity point of view. In another case, single crystal diamond, which is excellent. And then look at the, breakdown current density as well as carrier mobility. So we found reasonable, electron and holes mobility even on UNCD substrate with the current density up to 10 to the 12, which is still 50% higher than the graphene on SiO2. And then the real difference we clearly see on a single crystal diamond, because here the current density went to the 10 to the 9 amps per centimeter square, which is about 1,000 times higher than the copper. And this is probably the highest breakdown current density we have ever seen with any 2D material. This is almost similar to the superconducting wires, the current density that you see here. So this was really interesting to see how just by changing the substrate layer to the very high thermally conducting, you can extract more heat, from these graphene layers. Now the question here, of course, we use exfoliated graphene, which is really cumbersome. So we wanted to see how we can really do this on a device level at a wafer scale. So we came up with a new process in this case. We convert the UNCD, top layer into the single layer or multi-layer graphene by using this rapid thermal annealing process. It's very simple. We deposit a very thin layer of nickel on UNCD, and then it goes through this rapid thermal system with a temperature shock for about 1 minute. And then during the cool down phase, we can clearly see that the whole wafer, this is a 4-inch wafer of diamond on silicon, completely collapse into the nice, few layer to single layer graphene, depending on the condition. And then if you look at the cross section here, clearly you can see that the top layer of the UNCD converted into a few layer graphene, and we can clearly see a very nice, Raman spectra. And the unique feature here is which eliminates the transfer step, because that's where the defects are introduced. And then the diamond layer underneath acts as a solid carbon source here. You have very fine control on growing single or multi-layer graphene, and there is no stresses of nickel at the graphene diamond interface. And the processing temperature is really, which is accessible to any lab. So this was a paper published in Nature Communication, and we already have like 3 patents granted on this process. So then we went ahead with the fabrication process and clearly show that it has, again, very good mobility and the charge carrier density. So, really able to scale it on the wafer scale, and then we can definitely, fabricate it like a high frequency graphene based devices on this one. So what are the implications? I think the implications could be, taking full advantage of intrinsic properties of graphene. We have also shown that the graphene grows laterally, over the hole, and then, you can really fabricate devices, as a freestanding. Also, you have control where you can grow graphene just based on the patterning of the nickel. So you can think of, making really a sensor devices where you can convert those into the graphene nanoribbons and so on. So let me go to the last part of my talk, which is really a 3D, 2D integration of diamond with the 2D materials. And I'll talk about 2 cases here. One is a single crystal diamond with a integration with HBN as a dielectric for formation of FET. And then here is on the right-hand side, you can see that this is a PN junction diamond, based diode with the N-type MOS2, on top. So just to give you a little perspective on the FET-based, devices, there's a lot of research being done in fabrication of the surface FET, where if you hydrogen terminate the diamond layer, and then exposure to the atmospheric layer creates some kind of inversion layer and forms a 2D whole gas layer. And that acts as a kind of a channel where you can fabricate, gate and the drain and source and really can modulate the charges. So forming a surface fate. A lot of work has been done up till now in this case, showing, operating at very high voltages and even at higher temperature. One of the problem here is the stability of the hydrogen layer, and also to be able to perform at higher temperature for a longer time. And then the gate dielectric layer is the also another limitation, because to be able to apply the voltage, you need to go to the much lower thickness than this. So the question is, can we work around this and still maintain very good isolation and then preserve the integrity of the hydrogen termination layer? So we came up with the concept of introducing HBN as a 2D material. Traditionally, people are using gate dielectric as a ALD growth, atomic layer deposition, grown aluminum oxide on the surface. But we thought of creating an HBN, few layer HBN, and then depositing an aluminum oxide on top of it, and then see how it works. So of course, before we do that, we do the hydrogen termination to create this H termination layer. And then we go through the series of the fabrication step, where we expose now is to oxygen atmosphere to have the isolation of the charges, and then create this kind of source drain gate structure, and then deposit ALD grown aluminum oxide. So basically what we are doing is we are trapping the hydrogen termination layer with a very nice thin layer of HBN, and then on top of it, we are growing aluminum oxide, so that we can really trap that layer of a 2D whole gas, to be not exposed to the atmosphere. So this is the fabrication of metal insulator semiconductor kind of a diode characteristic, and in this case, just with the HBN and with the aluminum oxide, of course, we see leakage current density of the MIS diode is below 10 to the 6 amps per centimeter square, which is really good. And then we also looked at the DC output characteristics in this case, and we were able to clearly see the maximum current density up to 19 milliamps per millimeter, which is again very good with the combination of HBN and aluminum oxide. So if you compare that with whatever values which are available, in the literature with aluminum oxide thickness about 200 nanometer, our values of a current density is really, comparable, or in some cases, better than this with aluminum oxide thickness of just 10 nanometer, including the thickness of the HBN. So, at such a smaller thickness, we are able to apply, much higher voltage, about, 2 million volts per centimeter, and able to reduce the leakage current. So this was a really good, demonstration of achieving a good FET structure with a combination of 2D material. The other thing that we did, and this is still under, investigation to the next stage, is able to get a kind of a pseudo delta dope N channel. This is really interesting. When we deposit N-type MOS2 on a highly boron doped, P-type diamond, we able to see a very good ideality factor, about 4, and high current density with a nice leakage current in reverse biased into the 14 amps, showing a PN junction basically characteristics. It's really interesting to see why the 2D material will create a kind of an N-type surface charge, on the diamond, acting as a kind of a, PN junction here. And if this is really happening, this is really great and could be game changing, because it's acting as a kind of an N-type delta dope layer. I mean, in diamond electronics, people go to the great lengths in achieving the delta doped, N-type layer with ion implantation, and it's a very difficult process. But here, if we just by transferring the N-type MOS, if you are achieving that, that's really remarkable. And then now we are working towards fabrication of a, transistors and logic circuit to really see if we can, show a good operation of a device, with a high current density. So finally, I would like to conclude my talk by saying that this CVD diamond technology has really come a long way from producing this bulk diamond to the thin films of diamond on wafer scale. And then we are really enabling in new innovation in MEMS and NEMS, harsh environment electronics, as well as in thermal management. And this integration of diamond with graphene and other 2D materials really offers a great promise in developing these diamond-based electronics through an interesting possibility of this charge transfer doping. In case of this dielectric engineering, by incorporating this 2D hexagonal boron nitride layer, we clearly show that it has a lot of promise and really, take the advantage of this in going to the next step for high frequency electronics. And I think same is true with the PN junction, where it's kind of showing formation of this pseudo, delta dope in channel. And really more studies are needed in this case to understand the surface charge doping at the interface and how we can take advantage of this in really creating a, integration of diamond with 2D materials to really go and form this next generation of, highly efficient diamond-based devices. Finally, I would like to acknowledge various collaborators, in the diamond MEMS as well as in electronics. Alexander Balandin from UC Riverside, he did a lot of, thermal measurements, long time, and a kind of a diamond veteran, Jim Butler at that time was a Naval Research Laboratory, of course, long-time colleague Orlando Ocello, Robert Karpik, Chris Goodman, and of course my group and fabrication devices. And this also not have been possible with a lot of help from my postdocs and the students along the way here. And of course, the funding from the NSRC and the US Department of Office of Science and Basic Energy Science. And thanks a lot for listening, and I'll be happy to answer any questions.
Thank you very much, Professor Aniruddha, for this nice talk and replying to all of you. Time now for one or two quick questions. Dr. Das, you want to ask some questions?
I have some questions, one or two questions, most probably looking into the economics of this technology. Hi, I'm Dr. Das from Ministry of Electronics and IT in New Delhi. In terms of wafer size and replacement of costlier wafer, do you have any structures that can show that diamond can work on non-semiconductor and cheaper substrates? And what should be the general size going into, let's say, 5 or 10 years that we should look at?
Yeah, I mean, if you're talking about polycrystalline, it's already available. Single crystal, of course, diamond is a different case. But a lot can be done even with the polycrystalline diamond technology. And, there are various companies which are really producing these diamond wafers, 4-inch, 6-inch, 8-inch diameter. In fact, the system that I mentioned at CNM can grow at 8-inch diameter substrate, and various non-conductive substrate can be deposited, with the diamond layer. Of course, each substrate you have to do some kind of a, engineering to really match nucleation density, also thermal mismatch. That's another thing to work on. But since we can deposit at lower temperature, use access to very different types of substrate that generally you can deposit because of the requirement of conventional CVD diamond environment, which is generally happens at 800 to 900 degrees Celsius. So I think polycrystalline, problem we can deposit on various substrates, large area, and there are many companies which are doing already, at a commercial scale with a price comparable to the SiO2 wafers. So that is not a, new now. The real challenge is really go towards a single crystal substrate, because as you know, diamond is very difficult to grow heat wave epitaxially. Diamond likes to grow on diamond, and that's the major challenge right now. Is how we can grow, diamond beyond, few to at least, inch and 2 inch. There are a few efforts going on in Japan where they use the stitching technique. They grow, seeds of the crystal with specific orientation, and then they attach each other and then simultaneously to grow a big seed crystal. And then you do the N implantation and lift off, and then you create, more template of these wafers. So create, I think lower defect density is another challenge, and a lot of work is being done. And I would say that there is a, lot of work going on quantum, research, and then the diamond envy centers is another interesting area. And that's because of the quantum. I think there is a renewed interest in growing single crystal diamond on large area. So I'm sure with few years, I think there are various groups working towards really growing a large area. And what I think Rob mentioned, that also goes towards use this kind of hybrid approach uh, that we can use to grow a larger area single crystal diamond. So that's the fundamental question that everybody really wants to see. Once you can grow a large area single crystal diamond, and then the power electronics and all other things really become accessible now.
Right. Thank you, Professor Suman. It was a lovely talk from your side. We appreciate it. Thank you.
Thank you.
Dr. Sumant, it was indeed a very excellent talk. They were given an excellent overview as well as the challenges involved in this area. Thank you so much for kickstarting the day with such a wonderful talk. Just want to have a quick understanding of two basic things. You said that to grow it on single crystals, to grow it on silicon, you require tungsten layer over there. And you also said that when you want to grow graphene over diamond, you require, if I'm right, you said nickel. So is there anything that dictates selecting this kind of metal layer, or it is just the epitaxy, or what's it?
Yeah, I think when I mentioned, on silicon, it's not a single crystal. If it is a single crystal on silicon, if I can grow diamond, that would be a breakthrough. I think I was describing the polycrystalline layer on silicon, with a different intermediate layer. I think the gallium nitride, I mentioned, the little tungsten layer that actually passivates gallium nitride. And then, that's how when you grow diamond, you can still keep the integrity of the gallium nitride layer. In case of, graphene on diamond, it's again the polycrystalline diamond, and then we deposit nickel. So there is a, catalytic reaction that happens with nickel and carbon. And nickel also a very good nucleating agent, for graphene. Uh, some of the things that I did not mention here, but the growth mechanism which is mentioned in this Nature Communication paper, because UNCD has a lot of grain boundaries, the nickel, diffuse through this grain boundary very rapidly. But while it diffuses, it does the, uh, you know, it does this as a nucleation agent for the graphene to grow. And then that's how suddenly, at instant, you get a growth of a graphene, and then the nickel goes away and then sits at the interface. So that's how you get top layer, which is completely graphene. and the down below, you have steel diamond.
Thank you so much.
Thank you so much, Professor Anirudh Sumant, for the nice talk. It was very informative and very good lecture, and we are going in the same direction. So now I also invite you to attend the talk of Professor Yuri Bogosti, who is now online. Professor Yuri, a very warm welcome to you. Very good morning to you from India. Let me just have a short introduction of you before you actually begin the talk. So, dear participants, we have the distinguished professor from Drexel University, Professor Yuri Bogosti, the father of vaccines. And today he is going to talk on the chemistry and application of 2D carbides and nitrides, mainly vaccines. So let me introduce Professor Yuri. Professor Yuri Bogosti is distinguished professor and Charles T. and Ruth Back Professor of Material Science and Engineering at Drexel University. He also serves as Director at Drexel Nanomaterials Institute. His research group works on 2D carbides, nanostructured carbon, and other nanomaterials for energy, water, and biomedical applications. He is one of the highly cited researchers in material science, and chemistry. He has received numerous awards for his research, including ACS Award, Somaya Award, ACS Edwin Award for Chemistry of Materials, European Carbon Association Award. He has been elected as a fellow of the American Association for Advancement of Science, Materials Society, American Ceramic Society, the Electrochemical Society, the Royal Society, and many more. He holds honorary doctorates from National Technical University of Ukraine, the National Academy of Sciences Ukraine, and the Paul Sabatel University in Toulouse, France. He had also served as on the MRS Board of Directors and is acting associate editor of ACS Nano. He has an edge index of 171. And over to you, the father of vaccines, Professor Yuri Bogosti.
Thank you very much for this kind introduction and invitation to speak today. Let me share my screen so that you can see my presentation. So I am going to talk about vaccines today. Since I'm a material scientist, my presentation will be focused more on materials aspects, but I'm going to talk also about optoelectronic applications, applications in communication technology, and some other electronic properties and applications of vaccines. But for people who are less familiar with the topic, first of all, what are the materials we're discussing here? Those are layers of metal and carbon or nitrogen atoms. You will see vaccine structures here in this image with red dots being metal, for example, titanium or moly atoms, connected by black dots, which are carbons or nitrogens. And there may be surface terminations on the surface here. Most of these materials are metallic. There are two-dimensional metals, which is actually rare in the field of 2D materials. You can see them come in a variety of different colors, and those are plasmonic colors. Right away, basically, enabling application of these materials in optics, plasmonics, and electronics here. So why are we interested in 2D materials in general? Because they offer a variety of properties. There are many insulating 2D materials like boronitride, for example, hexagonal boronitride, oxides. There are semiconducting materials. Transition metal dichalcogenides are good examples here. And semi-metals, for example, graphene, a zero band gap semiconductor, and of course, everyone is familiar with this material. But all the attention to graphene led also to interest to other 2D materials. And in addition to delaminating known van der Waals structure like hexagonal boron nitride, moly disulfide, and others, scientists also showed that it's possible to take materials which don't have layered van der Waals bonded precursors and still make 2D materials like silicene, germanium, metal organic frameworks, and others here. And these materials actually add to many different properties of 2D blocks. All of them pretty much are flexible. So if you talk about wearable, flexible, transparent electronics, you really need thin two-dimensional materials. But they also offer high specific surface area, which is important for adsorption, catalysis, surface reactions, energy storage. And among those materials, MXenes really appear to be largely missing blocks because, as I mentioned, there are many semiconducting, semi-metallic, insulating 2D materials. You have just heard an excellent talk about nanodiamond, which is not natural 2D, but is used a lot in thin films. But good metals were really missing. What is also very important, there are many great 2D materials. Graphene is a wonderful example, moly disulfide, boron nitride. But Andrew Geim and Kostya Novoselov, researchers who discovered new physics in graphene, very quickly themselves realized that pure graphene has certain limited amount of application, and the future really belongs to heterostructures. And what is wonderful about 2D materials? They are flat, they are planar. You can use them as building block and pile up basically layers of different materials, like it's shown here in van der Waals light emitting diode. Hexagonal boron nitride, graphene, boron nitride, transition metal dichalcogenides, and then you repeat again boron nitride, graphene, boron nitride stack here, creating a device with current collectors, semiconducting layers between, and dielectrics outside here. In a very similar way, we can combine graphene, transition metal oxide, two-dimensional MXene, dichalcogenides, other materials, black phosphorus, because 2D are like bricks on Lego stones. So you really can build structures, materials, entire devices with exact functions. Moreover, you can predict their properties here. And of course, if you want to build a new world, if you want to build world made now not by taking a piece of silicon or another semiconductor or metal and carving something out, but taking two-dimensional blocks and building whatever you need with whatever properties you need. You need many building blocks with various properties. And as I mentioned, materials with truly metallic properties, high density of states at the Fermi level, high mobility, and high concentration of carriers were really missing. Discovery of MXenes filled this gap, giving us pretty much all kinds of building blocks for creating technologies of the future. So what are those materials? Let's go a little bit further in depth, especially for people who are less familiar with the topic here. MXenes name comes from transition metal M, one of these red earlier transition metals. X stand for carbon and nitrogen, and suffix "in" was added to show their two-dimensionality, like a graphene, silicene, germanium, phosphorine, borophene, and other things here. So they were initially made by selectively etching layered carbides and nitrides known as MAX phases. A colleague of mine at Drexel University, Professor Michel Barzoum, with whom we have done initial studies of this family of material, is an expert in that field, kind of a father of MAX phase area. So you can look at MAX phases as carbide or nitride layers here, connected by monatomic layers of A element, one of this blue, aluminum, silicon, gallium, and others. What we did, using the technique of selective etching or dealloying, as some of you may know it here, we etched away this layer of A element, releasing two-dimensional sheets of carbides and nitrides, creating a new family of materials about 10 years ago, which first was titanium 3C2 carbide made, and after that, many others followed very quickly here. So MAX, if you remove A, you end up with M and X, you add suffix in, and those are MAXines. This is how they were born. And they produce nitrides, carbides, carbonitrides. They can have several different structures like shown here. They can have also single transition metal or multiple transition metal in the structure. What is important? Since there are strong bonds between the A element and M element, you cannot simply mechanically delaminate those layers. You have to etch them. But after you remove this element, and we can do it over 10, 20 micron distances, making 10, 20 micron flakes, there is a weak bonding between the layers. Surface of this material after removing of aluminum, for example, HF uses the first agent, but there are many, many methods and many agents known nowadays. We get with titanium carbide MAXins. And its surface will be terminated by oxygen, OH, fluorine, whatever is your etching agent. And now there are weak van der Waals or hydrogen bonds between the layers. So it's possible to intercalate the material and eliminate it just like you would do it to, say, graphene, graphene oxide, or other two-dimensional weakly bonded materials, ending up with 2D flakes of carbides, nitrides, carbonitrides with some surface terminations here. And surface termination is very important, and I will explain a bit later why. What is also very important for these materials? As you could see from the periodic table I showed, we have a dozen of transition metals which can show mixing. We have carbon or nitrogen or they mix in carbonitrides. We can have pure M element, and we can have M2C, M3C2, M4C3, say other structures. We can also make solid solutions. Solid solution on M side where we can randomly mix element. We can make partially ordered structures when one transition metal will be preferentially in the middle layer, another is in the outer layer. But we can also make atomic sandwiches with one metal, for example, moly on the surface, another one, for example, titanium in the middle. And if you look at more than 100 stoichiometric MAXins predicted, multiply at least by 10 by termination, oxygen, OH, halogens, chalcogens, sulfur, tellurium, chlorine, bromine, iodine, and add an infinite number of solid solutions. You end up with potentially the largest known family of 2D materials, or maybe even materials, inorganic materials in general here. So to summarize, we have this M2X, M3X2, M4X3 structure. We can make solid solution. We can make these atomic sandwiches, or more technical name would be out-of-plane ordered MAXins. We can also have in-plane ordered MAXins, where atomic columns of different elements alternate. And if, for example, yttrium or scandium and moly. And if you etch away yttrium or scandium, you end up with monoatomic lines of vacancies adding up in ordered divacancy MAXin. So basically, we push atomic engineering to the limit. We can design complex structure in two-dimensional space. And this discovery continues. Just a year ago, we published a new system of Mach phases and, of course, Mach-Synths made out of them with 5 layers of transition metal and 4 carbon layers. And if you add surface termination, you get 11 atomic layers. More important, every flake will have this number of layers. So we have confinement, we have properties determined by their thickness. There are many very thin 2D materials, but those have very distinct properties. So we greatly actually expand the variety of 2D materials and their properties ability. So basically, I'm leaving you with a message. We have a huge, enormous family of materials with diverse compositions, diverse structures, all constrained, all basically well-defined and controlled. Now, what can they do? What are the properties they offer? And DFT calculations predicted that all bare Mach-Synths would be metals. However, if you take, for example, M2C structure, put oxygen on the surface, pull in 2 electrons from each metal atom like titanium, you may end up opening a band gap. Some of them are predicted to be semiconductors, but again, I will be focusing on metallic properties today. They have been predicted to be some of them 2D magnets, especially chromium, manganese containing Mach-Synths, giant Zibek coefficients, so good thermoelectric properties in semiconducting Mach-Synths, high Hall mobility, Dirac fermions, so cones in their structure. Tunable chemical superconductivity was actually already demonstrated by Dmitry Talapin's group for niobium-2s. Also, ultra-low work function and topological insulator related to it, quantum spin Hall phase, and so on and so forth. Moreover, again, all these properties are largely controlled by transition metal, carbon, nitrogen, and surface termination, for example, oxygen, fluorine, and so on. And it has been predicted that, for example, magnetic properties can be controlled this way. Just to give you one example, this is the density of state of non-terminating titanium carbide Mach-Synth. You will see a high density of states at the Fermi level. If this material is terminated by fluorine atoms, the density of state decreases. And if we put oxygen and each oxygen pulls 2 electrons from titanium atoms, it's even possible to open the band gap here. Some of Mach-Synths have been predicted actually to have wider band gaps, but again, my focus today is on metallic Mach-Synths. And what is wonderful, titanium carbide Mach-Synth that you can see in these pictures looks to you probably like a regular 2D materials. This is about 20 micron large flake, but it's actually produced by solution processing. You can make graphene flakes of that size. You will never make, or at least I've never seen, moly disulfide, for example, or any other dichalcogenides flake, because they don't have sufficient strength. This shows this material very strong. You can look at the sum of the flakes in TM and you will see that they have regular hexagonal form inherited from max phase crystals. They're single crystalline, as you can see from electron diffraction and high resolution TM images here. But you can, of course, restock them into films, make layers. And this film, like the one shown in this SEM image, may have conductivity going up to, say, 20,000 Siemens per centimeter. If you take a reduced graphene oxide, you will see typically values 2 to 4,000 Siemens per centimeter after high temperature annealing. You need to go to like 3,000 degrees C to pretty much graphitize it to get 6,000 Siemens per centimeter. This is very conductive. But amazingly, because of surface termination, these flakes are hydrophilic. They have OH, oxygen on the surface, considering them to be conductive clay or hydrophilic, water-soluble metal. This is a very unusual combination of properties, considered to be graphene oxide and graphene combined together. Metallic conductivity, water solubility, no additives, no binder, no surfactant, nothing needed. And this makes processability great. And of course, they're transparent in thin film, come a variety of colors that I showed to you. They're stronger than all solution process 2D materials. Only perfect single crystals of boron nitride, graphene separated from single crystals, will basically have high modules and strengths here, plus many other exciting properties. And there are many other properties which have been predicted, need to be experimentally checked. There is one more important feature these MXenes offer. There have been probably more than 200 two-dimensional materials reported so far. Of those, just a handful can be made in any significant amounts for practical applications. MXenes are produced by solution processing. And as a result, even from day one, we were able to make gram quantities of materials. There are reactors now in our lab designed for us by a Materials Research Center in Ukraine, capable of making up to 100 gram per batch. You can see here a 50-gram batch of MXene and solution of MXene flakes, single layer flakes in water. And you can take this aqueous solution of flakes and by Dr. blading produce a micron thick film, which is actually stronger than aluminum foil, has strength of 570 megapascal. Actually, A is missing here, it should be MPa, and 15,000 Siemens per centimeter. Imagine you disperse powder in water. You concentrate solution to make it liquid crystalline, so you need to have certain concentration of flakes, and you basically Dr. blade film on the surface, dry. And you get materials that can serve, for example, the current collector in a battery, micron thin, 10 times thinner than metal foil. And I will talk about some other applications of these materials, and having very high strengths and very high conductivity. You can see, for example, this 1 micron thick film can hold this model metal car. But what is again is great. All this processing can be done from aqueous solution, not water-based, what people claim usually when they write about aqueous inks. It doesn't really have surfactant or binders or additives or modifiers. It is just water and MXene flakes. And you can inkjet print them, 3D print them, spin coat, spray coat, do monolayer interfacial assembly, anything you can imagine pretty much here. And of course, if you have a colloidal solution of two-dimensional flakes, you can control flake size. I don't want to go into details. You can separate flakes into different sizes by density gradient and get flakes of different sizes. You can assemble them into films. And again, if you make a liquid crystalline solution by increasing concentrations that flakes cannot freely rotate, you will get a pneumatic liquid crystal, and you can either make films or even draw fibers, pure MXene fibers with high conductivity and attractive properties for many applications like functional textiles, smart textiles, electronic embedded in textiles. Of course, when we talk about electronic properties of these materials, we need to consider intrinsic intraflake transport, which is metallic, and carriers are electrons of transition metals. But also we need to consider interflake transport between the flakes. For example, if I have a multi-layer film like I'm showing here, there are, of course, thousands and thousands of flakes. But if you look at the single flakes, at room temperature, you will see a linear IV dependence. So these materials behave like metals. But if you look at the temperature dependence of conductivity, you will see that actually assembled films with multiple flakes in many cases behave like semiconductors. Many MXene titanium 332 other will behave like a metal, and then you will have increase in resistance, change in the slope because of defects in the structure here. But much of this is related to intercalated molecules between 2D layers or surface termination. For example, if you anneal molycarbide MXene, you will see like at least 2, even 3 orders of magnitude decrease in resistivity. But for example, the dependent still character of the dependence remains the same. For some other MXene, situation is different. We did experiments annealing titanium carbide MXene in vacuum of electron microscope, and you will see that with decreasing temperature, resistance decreases. So after synthesis and even after annealing to 750 degrees C, you always observe metallic behavior. However, if we go to other MXenes, titanium carbonitride, moly titanium carbide, they initially show semiconductor-like behavior. So the slope of temperature dependence of a resistance is different, but when you remove surface terminations and intercalated molecule, it can actually change to metallic like in titanium 332. So we have a surface chemistry control electronic properties here. The same is true for many other properties. For example, for work function. As we anneal materials, removing hydroxyl group, work function increases from 3.9 to 4.9 electron volt. We continue further annealing, we remove fluorine, work function decreases. And this is actually in a very good agreement with DFT prediction, with OH terminated MXenes having the lowest work function and oxygen terminated material having the highest work function. Same is true for many other properties of MXenes. For example, when people talk about nanotechnology, nanoscience, a classical example given of the oldest nanotechnology is this Lycurgus cup from the 4th century Roman work, which is red in transmission but green in reflection. If you look at MXenes, titanium 2C, for example, shows similar behavior. This is a foil, and in reflection, it is green. In transmission, it is wine red color. But titanium 332 will have green color in transmission, and this violet in reflection, and so on. And you can get almost any combination of colors because these materials are plasmonic. And these peaks, you will see plasmon resonance peaks, depending on the composition, structure, number of layers, cover pretty much the entire visible and infrared range here. And in case of 2D materials, there is a confinement in plane. So transverse plasmons will have certain position fixed by the thickness of this layer, and we know the number of atoms in all the layers is the same. So we have a material with plasmonic colors determined by its structure. So titanium 332 will have plasmon resonance transverse surface plasmon at about 800 nanometers. And my student, Kathleen Maleski, did study on many different MXenes. Titanium 2C actually will have plasmon resonance peak shifted to about 550 nanometers. And if you go to V2C, plasmon resonance transfer plasmon will be shifting towards UV range here. But we can do even better than that. We can actually do fine tuning by changing composition. Remember, I talked about solid solution in the beginning. We can change amount of, say, titanium and vanadium or titanium niobium in the system. And we can finely tune position of plasmon resonance and optical absorption. For example, with increasing amount of titanium, we will be increasing absorption in the visible range and shifting the plasmon resonance peak towards a longer wavelengths. And increasing amount of niobium will increase absorption in the infrared range. Moreover, while 2D materials have already been shown to have very attractive optical application in different wavelengths, MXenes can cover actually entire wavelength range in strong interaction with electromagnetic waves from UV to microwaves, radio waves over terahertz, infrared, and visible range. As a result, it leads to a large variety of optoelectronic applications here. So, as we know electronic properties, we know optical properties, we know how to control them by controlling number of transition metal carbon layers, composition, type of transition metal, carbon, nitrogen, mix of carbon and nitrogen, and surface termination. We can finely tune all those properties to meet the requirement in specific application. And this is truly unique for this material system. As a result, we can have a range of application from spintronics to electrochromic coatings, interconnects, electromagnetic interference shielding. I'll talk about it further in depth. We can make RFID tags and antennas. MXene, and this paper was actually just published like last week in Matter with colleagues from University of Nebraska-Lincoln, showing this metallic conductivity of MXene and very high breakdown current density. You just heard in the presentation of Dr. Aniruddha Sumant about very good performance of graphene on diamond. This is on silicon dioxide coated silicon wafer. So probably it will go even higher, but it's already, of course, a couple of order of magnitude better than copper and challenging performance of graphene in that application here. And moreover, we can further tune the properties electrochemically by, for example, injecting charge. If we take titanium-332 MXene with plasma resonance, you may remember at 800 nanometer roughly, and apply just 1 volt negative voltage in electrolyte, gel electrolyte environment, we can switch it from green color film in transmittance to blue color. We shift plasma resonance peak, but 170 nanometer with just 1 volt application. So basically, the message I am going to deliver here is that those materials are truly tunable. And of course, based on their properties, we can consider a number of applications. For example, they very well compete with ITO in transparent electrodes for LEDs. You will see this pretty much analogous performance, current efficiency when you use ITO or titanium carbide film. But MXene films can be produced in solution and put onto any surface. They don't have indium, so it's just titanium and carbon, abandoned common elements. And they're flexible. They don't break. You can bend them. You can pretty much load them to a much larger extent, stretch, and they keep their conductivity. Again, unlike ITO films. There are many other applications, and I'm not going to go in detail. I know we started already later, and I want to put you back on schedule to the extent possible here. But I will give you a few examples. For example, because of metallic conductivity, gas sensors made of MXene, based on adsorption of MXene, of gas molecule MXene, or intercalation between the layers, they give you a very low noise ratio because they're conductive, but very high signal for gas molecules adsorption here. And again, this was a major paradigm change because traditionally semiconducting materials are used in gas sensors and they needed to be heated to a couple of 100 degrees to show sufficient conductivity. So we get simpler devices with better performance. In electromagnetic interference shielding, where we published this paper in 2016, it was really breakthrough in EMS shielding. We showed that material with a couple of order of magnitude lower conductivity than copper or aluminum was nicely lining up in the ability to protect electronics from electromagnetic interference. Moreover, to reach 50 decibel, so 99.999% shielding efficiency protection here. It's sufficient to have just a micron or two thick titanium carbide film, replacing a 15-20 micron metal foil that is traditionally used, making much lighter, thinner devices. Moreover, to get to 20 nanometer, this is sufficient, 20 decibel, 99%, which is sufficient for a number of applications. It's a 40 nanometer film can do this job. And 1 micron film, as I showed you before, it can be freestanding, unlike metal film of the same thickness, compared to 2 millimeter thick composite materials used for MI shielding. Moreover, what we discovered in a late publication last year, the titanium carbonitride, which is actually has a lower conductivity than titanium 32, not only performs better, it outperforms metal in its electromagnetic interference shielding ability, pretty much breaking all the rules and showing that discrete two-dimensional layers have non-trivial interaction with electromagnetic waves, which still needs fundamental understanding. But it really opens new avenues in providing ultra-thin electromagnetic interference shielding for flexible, wearable, microscale electronics for small devices of the future. And again, we can easily reach 50 decibel with films which are an order of magnitude thinner at least than graphene, and 20 decibel can be reached with, again, nanometer thin films here. By the same token, we can use these materials for communication technology in antennas. 2 years ago, we showed in this article that actually titanium carbide MXene has a lower attenuation losses compared to other materials in transmission line testing here. More recently, we published a paper showing that if you make antennas, patch antennas, they actually challenge copper and show very good performance, not only in the anechoic chamber, but also in open range testing. Moreover, they really, if you compare radiation efficiency and thickness, show really record performances. And MXene antennas having only 15% of thickness and 7% of the weight of a copper antenna shows pretty much the same performance here. And we assembled patch arrays and tested them in let's say 28 gigahertz, and this is target frequency for 5G applications. You can also use these materials, of course, to make RFID tags. So from the first attempt, we make RFID tags reaching to about 8 meters distance here. And again, I'm talking not about materials which have been optimized, which received billions of dollars of funding like graphene, where thousands of people have been working on improving every properties. I'm talking about the first results. So what it means that there is plenty of room for improvement. And all this diversity of MXene properties makes some scientists like Hussam Al-Sharif from KAUST talk about emergence of a new field of electronics that he calls maxitronics. Basically, it's a MXene-enabled electronic photonic devices because of such a variety of compositions and structures, variety of properties that can be controlled by surface charges, intercalation, functional groups on the surface, ability to tune work function, band structure. Again, considering to be metals with a tunable Fermi level, which you can shift, not like a gold, for example. When you have a metal that's metal, you inject charges, you can basically shift the Fermi level. You can shift their plasmonic properties, as you see, work function, other properties here. And of course, with all this variety of electronic, magnetic, plasmonic, spintronic properties, application are possible. And first of all, again, whenever you need transparent, thin film, flexible devices, MXenes can offer advantages. Of course, there are many other applications. I don't have time to talk today. Particularly in my group, we work a lot on electrochemical energy storage application of MXenes, batteries and supercapacitors. And again, if you want to achieve high energy and high power density, you need materials which are capable of transporting ions, and this is what 2D galleries between the layers give you, transporting electrons, and this is what those layers of transition metal can give you. No solid state diffusion, because this is not a bulk material. But because of transition metal surfaces, it's possible to transfer electrons, reduce and oxidize reversibly transition metal on the surface, storing energy like in a battery, but with a rate of electrochemical capacitors, potentially reaching to the range when we have batteries capable of charging in a very short time. And we showed that for electrochemical capacitor or pseudocapacitors that combine double layer and redox storage, shown by this peak in the cyclical tomogram, we can actually do redox energy storage at rates going to hundreds of volts per second. So basically within milliseconds, we can enable redox energy storage in those materials here. And of course, you can actually make this battery embedded in a textile and again have wearable energy storage device here. So I hope I gave you an idea of what this family of materials can do. Of course, we have a very large number of materials potentially. So far, about 30 stoichiometric composition of MXenes have been demonstrated. Another 15-20 solid solutions have been reported. This is a small subset from hundreds of possible structures, from infinite number virtually of solid solution, multi-element MXenes that can be made. Of course, we need guidance from computational science. We need guidance from DFT regarding properties, which MXene to select, how to combine different MXene, and how to build devices combining MXene with semiconducting and dielectric materials, building multi-layer hybrid structures here. But we believe the future is very bright for this large family of materials here. And of course, many other applications are emerging. If you want to read about basics of this material, this review article we published in 2017 is a good starting point. But of course, there have been many developments in the last 3 years. I talked a little bit today about electromagnetic interference shielding antennas, some of the electronic applications, but of course, memory devices, memristors, spintronics, transistors are very promising. I didn't even mention catalytic and electrocatalytic applications, biomedical application, including medical electrodes, implantable and epidermal electronics, biosensing, dialysis here, optical application from LEDs to femtosecond and random lasers to surface-enhanced Raman spectroscopy, photonics, plasmonics, electrochromic coatings here. And of course, sensing, gas strain sensing, moisture sensing, electrochemical sensing. And of course, you can also not just make hybrid materials, but you can incorporate MXene into polymers, metal or ceramic matrices, creating composite materials, reinforcing their matrices, providing electronic conductivity to ceramic or polymer materials here. And of course, pretty much every single type of batteries, electrochemical capacitors, energy storage, but also energy harvesting devices like triboelectric nanogenerators. So we have a new family of materials to work with. They are already being explored in many applications. They are scalable. Many of them are made of earth-abundant elements like titanium, carbon, oxygen, moly, niobium. So that can be produced at scale and hopefully at a moderate cost in the future. If you want to learn more about these materials, we will be offering a week-long course on vaccines last week of March. You can go to my website to find a registration site for this course. Please consider it. And this is my very last slide. Of course, work I've done was possible because of an excellent group of researchers, excellent PhD students, postdocs, visiting scientists. This is my group. Of course, not this year picture because of pandemic. We were not able to get for a party together. It's in my house. A year ago, we have students from many different countries, including, of course, India, but also Turkey, Russia, Thailand, China, Ukraine, and France, and others here. Really, world-class research requires efforts of people from all over the world, and research is really on vaccine is going on in almost 100 countries all over the world nowadays. We collaborate with many outstanding researchers in many different countries. We also even receive funding from international sources in addition to US funding agencies here. But again, we're still in the very beginning of the road. Compared to graphene, vaccine, in spite, we have like 1,000 times more compositions possible, received maybe like a tenth of a percent of graphene funding. So with proper efforts and investments, we believe there are great opportunities, and especially for younger people in the room, students, postdocs. If you're looking about a research area to explore, look at vaccines more closely. If you're working on electronic application, electronic devices, consider where you can use them, how they can help you to achieve breakthroughs in science and technology. And with this, I'm going to stop. Thank you very much for your attention. I'll be glad to take questions.
Dr. Yuri, Professor Yuri, thanks for the very inspiring and very encouraging talk. Time for a few quick questions. Dr. B. Kumar sir from Trishur. He has, I think, some question. Are you online, Kumar sir?
Yeah, good morning, Professor Gogotsi. It was an excellent lecture. I enjoyed it thoroughly. I would like to ask you one very simple question. That is, your vaccine is, the surface is so reactive. You have so many reactive species on the surface. At the same time, you have also been able to selectively terminate it with OH and EF. So how do you control this selective reactivity or selective terminations of the?
Well, basically, vaccine picks whatever is in the synthesis environment, or you can exchange it terminationally. But actually, this is what makes material stable. If you take, for example, two-dimensional non-terminated vaccine and take it out in air, it will basically can even burn in air. It may become pyrophoric, just like, say, electrolytes, because transition metal, which has free electron to share, will immediately and very quickly and exothermally react. But when it is surface, slowly during synthesis, terminated by either oxygen or chlorine or sulfur, you basically passivate the surface. So actually, this surface termination exactly gives stability to vaccines. And initially, people reported vaccine degrading after a couple of weeks here, but we know nowadays that even single layer flake in solution of titanium-332, niobium-463 can stay in water for almost a year at room temperature, single layer flakes. As soon as you assemble them into a film, we have films being stored for years with very little change in properties. We made vaccine textile, I showed you, for example, in supercapacitors here. And my student washed them like a 50 cycles at temperature going up to 80 degrees C with just 3% of weight loss and several percent only in conductivity change of this material, things here. So this surface termination really stabilize MXenes. And again, all work we do with them, we do without any protective environment in lab air.
Thank you.
Let's have a quick question from one participant. Dr. Ganesh Hikavale, can you hear me?
Hi.
Dr. Ganesh, you can ask the question to Yuri.
Hi, Yuri.
Hi.
Hi, how are you? Excellent talk and nice to hear you after a long time. I was very fortunate to work with you and your MXene material in my past projects. So my question is there any chance we can make an electrical conductive tissue engineering scaffolds for like neural stem cell differentiation, like for biomedical applications?
Look, I think so. Titanium carbide and a number of other MXenes are biocompatible. And we work, for example, with Flavia Vitale from University of Pennsylvania, who develops implantable electrodes for brain. And MXene show better, actually, sensitivity compared to gold electrodes because of better impedance matching, we believe here. So what it means, and also there are papers from other groups we're not involved, showing use of MXenes as scaffold in tissue engineering and cell growth and proliferation osteoblast cells on MXenes. So I believe things like this are definitely possible. And if you look also at the diagram I showed on properties and application, very first papers on any biomedical application of MXene appeared just like 3 years ago, 2017. So it's still a very new field. And most of this work was related actually to photothermal therapy for cancer treatment or things here. So again, growing scaffold, controlling basically neural network and so on. I think this is an exciting area for applications, but again, it requires work and exploration.
Exactly. Thank you, Yuri.
My pleasure.
Over to Director Hyderabad for a quick question. Ratish sir, can you hear me?
Yeah. Professor Yuri, thanks a lot for the excellent talk. Only thing which I want to ask you, you have mentioned about molybdenum, vanadium carbide and materials like that. What is the stability of these materials? Like they are hydrophilic in nature or?
Yes, basically again, stability depends on the composition. And also on the thickness. So layers which have thicker, like a number, like a 3, 4, 5 layer of transition metal are in general more stable compared to M2C structures. And also titanium, niobium, for example, carbides are more stable than say vanadium. But if you make an alloy, for example, vanadium titanium, the stability, chemical stability, greatly increases. And also, of course, it depends on the particle size. Larger particle, more stable. Fewer point defects, higher stoichiometry, more stable. So again, it's definitely possible to make MXene. When you assemble them in a film and dry, they have high stability. When you process them, you really need to be careful. Just ensure that you have a high quality material with good stoichiometry, with fewer defects. So it is controllable.
Is there any possibility of giving any hydrophobic coating, like without affecting the properties?
Well, it's possible to give hydrophobic coatings. So MXene have been made hydrophobic by depositing molecules on the surface, grafting basically some molecules on the surface. And the goal was to make them soluble in hydrophobic non-polar solvents, because MXenes are soluble in water or polar solvents. So these coatings have made. However, unfortunately, pretty much every coating you make for the assembly will have effect because now you have some molecules between the surfaces. This is a common issue in semiconductor particles, nanoparticles, when people graft some molecules on the surface to stabilize them, to assemble them. However, what is also interesting, said that if you look at MXenes, you can modify the outer layer, but there are very little changes in the inner layer. So while you can change inter-particle transport, interlayer transport, intra-layer properties may actually stay the same. So you may still keep the same optical properties, same electronic properties, and conductivity. Because even if you do redox processes reversible on the surface, we have moderate effect in these thicker structures on conductivity here. So therefore, short answer would be depends on what properties you're looking for. You will either change them or not by making MXene hydrophobic.
Thank you.
Professor Yuri, thanks for the good lecture and a lot of applications of the magazines. I would like to, I have one query about the sodium-ion battery. Actually, we use this T3 in the Ti3 in the as the anode for the sodium-ion battery. Whether it is stable, where it will give some number of cycles less, or it is a capacity fading with observing?
It's actually very stable. Moreover, MXenes have been tested in lithium-ion, sodium-ion, potassium-ion, magnesium, aluminum, zinc-ion batteries, in lithium, sodium, potassium, sulfur batteries here. And what they give primarily is high conductivity. Also in metal batteries, they suppress dendrite growth, and metal sulfur batteries, they adsorb polysulfide strongly here. But like everything else, you need to design electrode architecture, because if you pile up flakes and make a very long diffusion path for anions, you can build a thick electrode. So electrode architecture design is important. Second, if you have a non-aqueous system, you can use it in anodes and cathodes. However, in aqueous system, MXene work very well on a negative electrode, but can be oxidized under high anodic potentials. And finally, in battery electrodes, you need to think of ACI and also interaction with electrolytes, because as we showed for titanium carbide MXene and lithium ion systems, solvents, which are very good, say, for carbon electrodes, may not be necessarily the best for MXenes. So again, you need to look at a battery as a system, finding not only optimum electrode material, but matching it to electrolyte to achieve real success. But last thing I wanted to mention about batteries, people pay a lot of attention to active materials. However, by making much thinner current collectors, by eliminating polymer binder, you can make MXene electrodes which are binderless and current collectorless. You can actually save more in energy efficiency, density per volume of weight by doing this compared to just increasing capacity or capacitance numbers here. And I think this is what is important to consider for people who consider use of those materials in battery. Because of this metallic conductivity, it really enables things that conventional materials cannot do.
So you mean to say it will be useful for flexible batteries or?
Absolutely. Well, again, you know, first thing is here, if you want to make out of MXene a battery for Tesla car or an Indian analog, you need a lot of material. Today, no one still makes it in this quantity.
Yes.
If you want to make a flexible, transferable, wearable battery, you have to use materials which are 1 or 2 dimensional. And here, for these thinner devices, MXenes are offering great opportunity today. And again, you make a battery without current collector, which will be flexible. And this is right away an advantageous application.
Thank you so much.
You're most
Okay, let's
welcome.
have a quick question from Professor Sulba Kulkarni. Professor Sulba Kulkarni, can you hear us? Ask your question.
I can hear you. Can you hear me?
Yeah,
Yes.
we can hear you.
Yeah. Thank you, Professor Yuri, for a wonderful talk. I just was curious whether it is possible to have piezo devices using vaccines.
What kind of devices?
Piezoelectric.
Piezoelectric. I don't know. Actually, one of my students asked me exactly this question in a discussion yesterday. There are theoretical predictions that vaccines, actually, you can look at vaccine structure as a 1-1-1 slice of a sodium chloride cubic structure.
Okay.
For cubic materials, you should not have piezoelectricity. However, since you open the surfaces and relax atom, actually you have deformation of the lattice. And there are computational studies predicting piezoelectricity in vaccines. So far, I have not seen any experimental verification. So it's one of the properties still to be checked experimentally.
Okay. Because I think that because the flexibility is there, it should be also possible. At least one property is taken care of. And as you said, there are some theoretical predictions. So I think there is a scope for this kind of property to explore.
Yeah. It's possible again to be shown. What has been shown, of course, that you can intercalate ions and molecules between these layers, changing lattice spacing and basically slower than the conventional piezoelectric, but doing significant dimensional changes. It has been used in soft robotics, in actuators based on vaccines, intercalation of ions and molecules.
Okay.
One last question, Dr. Prasad Rao. I think he's not here. So with this, I thank Professor Yuri Gogosti for his thrilling, enthusiastic, very inspiring and very new discovery of vaccine materials. Sir, I wish you all the best for the Nobel Prize. And I'm sure that you will make it to the Nobel Prize and you have done a fantastic work.
Okay, thank
you.
Thank you for
great wishes. And again, I wish you a very productive conference, everyone. Goodbye.
Thank you so much, sir. Thank you so much. Okay, bye-bye, sir. Good day. Thank you. Now I hand over to my friend Dr. Sudhir Argo, the co-convener of the conference, for conducting the next session.
Good morning all. Myself Dr. Sudhir Argo, welcome you all to the third lecture of this session. So Dr. Michael D. Irving is going to talk on de-risking metal halide perovskite semiconductor for solar photovoltaic applications. Michael D. Irving is PhD, currently working as a CTO of Hunt Perovskite Technologies, where he focuses on the development of metal halide perovskite materials and their applications in solar photovoltaics. Dr. Irving received a BA in chemistry in 2003 from Texas A&M and PhD in inorganic chemistry from Northwestern University in 2009. Dr. Irving currently holds 30 granted US patents and over 50 granted international patents and has 18 publications. I welcome Dr. Michael Irving. Dr. Michael, please.
Please, it is disconnected. Thank you, sir. And so happy to be here. And thank you, Dr. Kale, so much for the invitation. So tonight, or excuse me, this morning for y'all, tonight for me here in Texas, I want to speak a little bit about our company in perovskites, metal halide perovskites. It's something that I imagine a lot of y'all are already familiar with. But us as a company, we've been in the public eye for about a year now. We've been around since 2014, but we came out of stealth mode right at about a year ago in 2020. And we focus on developing the metal halide perovskite material and the devices thereof. Our primary application right now is on single junction utility scale perovskite solar cells. Our claims to fame, or kind of our direction, is focusing on the material's durability. It's known to be a easily processable, efficient material, but lacks durability. And this has been our focus since inception of the company. And we were the first to synthesize the most stable form of perovskite, FAPBI3, formamidinium lead iodide, in the cubic structure. We're also an earlier adopter of the most stable perovskite structure, be that PIN architecture in the planar arrangement. As mentioned, we have one of the largest patent portfolios in the perovskite PV space. We're at least top 3 internationally and the largest in the US. We have a bespoke facility built in downtown Dallas, of which we operate from. Quick kind of taste of the company. It's a company, right? So what do you think about what we do versus maybe an academic lab does? How does that compare? How does that contrast? And I think you'd be surprised by some of the similarities. So first and foremost, we do lots of synthetic chemistry. As mentioned, I'm an inorganic chemist, and that sways a lot of my approaches. And so as it's shown here on this slide as an example, we're doing synthetic chemistry of the electron selective layer based on a nanocrystal extraction layer. We also do instrumentation design and development. A lot of the things that we need are not available commercially. We have to design and construct them. So this is kind of a neat diagram one of my guys, Jesus, made for me, where it shows kind of napkin sketch. Then we do the design in SolidWorks and then actually construct the instrument. In this case here, this is an electroluminescence and photoluminescence imaging tool. We rely on rapid and automated device analysis. We make a lot of devices, I think far more than an academic institution normally would. So we have developed systems internally that allow us to do rapid durability testing, as well as chucks and different ways to contact and measure the cells to allow for rapid assessment of performance characteristics in addition to durability characteristics. Further, we focus on slot die coating. So we're developing, we have a commercial slot die coating tool on which we do development. And this is our tool of choice in terms of long-term manufacture. We feel that once the perovskite goes into production, this is the tool we'll want to use in manufacture. And then last, automated 3D and 2D data analyses. So we do lots, we have software engineers, we do lots of software development instead of just doing all of our workups by hand, allowing us to do machine learning, to do data correlation analyses, really kind of critical, but move quickly. And computational analysis and planning. So trying to be more educated in how we approach our problems. We do a lot of density functional theory work along with kinetic Monte Carlo simulations to help us better understand the perovskite system on a computational basis, right, on a theoretical basis. So we can understand some problems in very high throughput calculation, computer-based analyses, and then use those to inform our empirical experiments. Now to business on the company. So again, I'm certain many of y'all are very familiar with perovskite. Perovskite, of course, is a crystalline structure represented in the bottom right-hand corner there, typically of the stoichiometry ABX3, where A is an organic cation, B is the metal center, and X is an anion, typically a halide. Now, based on these commonalities of perovskite, what does perovskite mean to us, to HPT as a company? We see it as a revolutionary new class of ink-based, printable yet high-performance semiconductor. So I like to use this example because those are two things that have never coexisted before. Ink-based printable system that is also high performance. So high performance has been done before with, say, gallium arsenide. Ink-based printable has been done before with OPVs, organic photovoltaics, but never together have these two properties coexisted. And what does this yield from a commercial perspective? Well, utilizing additive manufacturing, otherwise known as 3D printing, if you leverage those two things together, the printable semiconductor and additive manufacturing, this results in a very low cost to construct a plant, or the CapEx, capital expenditure, of less than 9 cents US per watt, or less than 9 cents per watt for the full cost of the panel. Most of the cost of the panel, of course, is the glass. To make a glass panel, the perovskite material itself is almost free on a per meter squared basis. One of the more interesting characteristics is not just the cost, but also the size. So we calculate about 100 square feet, or 9.3 meters squared per megawatt. For reference, this is 1/10 of the size of First Solar's most recent facility constructed in Ohio in the US. So this is a very small footprint, and this is oftentimes, as we see it, by virtue of the printing process. The printer itself is just smaller than larger scale deposition tools, vapor deposition tools. So this allows for a very small factory. This also results in high throughput manufacturing. And of course, the perovskite itself, all the materials contained therein are all inexpensive and readily available. Just carbon, hydrogen, nitrogen, lead, and iodide. There's nothing else, nothing really exotic in there whatsoever. Everything's readily available. And one of the things I like to reference is that even in the case of silicon, there's mining. Batteries, right? You mine for cobalt, you mine for lithium, you strip mine for lithium, a very ugly process, very, very ugly. With perovskites, all you need is 1/10 of 1% of the lead that's currently in the recycling stream. So you don't have to mine for it, just in the recycling stream. It can make 1 terawatt of solar panels per year, per annum. This is a very important aspect of being green and clean going into the future. Not just something that's renewable or considered renewable, considered safe, or whatever. We got to think about how we access the materials to construct the product. So when I say printed and I say additive manufacturing, what do I mean? Well, we approach this from a soft die coating technique, as I mentioned in the very beginning of the talk. And the basic rundown of that is you would take a glass conductive substrate, print the whole selective contact. Then you print a perovskite precursor, of which you anneal and form the perovskite in situ. Then you can print the electron selective contact and finish up the device with metal electrode or transparent oxide electrode evaporation. And then you package it up with a second piece of glass, laminate, and an edge seal, kind of a standard hermetic package. And that's how you would make it on, a smaller scale, but also in manufacture. The architecture is also indicated here on the right. It's all in order as we described, but this is what represents the PIN supposed architecture. We have the P contact layer, the intrinsic perovskite semiconductor, and the N-type electron selective contact. Now, of all the wonders and virtues of perovskites, there's a big, big issue, right? There's a big obstacle to be overcome, and that's durability. I like to recollect that when I first made the perovskite devices, we got to a high efficiency very quickly. Within a couple of months in 2014, long before the academic groups, we were able to hit over 18%, 18.5 is what we peaked out. The problem is in the course of testing, I could scan the device a few times and get 18.5%. And then maybe the 10th time I would get 18. On the 20th scan, maybe I've got 17, and so on and so forth. It would hold up for a while, but then the perovskite source cell would rapidly decompose. At which point we knew that the efficiency promise was real, right? This is kind of the basis of perovskite as it was being derived in 2012 and 13, primarily after Miyazaki's, PV discovery in 2009. We knew that if we wanted this to be a commercial material, that the durability problem had to be solved. And to solve it, we had an approach that was fundamental, concept of building on the rock. So kind of break that into two parts. We have materials level durability, and we have device level durability. The major focus, as I said, I'm biased. I'm an inorganic chemist, and so composition of matter is kind of the main focus. But composition matter is by virtue of the ink chemistry, meaning that we say we're going to print these devices, correct? We print them, and then we wish to form the perovskite from the printed ink in situ, and in situ polycrystalline thin film formation. The ink chemistry has to be very specific. It has to be robust. It has to allow for proper kinetics of the perovskite crystalline growth to achieve a high quality material, or these compositions of matter that we find so desirable. This patent here ending in 396, this is the reference to the formimindium lead iodide in the cubic structure. That's kind of our keystone patent, and we center a lot of our chemistry around. Now, once we develop the right perovskite system, perovskites, as many of you may know, are ionic in nature. And by virtue of their ionic nature, they have unique properties like ion migration, for example, that matrix solids, covalent systems do not. And so we have to design very specific contact layers and device architectures around this ionic nature. So it's not really a problem per se, maybe something that was perceived that way in the beginning of the work, that the ionic nature was a problem. But once properly harnessed, the ionic nature of perovskite actually is a virtue. I'll show one example of this later on today. Also, metrology and testing. So we have made the assumption that the perovskite material or perovskite solar cell will need its own unique metrology. Silicon metrology or other thin film metrologies will not be adequate. That's maybe an over assumption, but that is our assumption. So we make sure that we're developing the right tools along the way, including high throughput durability testing. I showed some indications of that at the beginning of the talk, but we had to design a system that could do rapid and active 24 hours a day, 7 days a week durability testing for accelerated lifetime measurements. Now, so a taste of our durability results to date. So what we have done is we set a bar for ourselves of 90% retained power after 1,000 hours. We focused on 4 primary tests: heat, damp heat, UV light plus heat, and light plus heat. Now, the most important test, in my opinion, is this last one here. The damp heat, damp can be packaged out, but we were able to still pass that test. Light and heat are 2 things you can't package out, no matter what you do. And I say package out because all these tests were performed on non-hermetically sealed devices, meaning, yeah, they still had a piece of glass on top. That's mostly for mechanical protection, for scratches and handling. The perovskite and all the contact layers, the metal and what have you, are all fully accessible from the sides. And if you're familiar with devices like this, the water permeability or oxygen permeability rates are quite high, even across the lateral. And so I mentioned that is important because this damp heat test was passed in this architecture, and then we can further package this up in standard hermetic seal type packaging with an edge seal, what have you, and get even better performance than damp heat. But light and heat you can't package out. And so we're taking an Arrhenius approach based on this 1 sun at 75C measurement and applying that to determine long-term lifetime. And that's something that's currently in the works in our facility. Kind of a taste of the data. So this shows more or less linear degradation of the perovskite device under the damp heat, or the light, light heat conditions. We have 90% and 80% demarcation lines. Of course, these are some of our selected heroes. We have some that just do this, but that's also, of course, numerous variables, right? It's the best devices of the best design. Those are the ones that graduate up from an experimental device to our standard procedure, the ones that do the absolute best, and that's what's represented here. Now, when we first started, the hypothesis was we knew that perovskite existed, right? Somebody had done it before, but was perovskite a viable semiconductor in PV applications? Principally utility scale. Utility scale, it's just out there in a field, it's unprotected. Can it survive? Will it function well over a 20+ year lifetime? And so I'll draw your attention to this external quantum efficiency or spectral response set of plots here. And so this shows the solid lines are the EQE measurement before the durability testing, and the dashed lines are after the durability testing. And if there were a perovskite decomposition during the durability testing or accelerated lifetime testing process, you would see dramatic change in the shape of the spectrum. Here we do not. The before and the after are superimposable, meaning despite the fact we see degradation in the process, the perovskite material is maintained. And thus, the degradation is occurring in principle elsewhere in the device. So this is great, right? If the device itself has issues, those are all solvable engineering problems. But we answered the primary question: is perovskite viable in PV applications? And I think the answer is absolutely yes. So an example of more of the materials level durability test that we've done previously. So this is a collaboration we did with Colorado School of Mines, looking at under an environmental XPS system that they purchased. What is the effect of stoichiometry on durability? So in this case here, we have a lead iodide ratio near stoichiometric, so 2.8 to 1, and then super stoichiometric or in excess, 3.8 to 1 lead to iodide. And you can see here in the blue, yes, that's the beginning perovskite system or signal in the XPS measurement. And as you can see quickly, it decomposes over time over the course of 350 minutes. So rapid decomposition of the perovskite system when the iodide, the iodide is in excess of lead, in excess of the stoichiometric 3 to 1 ratio. But when you're near stoichiometric, we don't see this rapid decomposition. Now, we believe a lot of this decomposition is due to the X-rays itself. X-ray can actually decompose perovskite, but it has to be driven by something. And we come to believe that it is excess iodide that results in triiodide. And this triiodide molecule then, not initiates, but, it's written as a catalytic reaction, not really quite catalytic, but let's call it a catalytic reaction, where we are degrading it through the triiodide formation. Another bit here, we show pictures of the perovskite thin films. This is the pure formamidinium lead iodide here on the first row. We put it in a damp heat oven for 1,000 hours, and we see what happens. Right, so for the pure perovskite, around 200 hours, the perovskite is really starting to decompose, and after that, it's more or less gone. The perovskite under these conditions decomposes from FAPBI3 into pure lead iodide, indicated here in the yellow. Now, with the increasing addition of an additive, I can't tell you what the additive is, but it's not cesium. I'll just say that. As we increase the concentration of the additive to the optimal amount here, you can see after 1,000 hours, the perovskite persists. And it's very important to note that the perovskite thin film here is fully unprotected. There's nothing at all on top of it. It's just inside these very nasty 85C, 55% relative humidity conditions. And it survives. By spectroscopy, 96% of the perovskite persisted, with almost within the measurement error of the tool after this 1,000 hours. Now you do see a color change, and that's due to mass translation. The perovskite, when it's unprotected under these conditions, it likes to coalesce into mounds, and that's why it has kind of a lighter color, but all the perovskite is still there. It does persist. Another thing we wanted to show was high temperature durability. And this is same thing, perovskite thin film, unprotected. This time it's in an Anton Par apparatus, which allows for temperature and atmospheric control, attached to an XRD diffractometer, an X-ray diffractometer. In this case here, we started at 50 C, heated to 195 C over the course of, I believe, 72 hours. And you can see we have all just alpha peaks of the perovskite material, a little bit of the delta phase initially at 50 C. The atmosphere in this case is ambient, no flowing gases of any sort, just the ports are left open on the Anton Par attachment. But at around 135 C, you can start seeing substantial growth of the lead iodide material decomposing, the perovskite decomposing. So this is a bad thing. This is not good. 135 C is not adequate for long-term durability or substantial processing. However, with this balanced amount of the additive that I previously discussed, at 195 C, we barely have any lead iodide form. We get a little bit of a twinkle here at 175, even at 200, one click above 195, we still haven't formed really any substantial amount of lead iodide. We have, in principle, just a pure perovskite material still. So we have improved with this additive from 135C decomposition to around 200C before we see any decomposition. So the perovskite can also be made, damp heat durable, but also, relatively high temperature durable as well. So I'm sure you're curious about performance. I mentioned in the beginning, we focus on durability. That's kind of the key to what we do. So efficiency is also important, a little bit easier to maintain. However, the problem is the most durable components usually are less efficient than the less durable ones. This is kind of a dichotomy we have to live with. But that has actually not stood in our way. Typically, we'll make a switch from a poorly stable material to a more stable material. We'll lose some efficiency, but we learn how to regain it over time. So we like to set a bar of about 18%. We can show some data on that here. Our best devices of this design are around 20% currently. But we like to show the data in stabilized power output, meaning that if you scan a perovskite solar cell and it's not a very good one, it will demonstrate very high levels of hysteretic behavior. This means you can actually fake, to some extent, the efficiency. But if you show it in stabilized power output format, you cannot do that. So we start with the constant voltage measurement or voltage application. We bias the cell at a constant voltage and measure the current. We turn off the light for 30 seconds and then turn it back on and see if there are any transients. So if we have asymptotic behavior there, the device turns right back on, we got a great device. If it did something of this nature where it slowly turned on, that is a transient, which is indicative of a strong hysteretic behavior inside of the device. And so we don't see a structure like this in the stabilized power output or the current and voltage measurements, JSC and VOC respectively, then we don't have a quote unquote good device. Further, one of the best properties of the perovskite system is that, one, I mentioned this got a stability problem. We've solved that, right? We got that solved. Efficiency is great, right? So 20+%, the highest efficiency devices to date are over 25%, and there's a theoretical limit of around, or a practical limit at around 29%. We think that's possible. But what's even cooler is the low temperature coefficient, meaning that silicon and CAD-TEL cells have around -0.4 to -0.35% per degree Celsius temperature or cell rise throughout the course of the day. So as the panel gets hot, this high power cell loses this power and results in less energy output throughout the course of the day. But the perovskite system, at least at the scale of a 25 centimeter mini module, we're measuring between -0.05 and 0, typically around -0.03. And we built a special apparatus just to measure this, where we can cycle from 0 to 70 Celsius in a cyclic fashion. And you can see the expected inverse response of voltage, very flat GSC, slightly negative response in fill factor, and overall slightly negative response in PCE, or power conversion efficiency. So this is pretty remarkable behavior. We're really excited about this. And for reference, if you were to see positive temperature coefficients, this is not possible. That results from a positive response in fill factor, meaning there's a barrier inside the device that you're overcoming through KT. So positive is not possible. So if somebody says they've measured positive, they have a bad device. It should be slightly negative if you've got a good one. One thing that's a little bit messy is these are some early stage measurements, but I like to show this because in durability testing or accelerated lifetime testing, we've got this problem, right? Where I got an egg, right? And I heat this egg in an incubator and I heat it properly and on schedule, I make a chicken, right? But if I want my chicken faster, I can turn up the heat on the incubator, I put in the egg, and I expect my chicken faster. But in fact, what I make is a hard-boiled egg, not a chicken. So this is a big issue. And it's something we have to assess with perovskite durability as well. And so if we try to accelerate our lifetime measurements, oftentimes we can induce behaviors in the device that are not natural, things that would not occur in nature. If I put it out in a field somewhere, the wind's blowing on it, it's hot, it's 85 Celsius, you got sun shining on it. But these accelerated conditions are typically much more demanding than real life conditions. So one of the things we did, same 1,000-hour test, This is actually 500 hours of light exposure, where we turn the light on for 12 hours and off for 12 hours. We cool it down to 25 Celsius. We're running it at 65 C through the course of the day. Represents something that was more nominal of, say, a solar panel in the United States that's installed. And something that's quite remarkable that happens. And of course, we're digging more into this. We're getting more data. This is the initial data, but the perovskite system seems to exhibit a self-healing behavior. This has been reported in the literature to some extent, but I don't think quite like this, meaning that we can expose it for 12 hours, turn the light off, and whatever issue might occur, something that it would be a precursor of degradation, reverses itself at night when the light is off and the temperature has allowed to cool. So this is quite remarkable again, and we're digging into it more. So this is only a 500-hour measurement, even though it's 1,000 hours under tests, under only 500 hours under light exposure. So we need to, we are working on doing it for 2,000 hours and improving the number of cells and the data representation as well. But this is a very, very promising property of the perovskite solar cell. And last kind of some examples here, what we're working on currently, 150 millimeter or 15 by 15, 225 centimeter squared mini modules, something closely representative of an M2 form factor silicon cell. These is kind of the very first prototypes that we made. Actually, this is the very first one that's been made. And what are we doing to develop that? So we've focused on durability and efficiency. Now we're focusing on, to some extent, scale. We're going up 9x in the area from a 25 centimeter squared device area to a 225 centimeter squared device area or module area. So there is some scale there, but mostly this is about processability. This is us moving from our standard technique of blade coating to slot die coating I mentioned in the beginning. So we're testing out the tool of choice for manufacturers. So that is really kind of the key, in that we're representing a paradigm shift here in how perovskites, or excuse me, semiconductors are manufactured. So instead of epitaxial techniques or single crystalline growth techniques, we're looking at solution processing, printing. So we have to prove that process out. Is it reproducible? Can it be made homogeneous? And so one of the things that we've done here is using our PL imaging tool I showed at the beginning. This is one of the very earliest coats at the 150 millimeter device length aspect ratio. And with some development work of the inks, the ink properties and the coating technique, you can see we have a very heterogeneous PL response from the sample. And then with some modification, it becomes quite homogeneous, showing some really nice progress. And what I like to show, though, is even though this looks heterogeneous in the PL imaging here, the sample itself structurally is very homogeneous. And so we took the sample, cut it into 9 sections, and then performed an XRD measurement. And you see the diffraction pattern for all 9 of the sections are identical. So structurally, it's the same, even though there's some heterogeneity there in the PL. And so, again, as a company, we probably want to talk about what we're going to do with this thing. And I'm sure this is of interest to many people. So in the red, this is where we've been focused primarily to date, at least through the end of 2019. And starting last year, we started to focus on scale up and manufacturability. So this is a slightly larger module size, from a mini module to just a mini module, but also focusing on manufacturability. We have to be able to demonstrate the slot die coating technique. With success here, this will parlay into a pilot manufacturing facility. We will demonstrate the full size panel, the 2 meter by 1.2 meter panel, and manufacturing at rate, kind of the critical pathway. And then what is our technology roadmap overall? You know, our name is Hunt Perovskite Technologies, not Hunt PV or Hunt Solar necessarily. So we're really looking at a variety of applications of the perovskite system. It's a semiconductor we can use in a variety of ways. But our path forward, just on the PV side, focusing now on single junction. That's where we're at currently. We believe that has a 29% efficiency ceiling. Next, we're going to be looking at flexible applications. So that's printing it roll to roll on a polymer or flexible substrate, and then tandem devices. And in this instance here, I'm really referring to the perovskite tandem, and the outlook is a little bit longer in 2023 because the small band gap perovskite cell are in a standard perovskite silicon tandem you hear lots about, that's ideally a 2-terminal tandem design, a 1.75 EV perovskite with a 1.1 EV silicon for the back subcell. So to have a similar configuration perovskite, you have a wider bandgap perovskite in the front with a light incident side and a smaller bandgap perovskite cell for the subcell that's in the back. The small bandgap perovskite is a challenge. There's a lot of durability issues, even more so than lead with the tin system that's commonly used for the smaller bandgap. And so we're kind of pushing that out. However, we're in a lot of conversations right now to potentially push up this time scale and work on a perovskite silicon tandem. So I want to end there. Hopefully we have plenty of time left for questions if there are some. But I want to thank the team itself for all their individual contributions. As the CTO, I don't do any of this work. I just get to talk about it. It's fun to talk about. I wish I was doing it, but all the work is theirs. I really appreciate all of them. And then skip that second one. That's a mistake. Joe Barry and the NREL staff, the National Renewable Energy Laboratory, they've been very, very great to assist us and to support us along the way, particularly in the early years. They've been really great collaborators. The Hunt family for their support. Hunt family, they're the founders of a Hunt Oil Company in 1934. So taking oil and gas money and investing it into a green future is a really wonderful thing, and they're great supporters. We appreciate them. And last but not least, to a gracious audience, we really appreciate y'all taking the time to listen to what we have to say about Hunt perovskite technologies. And with that, take questions. Thank you.
Michael, very good lecture. Please on your camera, please. Your camera is off.
All right, camera on.
Yeah.
Thank you, Dr. Michael, for nice informative lecture on perovskite solar cell. Now the session is open for the discussion. Any question from audience? Ratish sir, Raghu sir?
Yeah, Michael, I have a question. Excellent presentation. I don't know, this question is very relevant as far as perovskite solar cells are concerned. So one of the problems associated with perovskite is structural stability. Mostly it exists in metastable state. Have you done any annealing experiment, typical annealing experiment to stabilize the structure before fabrication?
Well, so that's what we're showing here, that the the perovskite as synthesized is quite thermally stable. I think if I understand your question right, you are correct in that it's really, in the perovskite system, it's all about geometry, right? Balancing out the geometry, optimizing the cubic structure, and that's partially what is happening here. Demonstrating between no additive and additive, but fully stable up to 200 Celsius. I think this is quite robust, and I don't know if anybody has done the same.
Have you studied the tilting of the octahedra in it using laser raman or something like that to see that how the stable is the structure?
Yeah, so we have done that structurally. We don't have any measurable octahedral tilt. It's full on cubic PM3 bar M.
Fine, thank you.
What is the current efficiency now we are getting? Michael, what is the current efficiency you have got with these perovskite cells?
Oh, current efficiency. Yeah, so we're in the low 20s right now in our best devices.
Good. Excellent. This very perovskite results I'm seeing the first time. It's very good, 20% efficiency. That's very wonderful.
And I will note that all of our efficiency numbers are on at least 1 centimeter squared devices. Like what is shown here is on a 1 centimeter squared device. The records that you hear, 25%, those are on very tiny, usually around 10 millimeters squared or less devices. And these are all 1 centimeter squared or greater.
Thank you, Michael. I would like to see you next year here in India.
One
Sure,
more
absolutely.
question from Minal. Minal, please ask your question.
Thank you, Michael. It was really wonderful talk. Actually, I just had this doubt. When we see about commercialization of perovskite solar cells, then we everywhere read that lead is a problematic because of environmental concerns. So when you commercialize your perovskite solar cells, how difficult it was for you because it contained lead?
It's a great question. I thank you for asking that. We are working on this problem. I don't have it in this presentation. Everything's in this presentation. A patent has been filed for, and that's something we're actively working on, so I don't include it. But most importantly, lead is the best material for perovskite solar cells. We can't find any replacement yet that is high efficiency and gives good durability. Tin, for reference, is actually more toxic than lead. Lead is really not that toxic. It just has very bad reputation in its use over the years, and its abuse over the years. However, that is not an excuse. So what we're doing is we are adding lead sequestration materials directly into device architecture, such that if the device were to break and lead is leached by water or acid rain, that the lead would be sequestered by these materials. And so we're actually working on high efficiency, high durability, lead safe perovskite modules currently that are all printed.
Okay, thank you.
Yes, ma'am.
Thank you. Thank you, Michael, for giving a nice introduction, nice talk on perovskite solar cells. And on behalf of organizing committee, I would like to thank Dr. Michael. Thank you. Now, I hand over the digital dais to our senior scientist, Dr. Milind Kulkarni, for conducting next session. Thank you.
Thank you.
Good morning, everyone. I am Dr. Milind Kulkarni, and it's my great pleasure to introduce to our next speaker, Professor Vinayak B. Dravid sir. Professor Dravid is Abraham Harris Chair Professor of Material Science and Engineering and the founding director of Northwestern's Nuance Center. He received his BTech from IIT Bombay in 1984 and joined Northwestern soon after his PhD from Lehigh University in 1990. Professor Dravid's scholarly interests revolve around nanoscience and nanotechnology for energy, health, and environment. He has diverse research portfolio covering advanced microscopy, nanotechnology, energy policy, and emerging educational paradigms. His Google Analytics includes over 580 plus archival journal publications, H index of more than 100, more than 24 issued or pending patents on his credits. Some of his patents are licensed to startup companies related to nanotechnology for environment and sensor diagnostic systems. As Clarivate Analytics, highest cited researchers for many years, Professor Dravid's awards and honors include fellowships to numerous societies, inaugural class of Fellows of Microanalysis Society, Royal Microscopical Society, American Physical Society, American Association for Advancement of Science, Material Research Society, the Microscope Society of America, and the American Ceramical Society. He is the recipient of noteworthy awards like American Ceramic Society's Robert Coble Award and with Japanese Ceramic Society's Richard Fulrath Award, MSA's Burton Medal, IBM's Faculty Award, and NSF's Young Investigator Award. He is an honorary life member of Material Research Society of India and Yuan Li Fellow of the Chinese Academy of Science. He has been elected to Northwestern Faculty Honor Roll for several years for excellence in teaching. Professor Dravid has served as an advisor and consultant to meteorology, energy, petrochemical companies, IP firms, and the Chicago Museum. He advises NGOs, professional society outreach programs, international organization, and private sector about science, technology, and policy. One of Professor Dravid's passion is to enhance societal and global appreciation for science and technology, especially of microscopy, material science, nanotechnology, and energy and sustainability. With this introduction, I will request Professor Dravid sir to proceed for his presentation. Dravid sir, please.
Thank you. Can you hear me okay, Bharat?
Yes, sir.
Excellent. Thank you, everybody. It's been an amazing year. We've been so sequestered through pandemics. I hope I'll get to see you in person someday. I hope it'll be later this year. I'm originally, as most of you know, from Pune, which is the place where your headquarters is. And so I have very fond memories of my hometown. And I hope I'll have the opportunity to greet you and meet you in person later this year. So I was here, I think, in a similar capacity last year in a slightly different talk and different title. So I thought I'll pick up today's a continuation of the theme that you've seen in our research group. And so let me move to the next slide. Okay. All right. So I chose a little provocative title, as some of you see it, and also in the abstracts, Teaching Old Materials, New Tricks. So these are the materials of yesterday, the sponges and membranes. These are the petroleum products that have emerged over the last century, certainly more than that. So if you look at how the societies have evolved over the last couple of hundred years since pretty much the Industrial Revolution, certainly I think the Western society obviously grew much faster, but China, India, Brazil, and others are not too far behind. As a result, we have created an absolute mess in the environment. And part of the motivation behind this work that I'll present to you is how do we get this discarded stuff that we often throw away, such as membrane and sponges. Because when you get your gift from Amazon, you might have an iPhone, which is very small, but you have this large box with so much sponge and other packaging material, and that gets thrown out. So what we do here, as you'll see, is we create value-added product. And so we are teaching this old materials, the sponges, new tricks, and this new tricks being they can capture pollutants, and particularly in aqueous pollutant, as you'll see. This is the work of a number of my students at Northwestern University, and you're welcome to visit the research group, and you'll see a lot more details there. And just by way of introduction, for those of you who are not very familiar with me and my research group, obviously we do a lot of research, as you'll see, related to interfaces. So the genesis of a lot of the environmental remediation lies, as I'll show you, nanoscale phenomena that we study using advanced techniques, methods. But importantly, we also want to translate that basic science knowledge to technologies. And so these technologies, as you can imagine, environment is a massive gigaton problem. So you want an approach or methodology that's compatible with scalable, which I'll show you. Then last couple of decades, of course, the corporate R&D, particularly in the American context, has dramatically shifted. And it's much more pharma and IT dependent. So a lot of physical science and engineering innovations are now being done at universities. And one key element of that is something I manage called facilities and infrastructure. And that's something of great interest also to India and other emerging countries. And that in context with global initiative collaboration makes up most of my research group. So today what I'll talk about is greetings from our research group that you see on the top. Is our water subgroup, and these are really amazingly committed students and researchers, all the way from Vikas Nandwana, who's from my alma mater, IIT Bombay, some years ago. He's now a research faculty in my group, to Roberto Reis, who's the most innovative electron microscopist who looks at molecular structure at the interfaces, which is bearing on some of the problems that I mentioned. Stephanie and others are graduate students and undergraduate students who form this wonderful team that you'll see. By way of introduction, in case you're not very familiar with Northwestern, this is a suburb of Chicago. Chicago is home to Great Lakes region. We have the Lake Michigan. So 6 Great Lakes of the non-salt water reservoirs are in North America, as you see. And there's a tremendous challenge actually in many of these parts, even with so we have this fantastic resource, but it's also been getting tremendously polluted over the years. And that's one of the reasons that we picked up this topic as a way to translate basic science into applied technology. And a lot of the things that I mentioned here are relevant to an Indian context. In case some of you are interested, I'll be very delighted to tell you. We have a startup company which will have a .org arm that would clean up environment in the emerging economies like India. So I'll describe to you some of these ideas that come out as a part of this nanoscale approach to gigaton problem. So if you look at, as I mentioned, from industrial revolution to now, and of course with climate change upon us, there's tremendous challenges which already exist. Right? You have pollution. Even if you stop using, we can start using sustainable solutions. We have the legacy of the past that needs to be cleaned up. So there are a number of them. One, as you'll see, oil remediation. That's something some of you may remember from last year that I presented. But then this year, there's a dramatic shift in our research focus, and also amazing results from Stephanie's work on phosphate remediation. Phosphates are one of the two fertilizers, nitrate and phosphate, which are often used in agriculture with this tremendous Indian context there, where a lot of this fertilizer actually get run off through waterways and ends up in rivers and water bodies, which create this massive algae bloom and other problems that most of you know. Then, of course, along with remediating oil, typically it ends up with mercury and other heavy metals. Certain parts of the world, particularly in Northeast India, for example, has arsenic in water. So there are a lot of problems that need to be addressed at the scale, which is this massive scale. So our approach over the last few years has been, can we develop this nanotechnology solution based on the sponges? Sponges is this uncanny ability to absorb through capillary effect. So if you can create selective coating inside the pores of the sponges to capture particular pollutants, then you have a very smart sponge, as we call it. Secondly, sponge has this uncanny ability to squeeze out and in. So this ability to reuse also is an important asset for membranes. And third is, of course, scalability is a big issue. As I mentioned, we have this massive supply of sponges. So it's usually one has to actually pay to get rid of waste in America and a lot of the Western context. So you can actually imagine using a highly scalable product in the form of sponges, typically discarded, using affinity coatings, which are made of as earth-abundant material, which are carbon and iron. And that is the major innovation that you'll see in the rest of my presentation. So I'll start with oil remediation. This is something I think some of you have seen, so I'll try to accelerate. The basic idea is we take any typical discarded sponge, polyurethane typically, and we dip coat it in a slurry that contains our nanostructures of iron oxide based with carbon. So the carbon is the hydrophobic part. Iron oxide can be tuned with specific dopant, so it can attract very specific pollutants. And then we expose this smart sponge to air or water or soil, and it absorbs the pollutants, as you'll see. And then you recover the pollutant by squeezing in the case of oil, and you get the oil recovery, and then you can reuse it many times. And then you have the recovered pollutant. In this case of oil is, of course, the oil, as I'll show you for the later part, is phosphate. And in some cases, once the sponge is used many times, just like any household sponge, when it starts to break apart, we are developing a combustion process by which we actually convert it into an anode for lithium-ion battery. And that makes it a circular economy. So you have this, imagine the wonderful idea that you have the ability to use discarded products such as sponge, which otherwise forms a landfill. We are now using it to absorb pollutant and then recover the pollutant. And then at the end of its life cycle, we convert it into an anode material. So that is the circular economy of 2021. On the other hand, you can imagine that by tailoring the coating, we can make it adaptive to different pollutants. And I'll show you an example, several examples. One is oil, the other being phosphate, and heavy metal. So it's almost like a Swiss Army knife, depending on your need for pollutant removal. You use the appropriate sponge to attract the pollutant. So let me start with the oil spill is so ubiquitous, and I think most of you are familiar with the oil spills. Some of them very small in the neighborhood that don't make up the evening news, and then there are this massive one last year, if you remember, Mauritius spill, or most recently, just a few weeks ago in San Francisco Bay, Chevron company spilled diesel, 600 gallons. So there are all kinds of spills which continue to operate, and particularly with climate change, you have the Arctic is melting, so there are a lot more shipping lanes. So what's happened every time you have a shipping of oil, there's going to be spillage. So it's a very profound problem. And there are not many sustainable, profound solutions. So in fact, currently they use dispersant, which is basically spreading the poison, booms, creepers, all these other techniques that are just not sustainable. They're not economically viable. And the more and more these spills are becoming more and more expensive. So we've been working with ICOPAR, the Consortium for Oil Spill Remediation, and others as a part of a startup company to look at different strategies to mitigate oil spill and recover them. So let me just take a pause here and show you a short video that some of you might have seen before, but it's worth seeing it again in the context of this particular product. It's called as OHN sponge, and it's just a 1.5-minute video. I hope you'll get to see it and hear it.
10 years ago, a powerful explosion destroyed an oil rig in the Gulf of Mexico. The Deepwater Horizon well dumped an estimated 168 million gallons of oil and 45 million gallons of natural gas into the ocean, making it the largest accidental marine spill in history. The event sparked a nationwide call for more research into oil spills and their impacts on our oceans, environment, and lives. Studies over the last decade have advanced our knowledge of oil spills, resulting in novel applications of emerging technologies. One brand new technology is Northwestern University's Smart Sponge. This highly porous sponge has a nanocomposite coating of magnetic nanostructures that attracts oil and resists water. The coating can be applied to any cheap household sponge and binds with oil molecules, capturing and storing the oil in the sponge until it is squeezed out. The Smart Sponge can absorb more than 30 times its weight in oil and can be reused up to several dozen times without harming marine life. The National Science Foundation funded team says right now the Smart Sponge can be used effectively to remove pollutants and toxins in water and soil. It can also clean up smaller oil spills in a more economical, efficient, and eco-friendly manner, helping to protect ecosystems and surrounding communities.
So as you can see, the National Science Foundation initially supported this work, and they're very excited to conduct this media. And as a part of that, I think we were approached by a number of people challenging us to look at other pollutants. And let me switch back to the slideshow, and then I'll show you the rest of the presentation. All right. All right. So as I mentioned in the video as well, that we've developed this so-called OHM sponge. All we do is we take any polyurethane sponge and then we dip coat it with the slurry that's made of these two components, the magnetic component being the iron oxide, and the hydrophobic and oleophilic component being the graphitic carbons. And it's made in a very special way, which I don't want to waste too much time. But it's a very integrated sort of a structure that adheres very well on one side to the polyurethane, the other side it attracts oil. And as you can see pictorially, it's a hydrophobic, it repels obviously water, oleophilic, as soon as the drop is there, it disperses it. It's certain characteristic that I mentioned. And so if you look at the properties of this OHM sponge very briefly, any type of oil, hexane to pump oil, different viscosities can be absorbed. What you see on the y-axis is the mass absorption. So that means for 1 gram of sponge, how many more do you absorb? So you can see 30 times its own weight, it can absorb the oil. Secondly, you can see it happens at regardless of the pH. Sometimes, you know, waters are different acidic. They have different salinity, as you see on the bottom case. So seawater is roughly about 0.6 salinity. So even in seawater, it's able to absorb 30 times its own weight. And as you can see, the first cycle you squeeze just like a gunmaker juice, right? You squeeze it through the rollers and then you recover the oil. Then you do the second time, third time. As you can see, unless the sponge breaks apart, it can continue to operate and recover oil, and that's something very exciting. But then, of course, we were challenged that could it be due to the refined oil. So we tried, of course, with crude oil, very smelly. So we didn't do many experiments, but you get the idea that regardless of different types of crude, it seems to recover. And we can make this a continuous process. Just to give some example that we can make them within 30 minutes. You can have liters of the solution. And remember, only 10% or less, 5 to 10% of the coating is necessary to do the functionality. So again, 1 liter of the slurry goes a long way, and you can make them of different size. So any shape of the sponge, you can dip coat it. And in fact, last year we made the estimate that within a week we can do enough to be able to take care of the spill that happened in the coast of Mauritius. So that gives you a sense of the scale and the scope. But ultimately, we as scientists, we want to understand why and how it happened. So let me spend a few minutes to see how do we get the nanoscale genesis of this to get to the technology. So these are sponges which are very difficult to analyze, as you can imagine. They're very high porosity. So what we do is very innovative ways to make them thin slices for microscopy, so we can look at interfaces and other areas. And so that's an area that our group is advancing a lot, is soft microscopy. So these are microscopy of soft material. On one hand, we look at viruses and bacteria with electron microscopy. On the other hand, we look at polymers. And this sort of gives you a summary of different methodologies that we have. So what we're doing is effectively environmental remediation, but we're looking at why and how that particular phenomenon works using this atomic scale techniques and methods that we have. And just to give you a sense of how hierarchical this is, so as you can see, it's a macro sponge of the order of centimeter and tens of centimeter scale. If you look at the finer scale, as you can see here, is highly porous. You can see ligaments of the sponge, and the bright dots are nanoparticles. And as you can see, if you go further up in the scale, so you see it's going from molecular scale all the way to macro scale. And the affinity is given by these two components, which are at the nanoscale. You have the graphitic part, the iron oxide, they're intimate contact with each other. So that allows us to look at the molecular scale issues with interfaces using fluid surface interaction, for example. And then what we do is we look at the ultra thin slice of this material, as you see with the bottom left. So this is done with the cryogenic ultramicrotomy. So you can see the porosity structure, you can see the sponge, you can see the OHM sponge, and you can see the tiny coating everywhere around the surfaces of the pore. You can see there are no coatings here in the typical sponge, but in our OHM sponge, you can see there's an ultra thin coating, few hundred nanometers, and that provides the affinity for the pollutant. And then we do a lot of cross-correlative technique as to why is this surface that active for oil or, and against water. And then we do Raman spectroscopy at that local scale and follow the various features associated. For those of you who are familiar with graphene, can relate to these techniques. And we can really correlate different techniques to show that this particular surface coating is functional in a certain form. We also conduct in situ experiments. So we have a electron microscope where we can actually watch paint dry, and I often joke that that's not as boring as people make it out to be. So you can see very good surface affinities, and you can watch how water droplets move around. There are a lot of quantitative details that I won't have time to go. But we can monitor. So this is the next length scale. So we start with molecular scale. Now we are at the mesoscale, micro scale, to watch our interaction of fluid with surfaces, looking at angular distribution. So this is an oil spill. It turns out that the understanding that we glean from making the coating in a thin way and attracting the oleophilic molecules can be now converted into another technology where we are looking for minority oil. So oil spills are obvious. They are, they're dirty. You can see them, and obviously communities hate them. But there are this other hidden problem in many parts of the world, particularly in fracking areas of North America, because you have aquifers very close to fracking, and so as a result, there's always a risk of contamination of water with oil. So in fact, most of the oil and gas companies nowadays call themselves water companies, because either they're in the business of remediating very tiny amount of oil and gas, as in the case of fracking or in Canadian tar sands, or in the case of water polluted with oil and gas, and that is something we are advancing. So the same concept of OHM sponge can be converted into cellulose-based sponge, and then you can do very high flow rate. And if you have a 2000 ppm oil that you see on the left, typically industry standard is to use some sort of a walnut shell, and you can see it doesn't do as good a job as one would hope. But you see that without much optimization in the recent past, we were able to clear 2000 ppm oil into a potable water. So that's an exciting conversion. They're going from oil spill to minority oil. That gives you the way the technology is moving. Another area where we could use this old material of sponge and give them new tricks is to create an affinity coating that is specific to nutrients. So one of the biggest problems among many in water is excess nutrient. And particularly phosphorus is one of the very notorious nutrient, because you need amount of phosphorus. In fact, our body has nitrogen and phosphorus from a number of these processes that people talk about, especially the Bosch process of making the fertilizer. That nitrogen is among so many of human beings that in part of our base pairs in our gene. The phosphate, on the other hand, is a finite resource. It comes from the phosphate rock, and it is depleting. And there's an amazing article by Julia Rosen just a few weeks ago. This is February 8th. And the title was basically humanity is flushing away one of life's essential elements, that's phosphorus. And this is a beautiful article. I don't have the time to do justice. It is extremely well written and extremely deep detail. And the crux of the matter is in this is the phosphorus, the bottleneck of life. And particularly in the Midwest where we have a lot of lakes, we have Lake Erie and many others, where the agricultural waste goes into the lake, and most of it is phosphate, which again is nutrient for algae. And then you get this beautiful green algae, but it's ugly because underneath you have no oxygen. There's a eutrophication process, and that is a very terrible environmental disaster. But again, phosphate is a non-renewable resource, and it typically comes with many other elements and species. So what we did is we developed a cellulose bus instead of OHM sponge, which is our oleophilic, hydrophobic, and multifunctional. We are now, and this is Stephanie's coin called Pearl. So what we do is we phosphate eliminate and recovery, and I'll show you what I mean by that. And the way we do it is we have a scalable, same coating approach, but now we have coating is adapted specifically for phosphate. And this is based on this magnetic nanostructures, which are metal oxide doped with the specific element. We adjust the energy level so that the phosphate ion have a much higher affinity. It turns out that this affinity can be tailored with pH. The pH is a very easy thing to control. So the idea is at a certain pH, you absorb the phosphate. And all we do is we reverse the process of pH, and then you recover. So imagine a sponge is at one location where the water is flowing, phosphate ions are being attracted and captured by the absorption on the nanostructures at a particular pH. And then we collect this, go to another tank and change the pH and release, as you'll see, most of the phosphate, then come back and recover it. So just like in the oil recovery process, we are now doing phosphate recovery. So this is a brand new result that's just being reviewed as we speak. And what you see is remarkable, and we've done this repeated blind studies, and it's almost 99% sequestration of phosphorus. So what you have is actually our actual data from real water sample from Chicago Water Reclamation District of Greater Chicago. It's his actual world's largest water processing facility. And they use a certain two-stage method to remove phosphorus before it can be discharged or served to the community. And as you can see, it's so complex. It has sulfates, chloride, nitrate, bromide. All of them have a certain function. So we want a particular sequestration approach which does not compromise the rest of the ions except phosphate. And that's exactly what you see, that we have this tremendous selectivity of phosphate. So you start with a certain level of phosphate that's natural as a part of this cleanup process. And then just one treatment of our pearl sponge, and you have basically undetectable phosphate. So as you can see that this affinity is driven by this nanostructure. So then the question is, okay, you captured the phosphate, then what? So it turns out that this method is reversible. So what you see here on the left-hand side is the pH, the lower pH and higher pH. Lower pH, you can see almost high, almost 100% removal. So that means that low pH, the phosphate has a very high affinity for the surface, and it basically captures it. So imagine a scenario, so where now we have very low pH that can be very easily adjusted with some acidic water. And then you capture the phosphate. Then you take the phosphate to a different tank and you release it. As you can see, at a higher pH, you can almost release 70% of it. So what you see is the summary on the right. So you can see that the first bar is the capture bar. So you can see almost 99% capture. The second bar is the release bar. And you'll see there's a small difference, and that has some relevance, as you'll see. So we capture 95%, release 70 something. Then we go the next cycle, we again capture very close to it, remove most of it, because now remember now this 9% is with respect to the original percent. And as you can see that this can go on for a number of cycles. So that's just like the oil recovery. This is very exciting that you have now the ability to remove phosphate. A lot of basic science. I want to again emphasize, especially students in the audience here, that it might be a macro technology of gigaton, but the basis, the genesis of this phenomena lies at the very nanoscale interface. And what we do is monitor X-ray photoelectron spectroscopy, for example. Again, the details are not as important except to say that they're full of subtleties. What you see is the iron 2p edge absorption, this emission of X-ray photoelectron under sort of after desorption, after absorption, so you see some shift. So there's an energy transfer, and the reason why the phosphate ions are bonding on the surface is because of electronic interaction. And again, at some other point, I'll be happy to describe some of the electronic structure diagrams. So we see that there's a physics and the electronic structure basis for this affinity that we are tailoring. And then you see this is MNS, stands for magnetic nanostructure. So we can almost see there's a slight change. So in other words, some amount of phosphorus remains on the surface of this iron oxide, and that's why we don't get the second recovery fully. But that amount is relatively small, 15 to 20%. So you can see the 70% of the rest of the phosphate can be recovered, and that's very exciting. But that was done with the surface phenomena. So looking at surfaces, as you know, most of the XPS technique is surface sensitive. So this is some study that we're beginning to do, and we're getting a lot of insight when we're looking at sections, just like we did with the OHM membrane. We are now making section, and what you can see is you have the cellulose substrate, or the sponge is the major cellulose, and around it is this ultra thin coating of iron oxide based structures, which have this very high affinity, as I mentioned. And if we take this small portion here, and you can see it's magnified here, you can clearly see very thin coating of a nanostructure on the surface with the bright field, dark field. And then we do a lot of crystallography, diffraction to figure out what's it made of and so forth. However, now more recently, Stephanie did a remarkable experiment using energy loss spectrometry. So here is sections and materials looked at in the transmission electron microscope. And what you see on the top is iron image and the phosphorus L, and we are actually looking at the image that you see. ADF is annular dark field image, iron M image, phosphorus, and you can see this complete coincidence between phosphorus and iron that really gives us a lot of confidence that this is affinity-based absorption that is pH dependent, and that's a very exciting way to acquire and release phosphate. So as you can see, that there's a couple of stories that you just see here, that we take our typical sponge, and the coating gives you affinity for oil in one cases, the coating gives you affinity for phosphate. There's another student who's now doing heavy metal remediation. And then last but not least, we are looking at radionuclide remediation in aqueous, that's cesium and technetium, and that's perhaps a talk at some other time. The idea is, again, the same basic idea, get affinity. And if you have the magnetism, you can use robotic manipulation to move things around. So now the question is, what's the circular economy part of it? And that I mentioned, I alluded to in one of the first slide. Just imagine, just like in household, you know, and so some of us we clean up, especially in pandemic. And then when the sponge starts to fall apart, what do? So like I said, one of the students is looking at this issue. So you can create a controlled combustion. Remember, iron oxide has the catalytic property, and the carbon can be converted to graphite. And that graphite MNS composite is actually an amazing anode, and that's called as a new node. Both of this technology are a startup company, and new node is the trademark of Northwestern. So what we do is basically take the material such as a sponge with our nanostructure with carbon, and we are completing the loop. So after it does this oil recovery, all we do is we combust it and it creates this nanostructures. So this OHN sponge becomes our new node. And this is the work of Caesar, one of our students who was part of a competition with Argonne National Lab, so-called chain reaction initiative, and he went all the way to the finals on this concept. So what you have is the same thing that made the oleo sponge the way it is. So you have nanostructures of magnetic and metal oxide embedded within this graphitic network, and that provides you as a classic lithium-ion battery. And I don't need to tell this community and this crowd the significance of energy storage. There are Internet of Things that are proliferating everywhere. So you're looking for batteries, extremely cheap batteries, which do not need attention, which can be sort of deployed for years. And there are lots of such applications that I don't want to spend too much time, except to emphasize that transition metal oxide are a very viable additive now to graphite, just like silicon. So most of the anodes nowadays are silicon blended. And another version of that would be metal oxide, because they provide you with a very respectable capacity. And that is exactly what we show. And some of our early results are very exciting, that a typical graphite coating has a certain 400 odd capacity for anode. And the new node, because of you have iron oxide base or metal oxide components, they produce almost 3 times more lithium capacity. And because iron oxide is much cheaper, including actually graphite, then it actually becomes very, very cost effective. And then as a result, you can also reduce the weight. So we're very excited that, as you can see, we have environmental remediation of oil, phosphate, and then once the work is complete, you convert that into an anode. So I think I have more than taken my time. I should just quickly summarize that we have this amazing, at least to me and my student, an approach where we take an old material, old dog, we call it euphemistically, new tricks. And we have old dog being our sponges and membranes, and we treat the new tricks of sequestering, as you'll see, oil and phosphate. And so you can imagine that this ability to scale up and look at the interface at the fundamental level really is exciting. And it also becomes a part of resource outreach, because this sponge is a great example to show students and get them all excited. And actually moving forward, we now can see an opportunity to look at molecular scale phenomena. So how do we clean Ganga and all sorts of other dirty waterways is through this sponge type approach, but the genesis or the origin of this lies at the molecular level and at the time domain. And that's something I wanted to emphasize as a motivation for students and young folks in our audience. So this is a work, it's a result of a number of people, as you know, and particularly I'm very excited to announce our company, MFNS. And for those of you who are interested on the commercial end of this, I'll be happy to tell you more offline. But really, most of the effort here is basic science with number of agencies and other collaborators that you see in our own group, our Nuance Center that I run, and a number of other centers and facilities at Northwestern. So with that, I think I should stop and take any questions. And I appreciate your attention. And this is one of the very rare talks where I would say that, I talk for 2 days. I started at 11:30 at night in Chicago, and I just passed the midnight. So right. I think it's not very often I can say that I talk for 2 full days. Right?
Thank you.
Thank you, sir, for an excellent and informative talk. Now the session is open for 1 or 2 question and answer.
That is fine, as long as I get vada pav at midnight. There is no, what is that, Grubhub or something that can come to Chicago, right? That's all right. Go ahead. Please ask the question. No problem.
Yeah, Professor Dravid, thank you very much for your time, your valuable time. And actually, our students are very happy to hear from you. And basically, these membranes, I would see all this water purification, other things I have seen, no problem. But this will be taken up in huge scale in India, because India still rural area water problem.
Absolutely.
So people are using lake water, people are using river water or well water. Always this water is hard water.
Yes.
Okay. So whether we can have very small kind of device where we can purify this kind of water so that the person in the rural area can have the good water. This is one question. So we want solution for this one. Second question. See, in all our mineral industries, they are using the solvent extraction.
Yes.
Like in our Hyderabad, we have an NAFIAT. The hafnium is only 25 ppm, 35 ppm. Okay, and these people are taking solvent extraction and other thing, and it's a huge process, means long process. Through this membrane, whether we can have only this kind of metals attracted, and so that this process, the long process can be cut down to small solvent.
That's a great, both are the great question.
This is not only one. There are many solvent extraction processes. They are very costly because of this problem. So whether this membrane can work there?
Yeah, absolutely. They're both great questions. Let me take the first one first, perhaps. So the idea is absolutely correct that there are many parts of the rural parts in India, other parts of Africa, Southeast Asia. Water is contaminated naturally, also because of external factors like pollution. So there is a methodology that we are developing that combines this OHM membrane. Because remember, there are different pollutants, there are different methodologies. So one such is actually one of my very good friends. He's developed a test for arsenic using synthetic biology. So there are bacteria, when there's an arsenic present, they actually report a fluorescent tag and then it lights up. So imagine, but the point is that those are typically done with a test tube. So we're now developing that for our membrane. So imagine us, membrane will have bacteria, which is a reporter for arsenic and lead and other pollution. So at the minimum, initially, you would know that there is a polluted water, so at least you don't immediately drink it. So once you detect. Secondly, we're developing a sort of a suction type of pipe that purifies. So the idea is that if you have a puddle of water, if you suck it with a straw, that it comes out pure. That's one goal. And that obviously the number of people that are working on. And then the second question was about, I forget.
Solvent extraction, extraction of metal.
Solvent extraction. Oh, that's a great question. And I'll tell you, solvent extraction is a very common, and I learned a lot more about technology in the last few years than you can imagine. But it turns out the solvent extraction is great up to very high level, up to, as you said, maybe even 50 ppm. But depending on the type of pollutant, particularly oil, up below 100 is very difficult to do most solvent extraction. That's where the sponge is most ideal, because it is, we have shown as in some of the data you might see, from 100 ppm to literally non-detectable can be done with just one cycle. So that's one. Secondly, we use a flow reactor type of approach, whereby you can combine multiple sponges. So we have one sponge for oil, another sponge for lead, one sponge for phosphate. So we have this ability to multiplex different pollutants. And that's not easy to do with solvent extraction, because you're looking for the miscibility and solvent extraction. I've been studying that with some of the experts here at the Department of Energy, especially for nuclear remediation. You know, up to few hundred ppm, you can do solvent extraction. Beyond that, you cannot. Then 100 ppm of nuclear waste is also not very acceptable. So there's a niche for this particular product that we're very excited. It's at the very final stage. Even oil, there are many methods to remove oil. You know, the gravity just, you know, oil is light, so it'll come up on the surface. But again, when it comes to 1000 ppm and less, it's going to be very difficult. That's where this technology comes in.
Thank you.
Professor Dravid, I'm Ratish from CMET Hyderabad. Excellent lecture. Last time we have met at Pune also. So I have a very interesting question to you. Now the buzzword is resource efficiency and circular economy. The whole world is talking about that. See, once you use this sponge for absorbing oil, what do you do with that?
Yeah, so there are two ways. Again, one approach we are doing is oil recovery. So that means in most cases, when the oil spill occurs, you either dispose the oil, you burn it. That is not very helpful, correct? You can imagine when you burn oil, you're creating CO2 and you're creating waste also.
Right.
So one approach is you recover the oil that you can monetize. You know, there's no reason once you recover, if it's especially 200,000 gallon as in Mauritius spill, if we recover 150,000 gallon, you can sell that oil. Except one time, I think in the pandemic, the oil was negative, but most of the time oil has a positive price. So that's one. Secondly, once you recover the oil, you can do something with it. Correct? Otherwise, if it's dispersed, it's going to become a poison. So that's one. And secondly, as you can imagine, once you do it many times and recover it, then you can combust it to make it to anode. So I think there are both approaches.
That means you can reuse this sponge again for absorbing oil?
You can recover oil 20, 30 times. We got tired after a while because, you know, sponge like at home, you can squeeze, you can, you know, when you have oil water spill in the kitchen, you repeat sponge many times.
Right.
Only after 30, 40, 50 times, then you start to lose the pieces. That's when you stop. Then we say, okay, now take that oil-laden sponge. You basically burn it, but control burn it so it converts into graphite.
Okay.
And then we use that as an anode for lithium-ion battery.
Fine. Good, great. Thank you.
Kumar sir would like to ask questions, sir.
Yeah, excellent work, Professor Dravid. I just wanted to ask you a kinetics related question. See, you have a stagnant water and you have flowing water. So what is the efficiency of your adsorption process?
It's a great question. So for the oil case, it's obviously it's just the surface affinity. So we are doing next week a so-called an OMSET test. There's a facility in New Jersey where they simulate oil spills. And we are going through all the design of the experiment. So within 2 weeks, we'll give you very specific quantitative data as to what is the dependence on the salinity type of oil, the vibrations, the waves, and all those things. But we are very confident, because we have done all the miniature simulation modeling, model experiments. So we are pretty confident that, yes, regardless of the turbulence and other factors, as far as oil spill is concerned, it has the ability to absorb. The phosphate absorption, it depends on the flow rate. So I think all you need is a sufficient residence time of the fluid on the surface to have that affinity interaction before the water flows. And that's a tractable problem. You can simulate it. We're working with a number of people with fluid mechanics, but we are very confident that you can achieve very high flow rates and still be able to absorb. And as was shown, that we actually use the water sample of large quantity from the very water that tends to be cleared in the Chicago reclamation. So we're very excited that we have the ability to do that. And it's going to be engineering optimization, which is non-trivial, but it is something.
Thank you so much.
I would like to ask one question.
Yes.
Nitin Sali. Okay, so if there is no more question, then on behalf of organizing committee, I would like to thank Professor Dravid sir for accepting our invitation and delivering a very inspiring talk. Thank you very much, sir.
Thank you very much. Good luck to you. I hope I'll stick around a little bit. Otherwise, please accept my best wishes, and I hope to see you in person in my hometown in a few months.
Dravid sir, we would like to have in our Maharashtra Science Congress very soon, within maybe before May. This Maharashtra Congress will be Maharashtra Science Congress. We'll have on a webinar. So maybe at the end of the May, where the
absolutely one of my very good member of a group is now in India is Datta Latte, as you know. Forward to working with Datta. He's just been elected to I think Royal Society of Chemistry, and all of you are also members. So I'm very proud of all our accomplishments of our colleagues in India and CMET. My congratulations to everybody.
Thank you.
Bye bye, Bharat.
Bye.
Thank you, sir. Thank you very much. Now I will hand over it to my colleague, Dr. Sudhir. Dr. Sudhir, please.
Good morning, all. It is my pleasure to introduce the speaker, Professor Douglas McFarlane. Professor Douglas McFarlane is Sir John Monash Distinguished Professor and Australian Laureate Fellow at Monash University School of Chemistry, Melbourne, Australia. He was the Australian Academy of Science Craig Medalist 2018 and winner of Victoria Prize for Science and Innovation 2018. His interests cover a broad range of materials, chemistry, and electrochemistry for renewable energy generation and storage. He has published more than 700 research papers and 30 patents, and these have been cited more than 60,000 times. Its H index is 130. He is one of the Clarion highly cited author 2020. Professor McFarlane was elected to Australian Academy of Science in 2007 and Academy of Technological Science and Engineering in 2009. We'd like to extend our warmest welcome. We are so excited to have you among us today. Professor McFarlane, please.
All right, thank you for the introduction, very kind. Let me try and share my screen while I'm talking here. Okay, is everybody seeing that
yes,
screen?
Well.
All right, very good. Well, thank you for the invitation to speak with you today. I'm talking to you obviously from my backyard in Melbourne. It's courtesy of, I guess, what we've all learned to do during these difficult times, which is to attend conferences by Zoom and so on. But I've traveled extensively in India, although I've never been to Pune, and I would much prefer to be with you today in Pune, and I've always enjoyed attending conferences in India. So Zoom is a very poor alternative to the real thing, but we'll do our best. Following on from a bit of a theme here about circular economy, I wanted to talk with you today about a particular part of the very big picture of a circular economy. And I'm going to focus this, talk about this in terms of a rather important element. And that is very important to us all, which of course is nitrogen. So I refer to this as the circular N economy. You've probably never heard of this before. I think it's just becoming both a huge potential and a huge issue, as I'll describe today. My talk is going to be a little bit about what is possible here, with the occasional what I call deep dive down into some materials, which of course is the love of all of you here. So I'm just hoping to expose you to some of the emerging electronic and electrochemical materials that are going to be important in the future, and I'm hoping to convince you that these will be very important in the future. Okay, so let's dive into this. I shall just use that. Okay, so to set the scene, the current day, the 20th century N chemistry cycles. In other words, where do we get our N chemicals from? In fact, most of the nitrogen-based chemicals that we use currently come from a very important, but only about 100-year-old process called the Haber-Bosch process, which is in the center of this diagram. And this diagram is intentionally black because the Haber-Bosch process effectively makes all of these chemicals from carbon, a fossil source of carbon, usually natural gas. Okay, now you might immediately think, all right, well, that's just to do with chemicals. Actually, this is very much to do with us, because one of the chief uses for the ammonia that's produced by the Haber-Bosch process is fertilizers. Now, while it may be true that there's a lot of natural fertilizers used in India, worldwide, Haber-Bosch, therefore fossil fuel derived fertilizers are by far the predominant source of nitrogen fertilizers in the world. And of course, they end up going into our food system and they end up in us. And it's true to say that for most of us, maybe not all of you it depends where you come from in India, but certainly me and others here in Australia, it's probably true to say that a very large fraction of the nitrogen in our bodies, that's our proteins and DNA, have ultimately had an origin, which is one of those fossil fuels. So that's a little bit of a depressing sort of perspective. I'll talk more about about some of this, the right-hand side of this diagram later in my talk, but I'll just note in passing, since it's showing here, that when you make nitrates for nitrate-based fertilizers like ammonium nitrate, that's another process called the Oswald process, and produces a nasty content of nitrous oxide, N2O, which is one of the very serious greenhouse gases. So that process itself is also causing trouble. And the net result of all of that is that we've got this rather awkward nexus competition effectively between food production and climate sustainability. And I'll just let you ponder on that, and remembering that currently that a lot of our food is produced globally using these fossil fuel derived fertilizers. So here's the green picture. The question is here, can we start to green up all of this cycle, ammonia and nitrate being the key products that we're looking for, and how do we do this is the question. And one of the inputs obviously could be water, or as I'll talk about as a stepping stone, it could be green hydrogen. So this is getting a little bit more detailed as to how we might actually do this. So there's our picture. How do we do it? And the key point here is that while we may start talking about fertilizers, there's a growing recognition in the world that ammonia actually is a very useful energy carrier. In many respects, it's got very many properties as a fuel that are rather like methane as a fuel, natural gas. So suddenly this picture develops a new dimension, a much bigger dimension, which is carrying energy from parts of the world where renewable energy is very easy to generate. And this is one of my favorite pictures, and it's worth looking at it also, not only from the Australian point of view, but also the Indian point of view. This picture shows solar energy radiating down on the planet, averaged over night and day and summer and winter. So totally, this is effectively continuous solar energy in an average sense. And the dark brown colors, if you can see the numbers at the bottom of the slide, are nearly 300 watts per square meter. And of course, the bluey purpley colors, including most of Northern Europe, you might notice in the UK and Ireland, are very, very low numbers, well below 100. So if you're going to put a lot of solar cells somewhere in the world, where are you going to put them? And the answer is, well, Australia is a very good choice amongst the land areas of the world. This little yellow square kind of makes the point very clear. That is an area about 250 by 250 kilometers. And if you put ordinary solar cells, and the details are in the bottom of the slide on that, you can generate 25 petawatt hours per year. And if I was talking to you in person, I would ask some of the students to give me an idea what that amount of energy, is. What does it represent in the energy production of the world? And then maybe give somebody a prize for getting it right. And the answer is that's the electric supply of the whole world, just from that little yellow square. And to put that in a different context, that area that I talked about there is about the land area of Australia's 4 biggest cattle stations put together. So it's not a lot of land in terms of useful product. And I can tell you that our desert cattle farmers would be very happy to have some additional source of income like solar farming. And I'm sure some of what I've just said there could well apply to some parts of India. You can see the color scheme there. And you know, I'm thinking of Rajasthan and parts of northern Maharashtra could be very suitable for this as well. So lots of energy, not always where we want it though. And of course, in Australia, it looks like that. I suppose Rajasthan looks a bit like that too. The point is, how do we get this energy to where it's needed? How do we get this energy from Australia to, say, Mumbai or Delhi? And thinking about it that way, we discuss it as stranded energy. And the question is, what's in this ship that's shipping the energy around? And when you start to think that way, then you can start to identify possible ways of doing it. Currently, there's a lot of talk about green hydrogen. So use, and I'll talk a little bit about green hydrogen in a minute, but to use all that energy to make hydrogen, liquefy it, and put it in the boat. Well, it costs a lot of energy to liquefy hydrogen. That's more or less lost energy. So it's ultimately not the best solution. And there's lots of other problems as well, as you probably immediately guess, but there's a lot of talk about it. You could do something better with that hydrogen, which is to use it to make ammonia. And I'll talk about that in a bit more detail in a second. So there is a good way to get that energy around the world, because shipping ammonia is a very standard everyday concept. That happens in large quantities already for fertilizer reasons. And then I'm going to talk also about, well, can we sort of short circuit this complex process and make ammonia directly? And the answer is yes, and I'll show you a quick look at that. So here's a different view of what I was just talking about. This is the generation 2 idea. Renewables from various sources coming into a relatively standard water electrolysis cell. This is where the complicated, sophisticated materials are going to go. The large chemical plant in my picture before is just this little blue box. This is the Haber-Bosch plant being fed with hydrogen, green hydrogen. Ammonia is the product which is easily liquefied, 12 bar at room temperature, and is ultimately easily cracked into hydrogen or burnt, just directly burnt as a fuel, is all very possible with ammonia. So it's a great ammonia is a great store of energy if we can develop some of these processes. Here's a quick little deep dive into some green hydrogen producing materials. So here we're talking about using solar energy or wind energy to split water, not necessarily photochemical as this, well, that's a good idea. As this picture might suggest, I'm talking about doing it electrochemically, as in the photograph on the video on the right there. And if we look at some of the things that are going on in the electrocatalytic materials area in this regard, so this is now what kind of materials do you need on the electrode in order to split water into hydrogen and oxygen, 2 separate electrodes, anode and cathode. Here I'm talking about the oxidation catalysts. These are the catalysts that produce oxygen. In fact, that's the difficult step. It's 4 electrons. It has to get rid of 4 protons. It has to bring 2 water molecules together to make 1 O2. So lots of difficult things going on there. And it's typically most facile, most easy to do under very alkaline conditions. But proton reduction or water reduction to hydrogen on the other side of the cell is difficult under alkaline conditions. So there's a great interest in trying to make materials that would be able to do this water oxidation process under acid conditions. And that's what this is all about. Here we've made a material, and it's a combination of oxides. These processes are taking place at high electrochemical potentials. And it's a mixture of cobalt and iron, which are both very good water oxidation catalyst metals in higher oxidation states. But there's a bit of lead as well to try to get them to stay where we put them. The problem is that most oxides are at least partly unstable in respect of dissolving under acid conditions. And our strategy here is to use lead as part of that way of trying to anchor them into the crystal structure of the material. Here it is shown in our SEM work. But most importantly, this sort of catalyst does work very well in acid. You can see that this potential wants to be as low as possible. Here's thermodynamic. Here's this catalyst operating in sulfuric acid, and you can see it actually works better than it does in base, which is very good. And part of the trick here is what we call a self-healing mechanism. So even though the catalyst wants to thermodynamically dissolve, we're constantly redepositing it under effectively electrodeposition conditions. So the catalyst is reforming as rapidly as it dissolves, so it's dynamically stable. Okay, let me move on. That was the picture I showed you slightly earlier on. This is Gen 2. Just watch carefully as I switch now to the Gen 3 idea of this, which is same kind of cell, but now I've introduced nitrogen to the cell, changed the catalytic material, of course, and the product is ammonia, and the rest of the process is the same. The question is, what is this material, and what are these conditions under which we can make ammonia? And the problem that we immediately recognize is that from an electrochemical point of view, ammonia is quite difficult to reduce. Nitrogen is quite difficult to reduce to ammonia. Thermodynamically, it's not. In fact, it's easier to reduce nitrogen from the air to ammonia. 6 electrons, 6 protons required. It's easier to do that thermodynamically. The potential is more positive than it is to reduce protons to hydrogen. But unfortunately, that conditions under which this actually eventually happens, so this is not a catalytic problem, that is usually sufficiently negative versus these numbers in potential that in fact hydrogen evolution is always a competing reaction. And one of the reasons that it competes very strongly is that, of course, in water and in many sort of electrolyte type solutions that you might think of, there's a lot more protons around, so there's a lot more driving this reaction than nitrogen, because nitrogen is very not soluble, very insoluble in most solvents, including water. So one of the first things we did about this was we set about looking at nitrogen solubility in a variety of materials that are very well known as electrolytes. These are ionic liquids. I won't delve too long into ionic liquid chemistry, but just simply say that these are large organic cations and anions. And we're measuring the nitrogen solubility across a number of these compounds, which, because they're ionic liquids, they're also very good electrolytes. So this is the electrolyte solvent that we're talking about here. And comparing the nitrogen solubility with water, which is less than 1 millimoles per liter. So this is very, very, very small amount of nitrogen that we've got available to do our chemistry, whereas these materials can be nearly 10 times more conductive, so not conductive, more solubility for nitrogen than water. So that's a useful item in our toolbox, so to speak, to make this work. It's not too hard, at least to think that you've generated or you created a nitrogen reduction reaction. Here's an electrochemical experiment, relatively standard laboratory setup. We're scanning, or in this experiment, the potential negatively. This is on an FTO, fluorinated tin oxide electrode, in different gases, nitrogen versus oxygen versus argon, nitrogen being the red curve. Lots of scans here, so lots of scanning back and forth in this experiment, and measuring the current. So what we want to see is a large negative reductive current at some negative potential. And you can see that in nitrogen, we get a better, more negative current than argon. Looks good in theory. Actually, it's often not. And we've talked about this in this paper that's referenced at the bottom here this year, or this year just passed. The problem is that it's very easy to be fooled in this experiment by nitrate and NOx contaminants. And unfortunately, these contaminants are all around us in both the air and all of our solutions and all the surfaces, and even the gloves here. This picture is us analyzing the nitrate content of our gloves. So if anybody after my talk is inclined to get into this area, please read some of these papers by us and others about how to avoid some of these chambers of horrors, so to speak, before you get started, because it's very easy to get off on a wrong track when in fact all you're looking at is a very interesting process, but not the one that you think you're doing, which is nitrate reduction. There is an important experiment that we all do in order to be sure that we've reduced the nitrogen gas, which is to give it nitrogen 15. So expensive, but possible, nitrogen 15 labeled N2. And we can analyze the product of that reduction, because the nitrogen 15 ammonium ion has a very different proton NMR spectrum than the nitrogen 14 ammonium NMR spectrum. One is a triplet, the other is a doublet, because of the spin of the nucleus. So it's easy to tell that you've done it if you use nitrogen 15. So moving on then to something that really is quite productive in this regard, and where all of the nitrogen 15 experiments and so on have been done to really prove that this works. Let me describe one of these experiments now that really does produce ammonia in almost practical quantities. I think it's the state of the art. And this setup is a little bit like a lithium battery. We've got a lithium electrolyte, lithium ion containing electrolyte. Anybody who's working on lithium batteries should think that this is very much like what they've seen. Copper cathode, applying reduction current to that. In the presence of nitrogen, of course, the battery guys try to avoid that. We get lithium nitride, because the reaction between lithium metal, which is deposited on the copper cathode, and nitrogen is very, very rapid. So lithium nitride is the well-known product. And if you expose lithium nitride to some sort of proton source, which is executing a cycle in the cell between the anode and the cathode, we get ammonia. And that is exactly what happens. And the exact mechanism of what goes on this electrode is still a little bit open for a lot further in situ or operando type work, but it almost certainly involves a transient lithium nitride species at some point. And just to show you some results, many of these results are a little bit sort of deep dive into this, so I will not dwell on it too long. So we talk about the rate of the process in terms of a yield rate, which is in nanomoles per second per square centimeter. And perhaps all I need to say is that a truly practical rate is probably around about 100 on this scale. And you can see that we're rapidly getting there. And this histogram is as a function of potential. The other thing that's very important here is what fraction of our electrons that we're providing is actually producing ammonia rather than doing something else. And there's a number of something else's that could be possible here. And the answer is, in this particular set of experiments, we can see what's called Faradaic efficiencies, so current efficiencies, as much as 80% or more. And interestingly enough, and not surprisingly enough, that's also a function of pressure on the right. And we've looked at this in long running time. So we've got experiments here that run for 20 hours with very little happening other than the fact that the amount of ammonia just increases over that time, and the Faradaic efficiency stays about the same. So that's all good news in terms of imagining a cell that will do this process more or less continuously. So that's an emerging technology, shall we say, that a number of groups around the world are working on. Let me go back to this slide and then look at the process at the bottom. So ammonia to nitrate. So once you've made ammonia, one of the sorry, somebody trying to say something to me? One of the reasons you do this, of course, is that the nitric acid is an important chemical in its own right, but ammonium nitrate as a fertilizer is an important sort of simple fertilizer where you want to achieve the nitrate state. Nitrate is an important part of the fertilizer story. A lot of plants prefer nitrate as a source of N, much more so than ammonia or urea. This is possible. So the question is, can we do this reaction? And the answer is yes, we can. It's almost like a fuel cell reaction. It should produce energy because ammonia is effectively a fuel, and nitrates are a highly oxidized form of that. So we should be able to make a fuel cell out of that. That looks like a distant prospect of ammonia at the moment, but maybe one day this is going to be possible. Here's the sort of results we're getting at the moment. You can ignore most of what's on the slide except the bit in the circle, which is just showing that in an electrochemical experiment, now we're running to the high potentials, oxidizing potentials and oxidizing currents on the y-axis. If you add ammonia, that's the blue curve, you can start to see some new features, new currents appearing before this is simple ammonia solution in potassium hydroxide, before the solution goes into water oxidation. So before we get oxygen out, we can start to see nitrate forming. And a number of experiments doing these experiments different ways, adding amounts of ammonia here or spikes of ammonia, all show that this is genuinely depending on the concentration of the ammonia we've added. So that's all makes sense. However, one of the problems here is that we can get stuck at nitrite under some conditions. We can get very high efficiency oxidation to nitrite. Nitrite being NO2 minus, but the last step to nitrate can be troublesome, and that's nitrite is much less useful than nitrate. So there's a challenge there in achieving that last step. This is a long way towards that last step. So there are things emerging here in this ammonia oxidation reaction territory. And again, to go back to this one, what I've been describing is some early work going from ammonia to nitrate. But you might ask, well, we put a lot of energy in getting from nitrogen to ammonia, that was hydrogen energy, and then you kind of lose it again when you burn ammonia to make nitrate. Why not just go the other way around this cycle? Why not go from nitrogen to nitrate, which of course is what happens in lightning strikes? And the answer is, this is called the nitrogen oxidation reaction, the NOR. And in some ways, this is a holy grail of this cycle. It's possible in principle. It's an oxidation reaction, and it should be able to be driven by electrochemistry. but never really been demonstrated so far. So let's just say that one is tantalizingly possible as a way to get to nitrate. And remember, nitrate is really one of the ultimate forms of fertilizers. And I can say more in a moment about, there's some major environmental issue in parts of India is what happens when you have too much reduced nitrogen fertilizer in the soil rather than nitrate. Nitrate would be better, actually. So I can say more about that if anyone's interested. But let me then simply say, as heading towards the end here now, that that of course isn't entirely circular. Remember, my original title was promising to talk about a circular N economy, because all I've done is taken you from nitrogen to nitrate, and we have to ask, well, where does all this nitrate go, and is there sort of a problem here? And some of you will already know that nitrate pollution in groundwaters is actually quite a big problem. So we have to then take a step back and look at what's known about the rest of the N cycle. This is my last slide, by the way. I can talk about this at very great length, but I won't, so I'll just sort of try to summarize. This is not our work, by the way. This is not what my group does, but I think it's important as we talk about starting to use more and more ammonia and as an energy carrier and as a so-called sustainable fertilizer, that we're very conscious about what's going on in the bigger picture of the global N cycle. So this is a global N cycle. These are all the things. All these arrows are how nitrogen cycles in the environment. Couple of things just to point out, and I just encourage you to read this paper at the bottom if you want to know more. Total conversion every year is about 413 teragrams of nitrogen to reduced or other reactive forms of nitrogen. And about 50% of that comes from this Haber-Bosch process and agricultural biological nitrogen fixation. So what you might call human influence on that is about half of this total. The total that we can account for in total understanding current day is about 250 to 350. Even if you take 350 as being accounted for, it's still short. Our simple nitrogen bookkeeping isn't adding up. Now, it's quite a big miss. So you have to ask, well, where is all the rest of this nitrogen going? And here's the cycling, right? So let me just point out a couple of things. So first of all, some of that passes through us, but only about 17% of it does. Remembering that quite a lot of this is coming from the Haber-Bosch fossil fuel-driven Haber-Bosch process, but very inefficiently so. Of all the fertilizers we produce, only about 17% actually is eaten by us. The rest is one way or another is wasted. Quite a big problem, very big problem in certain parts of India. What else? Ultimately, a lot of that nitrogen, that excess nitrogen, ends up as nitrate in the groundwater and ends up in the oceans, and that processing load due to this extra nitrogen finding its way into the ocean has about doubled in the last 100 years, what we call the marine processing load. The cycle in that circle there is the marine chemistry processing of nitrogen, ultimately some of which ends up back in the atmosphere. But we've doubled the if you like, the load on that process. We should all think we need to be careful about that. And other things in the ocean are just not very well understood. N2O, a very dangerous chemical, has a lifetime of hundreds of years. Nitrate is fertilizing the ocean, so too much nitrate unprocessed is just going to change the ecosystem of the oceans. And some part of these things are accumulating in the deep ocean. Whether that's a good idea or not is not understood. So my kind of message from this slide is there's a lot to learn here. And as we talk more and more about sustainable N cycle, we need to know more and more about what the full cycle looks like. So the chemists can understand part of this, how to make it sustainable, meaning getting rid of fossil fuels from the process. But atmospheric and marine chemists and so on are needed to fully detail this picture and make sure we understand it. If we don't, then there's a real danger that we could repeat the mistakes of fossil carbon, we could repeat those mistakes, fossil carbon and climate change, we could repeat those mistakes in regard to the end cycle by switching from carbon fuels to nitrogen fuels. And that would be a very bad thing to do. So my message is here, we've got to be careful. So with that, I will just thank the guys in the team. And thank you for your attention, and hopefully I've sort of stayed reasonably on time. And certainly welcome any questions.
Thank you, Professor, for nice presentation. So now the session is open for question and answer. Maybe Nagesh is having some question. Nagesh?
Good afternoon, sir. Good to see you here today. I have been always delighted to see your research work, and always, especially in the area of energy and ionic liquids. Maybe last 4 years, before, I think 2-3 years, because we met during COVID. So I have been interacting with you during that time. And thank you so much for accepting our invitation, for delivering such a wonderful talk. Thank you, sir. Now,
Most welcome.
Always you introduce some new area of research, and because from ionic liquid, the energy, now this area. So definitely this process also, the ammonia, reduction of ammonia may be like a new area of research. So I gone through, like, while you were discussing, while you were delivering the lecture that time, how the kinetic control of this, the formation of ammonia against the H2 evaluation, because the processes, both the processes are very fast. So how you how to monitor such things, like electrochemically?
I didn't quite catch that, the last couple of sentences there. So how do I do what? Sorry.
Yeah, hydrogen evaluation, because when you pass the nitrogen and when you reduce, there will be a possibility that H2 may be involved again back. So against the formation of ammonia, how possible the reduction of ammonia against H2 formation?
Right. Okay. So I think the question is to do with almost the competition. Is this right, between hydrogen production and ammonia production in these cells? Yes. Right. Okay. Well, this is a very important question. Now, so one of our strategies that I talked about is to increase the nitrogen solubility. That helps to sort of push the nitrogen reduction reaction along. The other strategy is to try to inhibit the proton reduction reaction to hydrogen. Now you could say, okay, let's make this system completely anhydrous, no water, no other proton source. But of course we do need protons for the ammonia. The ammonia's got to come away with 3 hydrogens, of course. So the strategy then is to effectively optimize, is to limit the amount of proton source in order to have just enough. If lithium nitride is formed, then lithium nitride is a very strong, one way to think of it is that it's a very strong base, right? The nitride N3- ion is a very strong base. So it will rip the protons off of just about anything quicker than it can be reduced to hydrogen, sorry. So the strategy is to get the amount of the proton source and perhaps its acidity tuned, if you like, just right. And that's kind of one of the strategies that we're using at the moment, is to manipulate both of those things, the amount, but also its thermodynamic tendency to give up. So I'm now talking about the proton source, which could be water. In the process that I'm talking about, is the one that I showed a lot of results for, the most commonly used proton source is ethanol. Now you might ask, that's an unusual thing to use, but it is a good source of protons in a way that can be cycled, and the protons are a little less available than water. Right, so water is a little too acidic, a little too active in order for this process. It makes too much hydrogen. So ethanol partly cures that problem, and is obviously a very common thing to use.
Thank you, sir. Thank you, sir. Any other question from the audience? Okay, if there is no more question, on behalf of organizing committee, I would like to thank Professor McFarlane for a very nice lecture. Thank you, sir.
You're most welcome. And as I say, next time I would much prefer to be in Pune with you.
Okay.
Thank you, sir.
Now I hand over the digital dice to my colleague, Professor Rao. Okay. The next talk is from Professor Stephen Adams. I'm glad to introduce Professor Stephen Adams. Particularly, I have a lot of association with him for more than 15 years. To introduce him, Professor Stephen Adams did his PhD from Saarland University, Saarbrücken, Germany. Then he moved to Max Planck Institute, Stuttgart, where he worked with Professor Meyer. Then he completed his, he habilitated from Vatican University. Then he moved to National University of Singapore in 2005. He continued there at the Department of Material Science and Engineering. His research preliminarily deals with the rational design of inorganic materials and interfaces with optimal transport properties for advanced energy storage and conversion devices, with current focus on accelerated design of high safety lithium-ion and sodium-ion based batteries, in particular all-state batteries. He combines experimental data from electrochemistry, diffraction, and NMR, and try to get a high throughput computational design. He is the secretary for Asian Society of Solid-State Ionics, and he is the co-editor for Optocrystallography B. And he is a guest editor for several journals, international journals. He has more than 100 publications with more than 8,000 citations and more than 50 H-index. And under him, there are 13 PhDs completed and 4 more are ongoing. Above all, with my personal interaction, he's a great teacher. Once you attend his classes, you will never forget him. And his talk is tools for accelerated design of ionic conducting solids for energy storage applications. Sir, platform is for you.
Okay, thank you very much, Professor Rao, for your very kind introduction. And of course, you will see in this talk how you have contributed to this recent work. So we are working on different aspects here, where everything related to, let's say, batteries that make use of solid electrolytes. Not all are solid state batteries, but today I will focus more on the computational aspects, but also give some glimpse on how this led to devices. So this was, I think, lunch or dinner just after Dr. Rao left the group. So, okay, when you see such energy storage roadmaps now for many years, you have the impression, yeah, of course, the cathode has to go to a higher voltage, but the anode has to go away from graphite to something higher energy density. And the key point to enable this is always solid state electrolytes. And now suddenly all the companies come up with claims they have solved most of the issues, but there are also some companies like our Dyson here in Singapore that had to backtrack because it's not all that easy. So there's still room for further improvement of the materials. So what type of materials are we looking for? And they actually vary depending on your system design. If you really work on ceramic pellets as your solid electrolyte, then it's difficult to get, say, below 100 micrometers thickness. And then you need very high conductivities to have a acceptable current density in your system. And as you go to thinner systems, so you have to find technologies that allow you to have thinner solid electrolytes, then you can also work with materials that have lower conductivity, but maybe other processing or application advantages. So while the rest of the talk will focus more on the ceramic materials, I should mention that an important concept is to use these organic, inorganic composite membranes. I think there will be a talk later today on these materials. So here, for example, we have the Nasicon type materials, and they are combined with some organic materials here in tape casting. It's a highly stable material that we could then use in lithium-air batteries, or also by photopolymerization, which has the advantage that you have a much tighter control over the thickness, but you're a bit more limited in the types of polymers that you can easily use if you're not a specialist chemist in this area. So there, for us, we were mostly relying on pre-existing polymerization systems. But again, we can go to, let's say, 30 micrometers. Industry, of course, wants us to go further down to, say, 10 micrometers and still have a highly stable materials working on that. But for the rest of the talk, we will really look into the design of new materials. And yeah, traditionally, this was done by trial and error, essentially, and needed very experienced people to do that. And in the meanwhile, more and more, this is, in the end, the experience of the workers is replaced by databases that have this experience. And then you will see what are the features of the materials that make them suitable. And then can you predict new materials that should also be suitable? And some of these databases on this side are the computational databases. Here's maybe the experimental database, but most of them focus on the structure alone or on some static properties. This one is one that also gives you information on the ion transport pathway. So this is developed mostly by Shanghai Institute of Materials Genomics Institute, and we are involved in that. Okay, one approach I would like to explain here a little bit is our soft BV approach. So we take materials from the database, then check their plausibility, check the energy landscapes for the mobile ions therein, and from that make predictions on how the pathways look like, what are the barriers in, what would be suitable dopants, and then test these materials and feed this back into the database. Very simple software available freely from this source. Actually, this was from earlier this year, but in the meanwhile, some details here have changed, but doesn't matter. So we just take so-called CIF file, that's the standard crystal structure description files in such databases. Then you can see some basic information. You can check that the structure is plausible. There's also a tool then to look into the doping of the materials. We will come to that later, but first we will have a look into the ion mobility in these materials. And for that, we calculate so-called cube file. That's an energy landscape for point by point. We calculate what would be the energy of the mobile species if it would be at this position. And then we have a pathway analyzer algorithm, and that then tells us what are the migration barriers within this system, where are the equilibrium sites, where are the interstitial sites, and so on. And then there's also a link to a graphic display. And if you need more details, then you can get them in text form. So that, of course, these predictions are based on empirical methods, so we should check whether they make sense. So this is our predictions. This is DFT methods, and you see the barriers are reasonably correlated for such a fast screening method. And that is a major advantage of such a method. So you may, in one CPU hour, study 5,000 compounds with our approach, and you may need 100 CPU hours for one barrier with a normal DFT method. So it's, let's say, 10 to 100,000 times faster in practical applications. This is how it would typically look like. So simple sodium ion conductor in this case. When we have the structure, we can get the pathways for the ions, and we can get the migration barriers therein. So we can see at which point do we have a percolating pathway that is one-dimensional, two-dimensional, or three-dimensional in this system. And then we can, so actually this is here going into the depths of in this particular material, not so important. And then you can compare with experimental data, and you see the prediction is pretty close to what you find experimentally also. Okay, then that is of course used to better understand materials that are already known. So this is the LGPS. LGPS is one of the most important lithium-ion conducting sulfides. So the first compound was lithium germanium thiophosphate, but then this is a optimized composition with silicon here, with some chlorine here. And the main difference, you can see both have this highway for lithium ions, but the main difference is that the connection in perpendicular direction has a lower barrier for this compound, and that's why this material is kind of more three-dimensional, and therefore has even higher conductivity than this one. This has higher ionic conductivity than a typical organic lithium battery electrolyte. So the other common battery materials, like the Nasicon type materials, so that this exists in a low temperature monoclinic form, which is already reasonably well conducting, but then in the rhombohedral high temperature form, migration barriers go down even further. That's this form. We can use that to find new materials. So this was our Na11 SN2P Se12. This was the bond valence prediction. And then when we do molecular dynamics simulations, you can see that the pathways really look really similar to that. And then Dr. Rao came in and changed the way this is made to a more scalable method, and then demonstrated the first sodium selenium battery. So first all solid state sodium selenium battery made with these materials. This is more to show these bond valence calculations are then just the starting point. So once we identify a candidate, then we can go in depth. So these are DFT calculations to show, as we change the composition, what is really the optimum, what is the stable composition. And here, both for the this is the thiophosphate and that's ammonium sulfide. In both cases, the Na11 is the most stable composition. And when we do the, in this case, ab initio molecular dynamics simulations, then you also see other rather common thing is that solid electrolytes tend to have phase transitions. It's kind of inherent in such materials, because in order to be a good ionic conductor, you need to have more sites for the mobile species than you need to then you have the mobile species. But then slight changes in the energy as you heat up the material will be enough to lead to a redistribution of the materials. And in this particular case, this phase transition has then to do with the rotational disorder of the PS4 groups or SPS4 groups. But I think this is, I don't want to go into the details here, just to show. So once we have shortlisted a candidate, then we can go into more in-depth computational analysis, and we can go into making the material and making devices based on these materials. Another system we are currently looking at is the lithium tantalum phosphate. One side effect of our one-valence calculus is typically that for this problematic crystal structure analysis, you will often find that what is originally reported is only approximately true. Here, it was found that the lithium positions in the original report were a bit off, and when you then reanalyze them, you can see that, for example, this lithium 3 is not what was originally reported here on a high symmetry point, but it's not there. And then you can also better understand ion transfer pathways. So this was based on the pathways based on the original structure, and if you have the revised structure, then the pathways modify a little bit. So this is then DFT calculation, the MD calculation, sorry, and you see that this prediction and this again is very close to this. And this is really something you get in a few minutes on a PC. This is not very complicated to do. And as before, we can then look into this. And again, this material has a phase transition, in this case, very close to room temperature, where the monoclinic angle flips from above 90 degrees to below 90 degrees, or of course you can set the cell to have it the other way around if you wish. And when we do the analysis, we also see that the lithium distribution on the different sites changes, and that helps to understand why the activation energy seems to change with temperature in this material. So you see this curved shape of the Arrhenius plots. So that the slope here gives you the activation energy, but as you go to lower temperature, it seems to become steeper and steeper. Okay, when we look into making the materials, there we look also into getting it dense. That's a typical problem for oxide-based materials, that to really have high total conductivity, you must have a dense material. So the the bulk conductivity is always nice, but the total conductivity is really what you need, and that's typically rather poor. So here this is optimized conventional sintering, and if we do spark plasma sintering, we can push this a little bit further, and we can do it much faster. So this is again done in a few minutes. DFT studies show that the material has decent stability with cathodes, but limited stability on the anode side. So the green line here shows the voltage range over which it is stable, and correspondingly, if we just test it with lithium, you will see that, yeah, although the SPS, so the spark plasma sintered material, is better, you see that gradually here the resistance goes up, and therefore also the over potential here goes up, and in the end means we cannot use this material directly in contact with lithium, so we have to use higher voltage anodes, or we have to use coatings in between. And I think we've found a way to coat in the meanwhile. This is an example where we can see that the material, that the program not always gives you high ionic connectivity. So to be reliable, you also have to say if the connectivity is poor, that has to also come out from the system, and you get that here. So lithium iron phosphate is a decent lithium conductor, but sodium iron phosphate has a slightly different structure, maricide type, and that's actually a rather poor sodium conductor with a very high barrier here, 1.5 EV. So that's from DFT study, and when we do the small dots here are from our empirical prediction method, and we see that essentially we get almost the same. We also see that, yeah, because the method is computationally much cheaper, we can afford to look into more details of the pathway, whereas they have, for the DFT study, you have to make rather big steps. Here we can be as fine as we want. Okay, and the only way to use this material as a cathode material in battery is not to use this structure, but to use amorphous NaFePO4, and then you can actually get some rate performance, because in this amorphous material, so this is a structure model of the amorphous material that we made from molecular dynamics simulations with a force field optimized based on the crystalline phase, and then we see much lower barrier and therefore higher rate capability for these batteries. Oh, this is just an example from, if you heard Claire Gray's talk yesterday, lithium niobate tungstate as a good cathode material, high rate capability. Why is that so? So that's how the structure looks like. And when you look at the pathways, actually you have very low migration barriers here, around less than 0.5 EV in the perpendicular direction. And so with, say, 0.5 something EV in over all these block, you have good pathways into the depths in the, I think that's Y direction here, but the connectivity across here requires much higher migration barriers. So it's really a one-dimensional conductor, these materials, but it doesn't have the typical problems of one-dimensional conductors. Typically, one-dimensional conductors are easy to block because, yeah, if there's one foreign atom somewhere along the channel, then the whole channel is blocked. If you have such blocks of parallel one-dimensional channels that are interconnected, not percolating in this direction, but still over this block, then there's always a detour, and you can still also use this one-dimensional conductor. So that's why, so it's rather easily understandable why this is a decent material. Okay, but it doesn't always work. So in most cases, of course, it works, but there is a limitation. If you have so many mobile species in your system that the mobile species itself determines the packing of the crystal structure, then the prediction of the pathways from the other ions, from the immobile ions, becomes less accurate. And a typical example for that is oxide ion conductors, simple oxide ion conductors like zirconia, ceria. Yeah, 2/3 of all the atoms are the mobile species. Then, and they mainly feel the repulsion by other oxide ions. In that case, you still get roughly some trends, but this is no longer a quantitative prediction. So you really get a big scatter around the same trend. Only for those materials where you can say some parts of the oxide ions do not have no chance to be mobile. For example, they are part of a covalent network, so they are silicates. So you have rare earth silicates are some of the oxide ion conductors. Then you can say this: the ones bonded to silicon have no chance to move, reducing the number of mobile species, and then your prediction becomes accurate again. That's symbolized here by this full. But so this is a kind of warning sign. If you have too many ions of this mobile species and they determine the packing of the crystal structure, then you should not rely on these structures. Okay. But what are the benefits? Of course, you're no longer spent your whole thesis on studying one compound, but so this was done on one day. People can study the whole phase diagram of the system and identify where in this phase diagram are the promising sodium cathode materials. Here, the green ones are those with low migration barriers. Red ones are those with high migration barriers. And so the numbers give you the capacity of the material if the sodium can be used. But you see the problem. If you cycle the material, you go from a sodium-rich material to a sodium-poor material, and inevitably in this phase diagram, you always go to materials which have low chance or low diffusion coefficients for sodium. So you have to limit your capacity to a point that you're still in a range where the migration barriers are not too high so that you can cycle with decent rates. And you can then look at these phase diagrams also and say, oh, there's this nice green corner. Can I find structures that are in this corner and make them or turn them into solid electrolytes? So this was Na5 Fe04. That's a mixed conductor. If I replace the iron by aluminium, then I have a fast sodium ion conductors. And actually, yes, the prediction was fairly accurate. The material is not has no electrochemical window to speak of. So, but the prediction works very nicely. Another phase diagram that we should talk on is the lithium sulfide P2S5 LIX that we have studied again together with Dr. Prasad Rao, and there most of the known very high ionic conductivity sulfide materials are somehow related to this phase diagram. Cannot go into too much detail here. Some examples, the Li4 PS4. Just to see the pitfalls, ab initio molecular dynamics tells you extremely high ionic conductivity. When people make it, it has still high ionic conductivity, but not so super high. So there must be something wrong. And when we do our bond valence calculations, we are pretty much in agreement with the experimental data. That's the black line. And the blue line is molecular dynamics simulations, low temperature, fully in agreement with experimental data. But when we go up in temperature, short simulations give these values. Longer simulations give you then these higher values. Again, we have a phase transition where there's a disorder, rotational disorder of the PS4 group sets in, and that increases the conductivity. So ab initio molecular dynamics is right, and these data are right. So, but just the common way to interpret ab initio molecular dynamics data by extrapolating to this value as a room temperature value up here somewhere is nonsense. So this was a solid material. Maybe don't spend too much time on that. Rather stable compound, but low conductivity. And again, both the conductivity of pure material and the conductivity of doped materials we predicted, and what was found experimentally agrees well. Maybe skip this one just to tell a bit on electrode materials. So when we develop this for the solid electrolytes, it can almost in the same way be used to predict the rate capability of the mixed conducting materials, as long as they are limited by the ion diffusion, so only the insertion type electrode materials. So this is, I think, a picture for the sodium cases. See, always you have these sigmoidal curves, and then we can relink this shape and the critical points of it to the activation energy, to the dimensionality of the pathways, to the particle size, to tortuosity of the pathways. And so we can predict what it should be. So, and these are not fits to these curves. These were the Murray-Side type crystalline material. So this is from general analysis of the activation energies, we can get this curve, and then experimental data really follow this curve. And when we do this for the amorphous material, the three literature studies, and again, they closely mimic what we predict here. This point here seems to deviate a little bit, but we have to be a bit careful. Very commonly, you get some capacitive contribution for very finely distributed materials, and this slightly leads to this high rate capability. Okay. Just to show, there's a number of materials we can then combine. So we find in the analysis, this is a very high rate capability anode, this is a high rate capability cathode, this is a decent sodium ion conductor when doped in the right way, and then we could combine this and make a material. So this is a cross section of the solid state battery, again for Dr. Rao. And though the thickness of this solid electrolyte is surely a bit too high just for processing ease, you get decent capability, rate capability. So 2C means within a half hour you can charge and discharge, which for the solid state battery is still rather good. And you can use it over a very wide range from room temperature up to, so tested up to 100 degrees, but there's no reason why it shouldn't go up to 200 degrees. And such conditions are usually needed for the oil drilling sensors. Okay, last point I want to mention is that beyond the pure material, we'll also look into predicting a dopant to optimize the material. And so we come up with a machine learned combination of all these descriptors that we anyway need to know for the bond valence calculations. And then we can, for example, in a given material, like here bismuth iron oxide, say a particular dopant, on which side would it go? And you get this map of the site preference. Why did we choose this example? Just because there was a DFT-based reference for benchmarking. And while these can all be done again, I think less than an hour, really analyzing each compound. You see here those with this triangle, they are just guessed based on the trends seen, because DFT is so costly that they couldn't do it for all the materials. You can try to make it more quantitative, so we shouldn't go into much into detail here. Dopant effect solution energy or dopant solubility, you can really link the predictor value to these properties. And we can use that, again, coming to our lithium tantalum phosphate. So for example, on the tantalum side, maybe ruthenium would be the nicest dopant. On phosphorus side, sulfur we may not wish to have there for other reasons, but then we take the next one, silicon, and then really the silicon doped material can be made. And actually the program will also predict it doesn't help ionic conductivity really, because there are already so many vacant sites that this aliovalent dopant really has no influence. Okay, maybe as time we don't talk too much on this. So we try to extend this also to absolute conductivity predictions, but we skipped that. Just a few last words on moving on from individual materials to interfaces. That's really should be a strength of the material because it's computationally so cheap that we can go into those areas that are difficult to achieve by methods like DFT that are computationally much more costly. So for example, here we can predict why when you lithium iron phosphate, you coat it with lithium phosphate glass, the lithium conductivity goes up tremendously. What are these are the, in a cross section, you have this surface region has different energy profiles, and from that you can, if you translate that, you get exactly what is experimentally observed, the high ionic conductivities. Again, we like to combine DFT studies. So this is, for example, a DFT structure model of an interface between an electrode material and a ionic conductor. And there we use the structure from DFT, but then analyze what should happen, what are the easiest processes to happen, and where should ion transport happen, where should chemical reactions happen from our bond valence analysis. And then we tune with that larger scale empirical simulations where we can see, for example, here, the processes that lead to the decomposition of the surfaces, and then we can have a rational way to prevent this by the suitable coatings or such things. Okay, with that, I think I should come to the end. I should only focus on this method has the advantage. It's so simple. Every one of your students can do this if it has access to the CIF files, to crystal structures, can get these files and quickly has an idea of how ion transport pathways in this material would look like, and then can do the right type of higher level simulations or experimental studies to go deeper into these materials. And with that, I should thank you for your attention, and of course, people who have done the work and the funding agency.
Thank you, Professor. The talk is open for discussion. Is there anyone who wants to ask some questions?
Hi, Professor Adam, Dr. Kali here.
Yes.
So how this study, means your interface study is, your simulation study is useful for our interface study? Whether it is so much variation in the practical or something like that you observe in the interface study?
Okay, the interface studies are mostly to see what are the side reactions, like here. So this is a sodium cobalt oxide, and the cobalt then reacts with the sulfur here. That does the side reaction leading to the decomposition of the materials. That are the things that we have to see, and then we can also see how fast can this happen. Thermodynamically, it's very clear that none of the sulfide ion conductors or sulfide-based lithium-ion conductors, sodium-ion conductors is thermodynamically stable enough to be of practical use.
Yes.
But somehow in some cases it works, in some other cases it doesn't work, and so it's more the kinetics that decides whether the material is practically useful. So again, how fast do the reactions happen? What are the barriers against these processes? So like in the previous talk, all these reactions shown should easily happen thermodynamically, but nitrogen doesn't react so easily, so you have a huge activation energy. And so it's more to see how can we tune the materials so that those processes we don't want to have the high activation barrier, those processes we want to proceed fast have the low migration barrier. For example, you can also go to what Claire Gray showed. You can think of this as a, let me see, as a, yeah, a symbolic sketch of nanoparticles. So within the nanoparticle, your ion transport is fast, and the limiting point is to get across here. And then we have to see how we can put these particles together. If they are like particles, then yeah, as soon as we ensure a matching path, it should work. If they are different particles, we still have to see would that lead to a redistribution of the particles. So many of the good lithium-ion conductors, oh, that was what I skipped. Let me see, there was this mixed agrodites. So here you see two different building blocks. You can think of different regions of the crystal structure are different materials. And then there will also be a redistribution of the mobile species. You may have space charge layers between these regions, and all these affects the ion transport. And this can all be studied by such simple approaches.
Suppose in some of the some people are talking about the core shell structure. Suppose this is suppose the sulfide, your sulfide electrolyte is again have putting up some other conductive little conductive stable electrolyte, solid electrolyte. Where it works?
Yeah, sure. We have studied for a number of cases then sulfide solid electrolytes with some atomic layer deposition of high stability materials like niobium oxide or such things, and then that's definitely a key approach to do that. So that's why we study this intensely.
Thank you.
Any questions, please? I have one question, the last one, just because maybe I missed that one. What is the size you consider for interface study for the last example you have given?
For the interface studies, here, okay, you know, typically the DFT may have just a few hundred atoms. But when we kind of tune the studies based on these structures, then we can go to 10 or 100,000 atoms, and so above 100,000 atoms, that's becomes challenging too. But at least we get an order of magnitude larger. But more importantly, so I think this may only be 5 to 10,000 atoms, but you can run it for much longer time. So many of the things look nice at the first moment. Just the DFT calculations are too short. They may run only 100 picoseconds. Honestly, in the back of this, I'm running a DFT calculation now for just 5 picoseconds. I would never run a an empirical simulation for such short time, because all these processes will be slow. So I need for hundreds of nanoseconds is what we look for at least, and then still we may need to go to a bit elevated temperature to accelerate things. Then only we see these decomposition processes or the first signs in these empirical models. So we need larger systems, and we need to run the simulations for much longer time, and that cannot be done currently with the DFT systems.
Professor Adam, we should have good collaboration now on this, because
yes. So we have the right link.
Yeah.
in Prasad Rao, so who knows all
Professor
these
Rao
techniques.
is always there with us, so I think take the
So
advantage.
you have seen his name throughout the cited publications here.
I know.
Yeah.
I think Dr. Rao will continue that. That will be better for CIMET.
Okay,
Yeah,
great.
sure. Okay, if there is no questions, again, thank you, Professor Adams, for giving your time. Hope we'll meet in Pune as soon as possible.
Yes, so that was long planned, but
yeah, it is a long plan, and so we will hope this will happen at least the end of this year somewhere. Okay, so if there is no more questions, now the session will be break for lunch. We will meet back about 2 o'clock India time. Thank you, sir.
Okay,
Thank you
enjoy
very
your
much.
lunch.
Here's my card. Thank you. Shukriya. Shukriya. Thank you. Before my 50th birthday was passed, and I had taken my bet talking to myself that I visit 50 institutions of repute all over the country. And I did it. Wow. That's good. But that's the fun, you know. I visited like from Punjab, the Guru Nanak hospitals and medical college, amazing. From north to south. Are we showing a presentation also? Or let's see. Yeah. The time, why not? Here they reach, sir. We are in Dr. Kale's cabin. He is not there, sir. He's gone for lunch. I think he will be joining us. We are waiting for you, sir. Thank you. Right. Thank you. That's here. And maybe the office, I just find out how far it is from here. You sent me the maybe yeah, no? The Google map. No, shut it up. You are not sending me the location.
Ranjit, for the time being, you can unmute or mute. Sorry.
Yes. Yes, good afternoon, sir. Yes, sir. Good afternoon. Good afternoon. Same here again. Same here. We have definitely met. Now you know. Just finished it. Oh, yeah. Mr. Dheeraj. Mr. Dheeraj? Okay, sure. Right. Thank you. I think you say what would you do next? I don't have much of that. I only have a thoughts. What was?
I have lost 12 kilos during the lockdown consciously. There's the food control. No. And last April, like I was feeling like a pregnant couple. I need to do something. 97. I said, this is ridiculous. I've never seen myself in the 90s. It's like, at this rate, I'm very 100 every time. Very, very, very well. I can't do this. I can't imagine you as 97. So I started running. Wow. And then it took me a month to reach up to 2 kilometers. That's fine. I used to run.
Good afternoon. Yes, kind suggestion to the CMET Pune team. You please, because it's anyway a lunch break, can you kindly keep it mute so that our discussions need not go out?
Right. Good morning.
Hello, Professor Anish, sir.
Yeah, can you hear me?
So please start your camera.
I don't know why my camera is not working.
Yeah.
My video is on. Can you see?
Yes, sir. Yes, sir.
Okay. So shall I start?
No, sir. No, sir. Wait, few minutes. Please.
Shall I start really?
Yes, yes, yes.
Good afternoon, sir.
Good afternoon.
I'll give you a brief introduction about you, and then we'll start.
Okay.
Good afternoon to everyone. I am very happy to introduce you to our first speaker post-lunch session, Professor Animesh Jha. Professor Animesh Jha is a full-time professor of material science at the University of Leeds. His main research interest is in the areas of photonic materials and devices, light and matter interaction, and applications of such processes in device engineering. The above topic manifests Professor Jha's interest, which he has taken forward for exploring a range of applications in collaboration with two established laboratories in India. Professor Jha is also Fellow of the Institute of Physics, London, Royal Society of Chemistry, UK, and Optical Society of America. He has published over 440 papers in journals and conferences. He obtained his PE in metallurgy in 1979 from the University of Roorkee, India. Then he obtained ME in metallurgical engineering in 1981 from Indian Institute of Science, Bangalore, India. And later he obtained his PhD and DSc from the Imperial College of London in 1984. Today he is going to discuss about QDOS structures in glass for solar energy harvesting. May I now request Professor Animesh Jha to start his invited talk. Thank you.
Thank you. So how do I share screen? I can't see my file is open. So maybe. Well, can you see my screen?
No, sir. But have you gone to share screen option that is there at the bottom?
Yeah, I'm trying to share screen, but I can't share screen. This is okay. Just to let me. Do I have to join and sign meeting? I'm already there.
No, sir. No, sir. It's not required.
Okay.
Please close this window so that I think there will be less windows on the screen.
I don't know why it's not sharing the screen. Let me leave and join again, okay? Just a moment. Oh, sharing screen has stopped as this window is closed. Okay. Share screen. Now we can see. Can you see the screen?
Yes. Yes, sir. Yeah.
Okay, thank you. So, good afternoon. My presentation, as introduced by the chair, is on quantum dot structures for solar energy harvesting.
So next 30 minutes, I shall be talking about what is the goal of this project.
Excuse me, sir. Sir, just a minute.
Yeah.
Can you go to slideshow so that
Oh, sorry.
slideshow?
Yeah. So next 35 minutes, I shall be talking about quantum dot structures for solar energy harvesting and its importance in global context, basically. So, and if you have any questions after that, I would try to answer at the end of the talk. So this is a UK-India partnership seeking global solution for clean water and clean energy. The project has been supported by the Royal Society London for international collaboration with the CMET lab. It's also supported by the UKRI PhD program. And I also have another project with UKIERI, which is finishing soon, with ICER Bhopal. So in the Royal Society program, my collaboration is with CMET Lab Pune and the Savitribai Phule University, Pune. So this presentation would illustrate how we have come about together to deliver a research program and potentially a pilot scale development program, which would demonstrate the importance of this research for social and socio-economic benefit and techno-economic benefits, okay? So the context of my international R&D program is with, sorry, before I go, I must emphasize, without the help of PhD and undergraduate students, this program wouldn't have been possible. So you can see here the names of people: Vijay, Raj, Monad, James, Natasha, and Mubashir. They are the people who have been doing the hard work in the laboratory. And Dr. Kale, Prof. Gosavi from Pune University, we are supervising. So basically reaping the rewards of the students' hard work. So context of international R&D program: develop novel optoelectronic functions for energy harvesting using quantum dot and 2D layered materials on glass surface, and then carry out structure and analysis and heat transfer measurements and modeling. Very important if we want to understand energy models, energy transport models, and how does structure affect the energy transport, and develop manufacturing approach. So this is not just pure research. We want to make products out of it, and how does it impact in terms of collaboration with industry, which I will also talk. And we want to also look at new applications for exploiting this kind of structures in glass for energy harvesting. So I want to emphasize very important point here, and I would encourage all the people to spend some time exploring United Nations Sustainable Development Program. And that defines 17 different goals, which are listed here on the right-hand side. And goal number 6 and goal number 7 are sustainable development goals on clean water and sanitation and clean energy. Okay. I also want to emphasize United Nations distinguished scientists globally last year, in 2019, identified that if we do not control the emission and the global temperature rises more than 2 degrees, at least 1 million species will die. they will not be able to survive the climate change. That's a very sad thing to say, but it is a fact. And that's where um, our contribution as human beings is important, that we should explore how to curtail the global greenhouse gas emissions and maintain our environment so that we can live in harmony with the species which also support our lives, and vice versa. We have a we should have a corporate responsibility. I use this business like term, but that's nature is a business, and we have to have a corporate responsibility for that. In the same way, we must, as we rely on oceans, we have to support oceans. Without lives, without species living in oceans, we would not be able to survive. That's for sure. We are the last people to come on the planet, and maybe we will be the first people to go if we do not take care of the planet. So that's a very important message I would like to give. The other aspect of water, particularly, is extremely sad. Um, if we don't have clean water, this is data on the left-hand side. You see a picture of a child, and it has some statistics here. Nearly 2,195 children die. This is like 32 school buses of children die every day from diarrhea. And this is United States Department of Health and Prevention of Disease reporting. These are very accurate data collected over tens of years. And that's particularly sad. 1 in 9 children dies from diarrhea. Okay? And globally, every year, 800,000 children die from diarrhea. And diarrhea is caused by rotavirus. And it's prevalent in all over tropical world, subtropical world. And if children consume dirty water, any animal waste, human waste infested water, then this is the cause. And sad part, one of the saddest parts was the epidemic, cholera epidemic in Yemen in 2017, which affected more than 1 million people. And you know, here is the data: 2,261 people died in that epidemic. And one of the causes of the transmission of cholera is water, and patient is so sick that patient cannot hold water inside the body, so it vomits. Patient suffers from diarrhea-like symptoms. So the first thing doctors do is basically prevent the vomiting and diarrhea-like symptoms, because if the patient cannot hold water, patient will die, basically. And this is one of the tragedies of dirty water. Okay, so making available clean water for everyone is our another very big responsibility. If we don't have clean energy, children cannot breathe clean air. If we don't have clean water, they will suffer from these sad diseases like diarrhea and cholera. Okay, coming to basic science and basic physics, material science, etc. So I'll start with the global map of solar radiation. So this picture here on the left-hand side is showing you equatorial distribution of solar radiation across the Tropic of Cancer and the Tropic of Capricorn. As you can see, this part of the world also is the home for nearly 67 to 70% of the world's population. Okay, this part of the world is blessed with sunlight and also blessed with plenty of water because of the type of natural resources we have, the forest we have, the way Earth spins around its axis, and that's how the weather is controlled, and we get plenty of rain, plenty of water. Sadly, this is the part of the world which suffers the most acute shortages of water time after time. And India is a very good example, as you know. So why this situation has been arising, and the blame is population growth, poor water distribution network, poor water management system. Okay, so one of the ways we can change that, if we empower people and the community with water resources, that they produce their own water locally. That way we can change people's attitude, and therefore we can educate people the importance of pure water, drinking and consuming pure water for cooking, as well as for bathing and laundries. So if you look at the solar energy distribution in India, different parts of India has different intensity, radiation density. So these are measured in terms of kilowatt hour per meter square. So if you go to north, the average density is less than 4.5. As you come down south, the average density, as we are moving more towards equator, the parts of India are very hot, as we know. And that's where we think this kind of solar energy harvesting technology would benefit. I also want to emphasize one very important point, that the more you dump things like polymer, etc., in the water, the worse the pollution situation is, because the polymer degrades in water very, very slowly. And when it degrades, it also produces very small sub-micrometer to nanometer scale particles, and they do not submerge into the deep sea. They tend to float. Many of the laundry products you have, cleaning agents, also have polymers in it. And it is again another disaster which we are facing, that ocean water is so polluted that we are contaminating the entire food chain. Impact of warmer ocean water is also detrimental for weather, because we see unpredictable behavior of weather patterns all the time these days. The right-hand side slide shows you the electromagnetic radiation absorption of water, and corresponds very well. If you have clean water, it would, the minimum absorption is at around green wavelength, as you can see here. But if you contaminate with plastics, etc., then this shape will change quite dramatically. Okay, so these are some of the topics I think would be of importance in future: energy harvesting, hydrogen generation, photocatalytic reaction, interaction of chemicals for biotechnology, large area functional coating for building and environment, for built environment where we can also capture energy. So these are some very important aspects of quantum dot structures which would emerge in future. So to summarize, just very important points. This is the vision picture. This picture here, right in the middle, you see the solar radiation map, and that's the distribution of solar energy when it falls on the surface of Earth. So you have ultraviolet from 250 going up to maybe 400 nanometers. Then you have visible radiation. Then quite a large part is infrared. So you may ask, why can't we do this in ordinary glass? Well, you can't do it in ordinary glass because ordinary glass transmits quite strongly in the some parts from ultraviolet to infrared. So you would not be able to capture solar energy. It would transmit through, and that's why you cannot use just ordinary glass. And if we put color centers like quantum dots, that's where the change in the absorption behavior takes place. And this is quite nicely illustrated in this picture of UV spectroscopy of a quantum dot. And you can see how strong the absorption is in the red curve. As we control the size of the particle, the quantum dots change and help in absorbing large amount of energy. And that's quite important. So what we are trying to say here, the energy absorption is dependent on the color centers in the glass. That's the summary of it. And if we can enhance this property inside the glass, we then understand how the energy migration is going to take place on a nanoscale or a sub-nanoscale. And that's a phenomenal statement, I would say, that how energy is controlled on a nanoscale. Okay, considering the wavelength of the photons is much, much larger than the quantum dots we're talking about. So you can see where the beauty of physics is. Okay, so we can still utilize famous models like Kirchhoff's model, where you can define energy absorption equal to absorbance times incident radiation, and then use the black body radiation model and define the energy in terms of mass times the specific heat times the temperature difference, and use the standard model to characterize the energy absorption. So when you have things like cadmium sulfide doped glass or manganese doped cadmium sulfide glass, and you make it and then you heat treat it, the color changes, as you can see, depending upon how you heat treat it. And that you can follow up using X-ray powder diffraction technique. So here you can see how the crystallization inside the glass has begun. And this crystallization relates with the formation of quantum dots, which we'll discuss a bit later in more detail. So these are basically silicate glasses, some of which Dr. Kale and our group have already published. So these are just basically dopants. We use CDS and we also use terbium, rare earths. So when we make, as the glass is produced, you can see the amorphous X-ray diffraction peak when there's no heat treatment. As we provide heat treatment, the glass starts becoming more crystalline, and we can see at high temperature crystallization is beginning. And that's consistent with a lot of previous studies which Dr. Kale's group Professor Wasabi's group have done. So this is just another example with terbium. Okay. What is spectacular is the behavior of the absorption curves. Depending upon which rare earth and which quantum dots you use, the change in the shape of the absorption, ultraviolet to infrared absorption, changes quite dramatically. Huge absorption, and this is what I would have expected. So this kind of change in the absorption is fundamental for energy harvesting. Okay, and again, I said to you guys that here is the electron microscopy image of quantum dots in the glass. So the darker gray part you're seeing are basically quantum dots. The amorphous background is glass. And what I want to emphasize to our listeners here, particularly young scientists, this is electron diffraction image. And you're seeing contrast. That means that diffracted beam is interacting with different chemical species and producing that contrast. So if you say, oh, because this is amorphous, we won't see anything in the glass. No, that's not true. In fact, if you can see the scattering of electrons, the scattering pattern from the background tells you that how much is the local variation in the composition of the glass. Okay, so there is quite a lot of contrast variation, especially throughout the glass structure. Although it is amorphous, but yet you can resolve that. This is very interesting because electron wavelength is 0.025 angstrom. Okay, and you can work that out from De Broglie's model, whereas you're looking at the scales of quantum dot, which are in few nanometer scale. So you have a very nice wavelength to observe particles, analyze particles. So as you magnify, you can just about to see distinction between the matrix. The bright phase is the quantum dots and the dark phase is the matrix. So how these quantum dots are basically crystallizing, you are able to see it. Okay, next part is the model. How we characterize heat transfer. So basically, my assumption has been to ask my students to look at that, think that you have a glass reactor and energy is falling and you formed a quantum dot layer, and as the energy is passing through, the light is being absorbed into the quantum dot and then heat is extracted by the water. So that's the model we are looking at. So again, recapping on what we have seen before, this is your solar radiation here, map, and that's the quantum dot structure. And again, I'll emphasize, depending upon the heat treatment and depending upon the composition of the quantum dots, we see very strong absorption. That's where the material science comes in. I won't go into the details of the model equation, but we have worked quite a lot and developed the model equation for heating of the glass only using a lamp, which is about 400 watts in power, output power. So what we do basically is simulate the condition which replicates the solar radiation map in India. For example, we can design any kind of radiation mapping because we have radiometer, which we use to measure the radiation falling on the glass surface. And we also use similar kind of approach for modeling when glass is in contact with water. So you have a heat source, heat sink, and heat source, heat sink with water and without water. So we're basically taking all those factors into account. This is not something new. There's quite a lot of background literature, but we have adapted the literature for our own scenario. The key message here we have is how does the quantum dot change the absorptivity, heat absorption inside the glass. So basically what you're saying, how does the specific heat capacity of the glass have changed, which is contributing to enhance heat transfer. Okay, so if we then start looking at the photothermal heat transfer, this is what we are seeing in one of the categories of glasses we are looking at is tellurium oxide glass. And these have high heat capacity in general. And depending upon how we use the the different types of dopants, we have temperature rise, and then we switch off, and then we characterize how the heat loss is taking place. Okay, so you can see here the maximum temperature here is 75, plateauing around 75 degrees Celsius. Also, please note this temperature rise is extremely fast. Within 10-15 minutes, we are reaching almost 75 degrees centigrade. When we insulate, we can reach above 100 degrees centigrade very, very quickly. This is important, particularly when you're thinking of producing hot water. And why these things are important now, we can do these measurements and then start doing larger scale model design systems. And again, comparing the model, so we have been modeling. So you can see the model quite nicely follows. There are some differences because we don't have yet correct CP data. So when we model the CP, we will get very good fit. This is the temperature rise in a Pyrex glass. You can see how slow that is, and it's only going up to 60 degrees centigrade. Whereas here we are going very, very rapidly to 70 degrees centigrade. So this speed of temperature rise is very important because you don't want to wait 2.5 hours or 3 hours for hot water to come. Okay, so it could be quite useful in a larger system, but what we want to design is an efficient heat transfer system so that the water can be heated quite rapidly. This is another important development which we have brought out through collaboration with the Pune University, particularly Professor Basavi. He has been very helpful in making us understand what facilities are there. So Department of Science and Technology invested huge amount of money in building a solar farm outside Pune, which is about 50 kilometers away, I think. And this farm, I'll show you a picture in a moment, is based on using Pyrex glass in the solar concentrator. So our idea is to replace the Pyrex glass and use our quantum dot engineered glass and see how fast we can heat the water in a solar concentrator, and can we produce hot water very quickly and then store that hot water and continue in a quantum dot vessel, basically, so that water remains warm throughout the day. And if we want to then insulate this water, we transfer into a storage tank where it will remain insulated for domestic use or community use. Okay, so these are the just concepts. So that's the solar farm. You can see large number of, I think there are more than few hundred concentrators, and you can see the streaks of bright light here, and these are the concentrators, and the concentrators are basically tracking the sun. So it's already mechanically controlled from remote, and this is basically a power generating station. So from these solar concentrators, they are able to produce 125 kilowatts of steam power. I'm talking about steam power. That means the temperature at the end of the cycle reaches more than 175. In some parts, I have been to this farm. I've seen steam being generated at 200 degrees centigrade, and that then drives a turbine, and you generate power, and that power is fed into the village, nearby village, where electricity is distributed. So that's a huge, huge benefit to the local community, and that's exactly what we want to see. Our goal is how to make whole thing far more economical so that every home can have it. Okay, so that's the ultimate goal. So that's my last slide. So we started this project after discussing with Dr. Kale in 2017, March. Actually, it was this day in March in Pune when I was attending the anniversary day. It also coincided with the International Women's Day. So we were there and we discussed this project, and then we won the grant later that year in 2017, and that's how the project started. We would have done a lot of work last year, but I just was there last year in March discussing how we should carry out experiment at the SPPU's solar farm, and then COVID hit us. So experiments, we have just predominantly focused on modeling and doing experiments here in university. But what I want to also tell you, something very new has happened. Last year during COVID, our UK government also announced a big clean glass manufacturing program. And this is a 30 million investment, which will help us in making a in commissioning a pilot scale facility in St. Helens near Liverpool. Liverpool region is very, very industrially driven. They have lots of chemicals and glass factory there. So that's one of the regions. This part of the UK was chosen. And at the moment, the pilot plant is being commissioned. And the goal here in this Glass Futures Limited is to produce clean glass. That means so net zero emission. So we want to curtail greenhouse gas emission and also make glass products which will save energy and cut down emission from during application. So when we say during application, means if we make window glass, that should be saving energy. And if we make display devices, that should be saving energy. And there in applications, this is where we see quantum dot structures can make a big transformation in energy saving. So with this statement, I would say I would like to thank you, all of you, for paying attention to my talk. And if you have any questions, please let me know. Thank you. Yogesh? Hello, Yogesh.
Sir, good afternoon.
Thanks a lot, sir, for your nice lecture. It's really an innovative approach. The session is open for some questions.
Sir, good afternoon, sir.
Hi.
Thank you so much for the excellent and useful presentation and the way to move forward in collaborative projects. I think this is a classic example where the university, industry, and has taken up a pilot plant and brought it the item out. That's really great. Sir, as for this last slide, which is there being presented, 30 million investment. So this is in the pipeline or already?
No, the investment has come in from the government, and as we speak, the pilot plant work has already begun. So this work will complete by 2023. We want to expand this collaboration with international links, and one of my goals is also to extend this collaboration in India and work with wider communities, not just in UK. This is not just for UK, because as I said, climate change is not just for UK, it's a global problem. And we all have to make our own contribution. And that's quite important. So this is why this Center of Excellence has been created.
Thank you, sir.
Any other question? Sir, I have one question.
Yes.
You have shown that there is a plant which is there in the village near Pune, and water gets heated, and then the turbine runs to generate electricity. Now that water which is there after the generation of electricity, can it be used for drinking purposes?
Yeah, that's a very useful question and very nice question, actually, I should say. The whole idea is the water, superheated water, will be collected into the storage tank, and it will be filtered so that we can use it for community use or drinking water use. One downside of overheating the water is the mineral loss. So we will have to make adjustment for mineral loss, and that would be then useful. By the way, we are also considering at the moment how to cool the water using solar energy, and that's a new physics. Okay.
I think, sir, that thermoelectric coolers can be useful in that sense.
You see, thermoelectric coolers are very expensive. I tell you this because I have spent more than 20 years of my time in research in optical communication system, and I have looked at big network systems. An amount of heat generated in network systems is so much. So, for example, if you look at Google's server houses or Yahoo's server houses, you would require a mini nuclear power station to support the heat, the cooling in these server houses, amount of heat which is liberated. So, capturing the waste heat is very difficult, and particularly the low grade waste heat, which are below 200 degrees centigrade, because you are limited by the laws of the third law of thermodynamics and second law of thermodynamics. Okay, so that's quite challenging, and that's why if you develop some other ways of cooling, that's much better than just think about standard thermoelectric cooling, because thermoelectric coolers are there, but they are not very efficient. You have to come up with some better solution.
there are no more questions, let us thank Dr. Ramesh Jha for such a nice introduction, nice lecture. Thank you very much, sir.
Thank you. Thank you very
Now
much.
I hand over the session to Dr. S.B. Rani. Thank you.
Hi, Nandish.
Hello, hi. Good
Hello.
good afternoon.
Good afternoon. Good afternoon. After almost more than 1.5 years, we are meeting on to online platform.
Yes.
After
Yes.
I think this quantum dot workshop.
That's right. Yes.
So let me introduce Dr. Nandish. Nandish is a basically chemical engineer with an executive MBA with more than 25 years of experience working in various industrial sectors, managing a multidisciplinary engineering team on research and commercial projects, ranging from basic concept developments, pilot plant design, to full production scale design, including installation, commissioning, training, and handover. Dr. Nandish has worked across a range of market sectors, including specialty chemicals, pharmaceutical, biotechnology, FMCG, energy and environment for diverse mix of clients from SMEs to research organizations to multinational blue chip companies. So, Dr. Nandish is having expertise in the areas of engineering design and field project management, manufacturing operations, product and process development, business operations and management. With this small introduction, I would like to invite Dr. Nandish to deliver a lecture on importance of techno-economic analysis in projects on this MEMP 2021 platform.
Thank you. Thank you very much. I'll just.
Dr. Animesh, Professor Animesh.
Can you see my screen now?
Yes, we can see.
You can see. Okay. Okay. Yes, I think as a quick introduction, so as to where, thanks for the lovely introduction. Thank you. And just to pick up on some of the things which Animesh spoke about in the last session. I mean, myself, Animesh, Dr. Kale, Dr. Gosavi, and others, we worked on this quantum dots, and we were there about 2 years ago, and that's when we first met, and we were talking about this conference, and I thought, the last time I put this concept of science to society, so I wanted to elaborate further on it and talk about techno-economic analysis. My experience is more on the specialty pharmaceutical side of things, but I hope things which I talk here will be useful for everyone, because some of the basic concepts remain the same. And just to finish on something which Animesh, you spoke about, in regards to low-grade heat, it is a difficult problem, but I think there are more and more solutions coming out. We came across something recently, which uses the organic ranking cycle to generate power, but this has been used on ships, on cruise liner ships and so on, where there's plenty of cooling water available, and therefore the economics stack up. So that's something which we can discuss later on. So coming back to my session here, so I just want to give a very quick introduction in regards, Mandrachem, the company which I own, who we are, what we do, and what role we can play, and what role we have played in various projects. Then I wanted to just touch upon this technology readiness levels, because we work with a wide, different, diverse range of projects. So I think I just wanted to talk about what is a TRL, then talk about the commercial path, what are the different steps in the science to society journey. Then I want to just talk about techno-economic analysis as to what is it, when is it to be carried out, how is it done, and benefits, and how we see on a lot of the projects which we are working on, how it has helped us to hone the design, to make it commercially viable, to help us think out of the box and come out with solutions. And then I'll just summarize it. So, and I hope it will be, everyone will have something to take from this talk here. So a quick introduction. So Mandrakem, our strapline is as it says, making it possible. We try to make it possible for our clients. So the company was formed in 1990. I've been working in the industry for nearly 25 years. And sorry, I think there's something, yeah. And I worked in this industry, and we worked on a lot of projects, over 1,700 projects since its formation in 1990. And what it allows us to do is actually give us experience of working on different projects and using some of the cross-fertilization of ideas. So basically, we worked on projects which are, small scale, development scale to right full commercial scale. We worked on projects which are, only 5 to 10,000 pounds to worth 20 million pounds. We worked on projects which are like batch-wise or continuous. So all these different type of projects and in different sort of subjects and in different sort of disciplines, different areas, right from nuclear, chemical, pharmaceutical, food, allied industries, gives us the options to have new ideas where we can use to address the challenges, the technical issues, and use that. And in the process, as you can see from this slide, again, sorry, going back to that, we won quite a few awards, and that's our office here, which you can see on the left-hand side, for all our efforts in there. And the way we make it happen is because we have a multidisciplinary team. Out in my office here, I've got people who are process engineers, chemical engineers. I've got people who are sort of mechanical engineers, some electrical control and instrumentation engineers, designers, draftsmen. So what it allows is actually that we can use all their skill sets to help us deal with projects, and that so that we don't have any blind spots. So we can address if there's a challenge, we need to then pool together our resources and come out with solutions which are technical and economically viable as well. Like Animesh was saying earlier about the chillers, we need to have something, technology, and having a solution is one thing, but having it economically feasible is the challenge. And we come across this challenge on a lot of projects. I mean, this project execution scope, this is what we tend to do for our run-of-the-mill projects, where we go through the initial engineering stage, where it could be just a concept stage where we're trying to get a quick feel for cost estimation. It could be as simple as trying to get a plus minus 30 or plus minus 50% cost estimate, or you can go all the way up to the detail engineering stage where you can get up to plus minus 10%. So economically, you can understand. So we can get a very good feel for the project costings, and therefore then that allows you to do the full techno-economic analysis. And the reason I'm saying all this is I think it's useful to get companies like us, it may not be us particularly, but similar to us, on board as part of the collaboration strategy, because we can allow things to make it possible. We can take it from the initial design stage, to the procurement stage, and then the construction management and commissioning stage. We've got here, local regulations in UK, so we need to train people in certain regulations. They have to go on training courses, but that allows us to actually also build projects. I think once I start going through some of the examples, it will help to sort of crystallize those thoughts. So this is a project typical life cycle. So if we start with the conceptual, again there'll be some which will. These are again projects which have a decent technology readiness level. I think there are some projects where it's really early stage. So in which case there will be a very rough estimate. Whereas if there is a lot of details in there, then we can look into it and try to sort of get more input into it. Again, the overall emphasis is to start with, there's a lot of risk, lot of uncertainty. And what we are trying to do is actually get and reduce by doing more work. We try to reduce the uncertainties, give it a better chance of success. We try to reduce the overall risk, to do so that, for investors or anybody who wanting to look into it a bit more, it's easier. So these are the two graphs, so the one on the left hand side here, which talks about the uncertainty cost profile. So as you can see, initially there's a lot of uncertainty, and as you start going through the project, you start to reduce the uncertainty, you start to reduce the uncertainty profile, and therefore the risk. And also the decisions influence on time. The more it's easier to make any changes earlier on in the project because it costs less. Once you're further on into the project, it's then actually very difficult. It's also very expensive to make those changes. In regards how we add value, in regards overall technical and commercial risk, because we have a range of sort of multidisciplinary team who got. Sorry about this. I don't know. It just seems to be just moving on. We have range of people who actually can work on the chemistry side, but also on the chemical engineering side, on the basic science, but also on this sort of detail engineering side. We have all these peoples. Let me just, sorry, I think what I'll do is, yes. Sorry, can you still see my slides?
Can you make it PowerPoint?
Yeah, I think for some slideshow. Yeah, I think what's happening is just moving on actually. So I think someone's just put some. Okay. Yeah. So
now it's okay.
Okay. I think so. Then we actually have got all these different skill sets which will help in the overall support on science to society journey. Now what I'll do actually is touch upon this technology readiness levels. Can I just ask actually, have you heard about the TRL levels so that I don't...
Yes.
Yeah. Okay. You heard about this. What's happening is actually the slides seem to be moving. So is it okay if I just show it this way and I'll just reduce this?
No, it's okay.
Yeah, it's okay. All right. Okay. Yeah, I think in regards to TRL levels, this is something which was, I think, put forward by the European Union, to start with. And I find it actually really useful when we are talking to clients and trying to understand where we are and how we actually go about on this journey. So I think you can see actually, the first three levels, it's the research. I think you can see it's the research, and then it goes on to the development scale, and then the deployment. And the emphasis seems to be like in our world. So if we have sort of initially like experimental work, which is carried out in the laboratories, then you would move it to pilot plant scale, then you would move it to the demonstration scale or production scale. So that journey has to happen. So, and what we found is collaboration is key. And so TRL 1 to 3. So basically what seems to happen is between TRL 1 to 5, we normally get some government funding or some funding from some trade organizations and so on. And the investors, the private sector, they want something which is in the TRL 8 to 9 level. So what happens is between this TRL 5 to 7, we loosely call it as the valley of death, where we've seen actually a lot of projects. Over the last 25 years, I've seen a lot of projects because they don't have enough support. They seem to struggle in this valley of death where, for example, going from TRL 6 to 7 is incredibly difficult. And without proper funding and proper support, it won't be able to move on to the next stage. So I think that's where collaboration then becomes key. So if we involve everyone right from the early stages and get everyone's buy-in into it, then it helps to move from these TRL levels and make progress. There's also, you would have heard actually various different readiness levels. There's manufacturing readiness level, which talks about reliability, maintainability. Again, affordability is the key. there's also industries where there's a regulatory readiness level. Because like say, we are working, we have Airbus as one of our clients. In the airline industry, everything is regulatory. So it needs to have the desired regulatory readiness level, or in the IT industry and so on, there's the system readiness level. And so there's all of this. And again, the key point which I wanted to mention is about navigating this valley of death. We have been working and seeing projects which suffer from that, in between. So I think if we navigate that, then it helps. And the way to work that would be actually to understand this design to deployment journey. So as you would know, so I think some of it I'll be reiterating it. It starts with the market need, as to what the market needs, what the customer wants, what is the gap in the market, and then understand what the capacity, so how much are they willing to buy, what are they willing to pay. So it's trying to understand that need, and also having people on board, or companies and industries on board, which will support that. So then we have the design, the technology, the new idea, which we have in mind. Then can we produce that in quantities, bigger quantities? And what are the technologies for the process we are going to use it? We need to have an understanding of that. And then it goes on to the product optimization stage. Again, in there, so it's okay, we can produce it, but can it be produced in a standard way, so where cost also comes into play? And that's where the techno-economic analysis comes into play. So if to see that whether we can produce it economically, so and whether it will be viable. And then the product to market, whether there's the whole supply chain available. For example, we produce it, we are producing in big numbers, but do we have the supply chain there to sort of buy it, to distribute it, sell it? So the whole design to deployment journey, and having all the relevant partners in there. So this is the commercialization path I was trying to highlight earlier, is that like CMET and companies like so you're in the research side of things, but there'll be industries who will be wanting to to buy the technologies of you. So they need to be sort of collaboratively involved in the earlier stage. There'll be various other supporting organizations. There'll be organizations like us, like others who would actually in the wider supply chain, who, if we can sell the ideas early on, get everyone involved early on, get their buy-in early on, then we can make it possible. And all the resources together can help to get our product out to the market as quickly as possible. These are the key stages in this in the practical commercialization process. This was something which was in one of the R&D management conference in Cambridge, UK. So it shows how the first step is relationship building. So where strategically we involve all the different partners, all the different stakeholders, all the companies who are likely to be involved and who will make it as a success. That then builds up into the technology product development. That which then leads to the business strategy formation, and then we actually have the growth and maintenance strategy. So as you can see, the attention line, it starts with strategy resource to start with. Then we concentrate on the product side of things, the knowledge product side of things, and then we keep growing it and trying to make it a commercial success. Because an idea, a technology, if it remains as just an idea and doesn't find its way forward, which will help the society, which will then it just stays like that. And it is just sad that because then all the efforts, all the ideas which are spent there just stay there. The worst thing is to having to leave these ideas in this valley of death. We need to somehow move this, and TEA will greatly help. I think, so what exactly is techno-economic analysis? It's basically a detailed examination of the plant and market conditions, trying to understand the technology characteristics, what are the advantages, what gap it's trying to fill, what are the details, what are the pinch points, what are the critical control parameters for this. Then based on that, have a feel for the capital cost, which will be one-time expenses, then the operation costs, and then based on the market needs and so on, we can get revenues for how how much are we going to charge? There's also non-economic factors, which could be regulatory, which could be social, which could be political, which could be environmental considerations, and various others, and also plant location, because we are working on projects where it may not necessarily be profitable to invest something here in UK, but the economics work out that if we build something in India, we can get some cost advantages and make it viable. So basically what it does is actually connects the R&D, engineering, and business. And I think it's a tool very powerful. I've used it so many times, and I think I feel that the more and more we use it, the better we can see the advantages, the benefits of it. So how do you actually go about it, in regards to techno-economic analysis? I always try to conceptualize things by using what I call as the SIPOC model, which is, like you have the suppliers, input, process, output, and customers. So if you have the whole, all of that in your mind, then we normally start with the process model. Again, process, I don't mean it's just for chemical, specialty chemicals or pharmaceutical. Process is any process, whether you're producing a quantum dot technology, some nanotechnology or whatever, it will all have a process which will take certain input materials, convert it into certain output materials. But once you build that process model, it then gives you a feel for a certain capacity, for a certain production rate, what sort of sizes you require, what sort of unit operations we require. And that then allows us to build the capital cost model as to how much it's going to cost, what are the installation, what are we looking at, and what sort of footprint we'll need to produce it. Then the operating cost, which is variable, fixed, and general. And then that can lead to all the cash flow analysis, net present value, internal rate of return, payback. Different companies and different investors will have different criteria by which they'll analyze projects. I mean, I've seen in UK, when I first started work, about 25 years ago, if we used to have a payback of something like 8 to 10 years, things would fly. Projects would get approved, and we would see it to completion. But overall, as time passed, the risk appetite of companies, of big corporate companies, have reduced. And nowadays, people are expecting, full payback in 3 years or 2 years. So if it's a very capital intensive project, unless you have actually very, very huge profit margins, we won't be able to recoup that. So I think what that means is, technically, it has to be we have to go back to the drawing board and try to see how best we can produce it at a very cost-effective manner, so that it proceeds to the next stage. This is just actually pointers, and again, sensitivity analysis. We can see once you have this model, we can see what are the process dependencies, and also we can do univariate optimization, where, like for example, if there's conversion, so you can see how the conversion is going to have an effect on the internal rate of return or on the net present value. Monte Carlo analysis, because that that relies on probabilities and random numbers and so on, to see how if market prices suddenly change, then how it's going to come out, or produce tornado diagrams, where you have various different outputs, and to see how things will be changing. So it's got huge amounts. So now what we'll do, I think now we've just looked at the basics of that. I want to just go through a few projects where we have applied it and try to tweak the projects to see how we can help it to move on to the next stage. So like this research project at University of Salford, it's a low TRL project, and again, it's in very, very early stages. So we can't do a full-blown TEA on it. But what we looked at is, basically as a concept, what it is, slugs, snails, they have something in their gut bacteria because they seem so frail and fragile, but actually they've got enzymes in their guts, which is very, very powerful in breaking down lignocellulosic material, which you can see they are just lying in woodlands and so on. So there's some in Africa, there's some slugs. So Salford are doing this work where they're going to get this genome from this enzymes out and then try and develop it further to see how it can break down material. And so at the moment, they're also planning to use it, combining it with nanotechnology so that we can have a basis for that. So we had various discussions and again, using nanotechnology, there are some nanotechnology which uses what they've seen some very good results, but then economically it was going to be very, very expensive. So that now they're trying to explore other different sort of ideas in that. So that's a low TRL. The big project which I want to talk about is this Newton Bhabha Fund, a biotechnology project. There are different work packages within this project, and I'll just spend a bit more time in going through this project and as to what we are trying to do. This project, it's to do with valorization of waste from a sugarcane factory. As we all know, actually, sugarcane industry is quite cyclic in nature. Sugarcane grows for a certain time, and the plant is running only for 6 months of a year. And most of sugarcane factories, whether it's in Maharashtra or elsewhere in India or in Brazil elsewhere, they are struggling. Because sugar, the government has imposed certain cost, sort of restrictions on it, so they can't. So in regards to profitability, unless they make other value-added products like ethanol, high-grade ethanol, and so on, they're all struggling. We are working with a company called Gayatri Sugars, based north of Hyderabad. And what we are trying to do is actually, there are two waste streams. One is sugarcane bagasse, which they just use it to chuck into boilers and produce steam and then power, but the rest all just lies out in the yard. And the other is spent wash waste from all the fermentation and from all the sugar plant and so on. So what we're trying to do is create value streams from these waste streams. So basically, from the bagasse, we are going to make microcrystalline cellulose, but also the residual sugars which are there in the sugarcane bagasse. We got a fermentation process using Candida tropicalis yeast, which will work on the hemicellulose in that bagasse and convert it into xylitol. And xylitol, as we all know, is a natural sweetener, so which is used in chewing gums and also sort of it can be used in chocolate brownies, chocolates, and various other things. And with the spent wash, we are trying to produce volatile fatty acids, which is acidic, propionic, and butyric acid. And also these acids, when we use them to treat the sugarcane bagasse, we can produce VFA activated filters. So which again has got huge sort of applications, potential applications. But the project, so what we've done actually, we have created a draft economic analysis model. So there are these 4 value streams. So this is just a typical example. So so we got xylitol as one value stream. We got microcrystalline cellulose. We got volatile fatty acids and volatile fatty acid activated filter. So all of this we integrated the whole process and created an overall techno-economic analysis model. So based on that, we basically had a PFD, then process instrumentation diagrams, equipment list, and so on. I think, and once we defined that process equipment, we got a feel for the capex as to how much it's going to involve money-wise. Because, as I said, the profit margins are very poor, and so we need to find out how we can optimize the whole system. How we can reduce the capex. Again, in regards to OPEX, which is operational expenditure. Based on the mass and energy balance, we know how much material, services, utilities we are going to require. And using all these details, we put it into the model and we produce this techno-economic assessment and look at the financial indicators. And what we are finding, I mean, there are a lot of challenges on this project. This is how we would be actually doing the overall capex cost, based on the purchase equipment cost. And because we know it's a solid and fluid processing plant. It's got both bagasse, solids and also the fluids. So based on these various Lang factors, we can work out the issues. But what we found is actually based on the techno-economic analysis, is that there are certain elements of the process, like for example, the steam explosion. there's a pre-treatment process for the sugarcane bagasse. Basically, any bagasse or any so woody material has got lignin, hemicellulose, and cellulose. To expose the hemicellulose, which the bugs want to eat and produce xylitol, we need to sort of pre-treat it, using acid and also steam. But what we found is, the experimental work, a lot of experimental work has been done over the last 2 to 3 years. What we are coming out is actually quite capital intensive, and that won't sustain itself. And also using they're using weak sulfuric acid. What that means actually, if you use weak sulfuric acid at high temperature, you're going to need some really exotic material of construction, which again jacks up the price. So we are trying to see how we can use alternate acids. So instead of sulfuric acid, can we use phosphoric acid, for example? Or and to compensate for that, we can have a little bit more residence time. In regards to steam explosion, so how can we use really hot water? Can we use a system which is not capital intensive and requires a lot of maintenance work and that kind of work? So it's helping us to understand where are the pinch points, which are the points where we need to optimize. Also, in regards to downstream processing costs, what we're seeing is actually when we're producing VFAs and so, if you produce very weak solution, then you need to actually you need to concentrate it to sell it as a product, which means you have to use steam. You might need distillation column systems and so on. To evaporate water is very expensive. So we need to find ways how we can use a combination of membrane technology followed with distillation. So I think it's again what I'm trying to get at is actually just mixing and matching different technical solutions to come out with something economically viable. The other thing, actually, even looking at the end product, at the moment, for example, xylitol is currently sold in the market as crystals, because one says crystals as a sign of purity. But if you can sell it as a solution, maybe a 30% solution, and we give the certificate of analysis, which says that this is a pure product, then we should be able to sell it. And the advantage there is actually we won't need a lot of the capex, so a lot of capital equipment to allow to convert this 30% solution into crystals. You can reduce capital costs, operating costs, and be able to sell it. And also in the end, if the end user is takes these crystals and converts into solution, then there's double handling there. So instead, why can't we sell the solution? So that's what we are thinking, so and trying to see how we can push it forward, overcome all the challenges, and make it a success. Now again, the quantum dot glass project, Dr. Animesh has already spoken to you a lot about this. Yeah, this again at the moment we have put it as an application as part of an Innovate UK grant project here, and we are waiting the outcome for it. And again, as part of it, we'll be trying to develop it further in regards to doing a techno-economic analysis and so on. Again, it's got huge range of applications, and we want to move it from it's low to medium TRL, and Dr. Animesh has already done a huge amount of progress in this. So we want to move it further so that it crosses the valley of death, and something which we can then be commercially deployed into the market, so that it's something which will be useful to everyone. Again, so biotechnology projects, I've got some examples here. So where we got this bulk chemical production plant. A traditional chemical plant was literally like a really high temperature, high pressure process. Very safety critical. And if you go to a biotechnology process, we're trying to use Mother Nature and how it behaves to convert something which is really nasty into something which is really useful. And the way, again, it helped, it was serendipitous as to how this came about, but someone spotted some bugs and some chemicals at a effluent treatment plant where they should have seen the raw material there, but instead they were seeing the product. So these enzymes, these microbes were then assessed, and it seems this chemical, it's a red listed chemical. It's so nasty that if we human beings smell it and we are exposed to it for about 90 seconds, we will be dead. Whereas these bugs and enzymes consume it, and produce something which is useful to us. So that I have seen it grow from a like really low TRL all the way to sort of in a commercial deployment. Now there are production factories of these which are there in UK, US, Australia, China, everywhere. And what it helped us when we were trying to do the TEA analysis, safety and every other aspect, it was already sold. What it told us is that we need to optimize on getting the right concentration. If you don't get the right concentration, we won't be able to make it commercially viable and commercially successful. So there was big emphasis placed on certain elements of the process. And when we developed it further, we could make it commercially successful. So TA played a huge role. Again, I think in the interest of time, I'm just going to sort of skip through a few of these. We've done various development projects where there's batch processes which have been converted to continuous. Again, I think we looked at TA to see what are the variables we need to tweak, we need to tune to convert it. Again, in regards various chemical and pharmaceutical projects, like the one on the top right-hand corner, we had to again think out of the box. This was a pharmaceutical company, and if we could somehow build a storage tank farm, I mean, we used to call it as this tank farm in the air, and it was really novel, when it first, and when you look at it, normally most of the tank farms are at ground level. We had to design a system which was actually built above an existing building with all the tank farm and so on. And that made it economically feasible. Otherwise, it wouldn't have a chance to succeed. So again, various where we use TA to produce optimized design to increase capacity by playing with the technical aspects and getting a good economic output from it. So just last couple of minutes, last slide. So in regards to importance, I think I can't emphasize enough, collaboration is key, and it helps to connect the dots. I think it helps to think out of the box and use experiences from different people with different skill sets to help grow this technology and take this technology forward. And TA, what we've seen actually, we can do it both actually, a top-down approach or a bottom-up. In the top-down is based off, what does, if you have a certain cost goal, I think we need to see, so what does a performance cost need to be? Or the bottom-up, so based on certain set of inputs, we just work our way up and try to see, so what numbers, whether it's good or bad. It can be done at all stages, so this TA analysis, the rigor will be different. If there's very little data, you can't do a very detailed analysis. But then again, every little bit helps in taking it to the step forward. It helps to analyze, our focus or attention on certain elements to understand what are the key levers in this, which if we tweak or change will give a big benefit in regards to cost and in regards to economics. And assess the profitability and risk in regards to process and market parameters. And generally, I think it helps to confidence in decisions, avoid surprises. And I also wanted to have this, the circle of, you might have heard about the circle of influence and circle of concern. Technology development is a challenging task, and I've got a lot of time, so we see so many technologies, ideas where we spend 5 years, 10 years of our life. And it takes a lot of energy, a lot of positive thinking, a lot of collaborative efforts, because it's not simple. It's very, very challenging, and many fall by the wayside. I think all we can do is try and expand our circle of influence in regards to technology, in regards to that, to push it and have proactively, spending positive energy to make it a success. So that's my talk on this TA. Hope it was useful to all. Thank you.
Thank you, Nandish. Now the session is open for questions. If somebody is having questions.
Nandish, how are you?
Yeah, I'm fine, sir. I'm fine. Thank you. How are you?
I'm fine. Very good.
Good. It's good to see you and good to meet all.
Regarding this spend wash, this one, I think there are many industries also, again, are looking for this technology. Many people have come. So whether we can we can do something there.
Yes.
Whether we can directly line to them to you or through CIMIT, it's possible.
Yeah, absolutely. Yeah, I think let's talk about it, because I think there's huge amount of applications there, and it is a problem for them as an industry, because whenever you go to a sugar factory, you see sort of huge lagoons of spent wash. There's smell issue and there's all the environmental issues and concerns. If you can get something from it, that should be really good. Animesh, I saw you raise your hands. Sorry, I think you were on mute.
Yeah, Animesh is there. I haven't seen him. Just him.
No, Animesh, you're on mute.
Animesh.
Yeah, thank you.
Dr. Nandish, can I ask you a question?
Yeah, sure, please.
Please, Professor Jha, please go ahead. After that, I'll ask you.
Nandish, you talked about consumption of sulfuric acid, etc. If your molar concentration of sulfuric acid is less than 1, I think you will be better off using glass coated steel, and that has very long longevity. It's one-time investment and it's useful. Or you can use fiber reinforced polymer glass composite. Again, it's one-time investment. I think the simpler answer for that particular thing is you are already producing acid, you said, propionic acid and butyonic acid. So why can't you use concentrated forms of these acid in the digester?
Yeah.
And if you have temperature going above 100, look at this, doing this in a pressurized vessel and see how the degradation of the cellulose is taking place. I sincerely think that the organic acids will give you much better yield, plus you don't have this liability of disposing of the sulfates, because protons are already being absorbed in your acid cellulose destruction. But what do you do with the sulfates? That's the big question. Okay, so I think there are ways and means to look at it in terms of utilizing your own byproduct for generating more product.
Yes. Yeah.
And I have done more work with in mineral processing with organic acids rather than going for inorganic acids, and I found them working very nicely. And people say, oh, they are more expensive. Actually, they're not, because if you look at the capital cost involved with handling inorganic acid, is definitely much more.
Yeah.
Thank you.
Yeah. No, thank you for the suggestion, Animesh. We have looked into sort of various different acids like phosphoric, and again, the issue at the moment what we're having is we've got a soup in regards to volatile fatty acids. It's a low concentration material. We're trying to see sort of how we can make it sort of decent concentrations, because the hemicellulose, we need to expose it and then grab hold of the hemicellulose and get it into some sort of solution, which will then the bugs will eat and chomp away at it. So, but I take your point. So, and again, in regards to material of construction. Yeah, thank you.
Thank you.
Yeah, Dr. Nandish, excellent lecture, because we at CMET, we work like Fraunhofer Institute. We run plants up to TRL level 7. Okay. Wow. So we are well aware of the technology readiness level, but the question which I want to pose you is that, like, what in your opinion, what is the best ROI for a successful technology to get rid of the valley of death?
Yeah, that's a tricky one. I think in regards, because every project, what we've seen actually, every project is different, and the investors or the corporate companies, because if I give you an example, I'll give you a few examples actually. So we have companies like Airbus who are into sort of, so they make the Airbus wings and so on here in North Wales. We also clients like BSF, who are the biggest chemical company. BSF have got sort of, where they are in for the really long term. So they will be okay even with this with a smaller return on investment. But because they're looking at strategy wise, for a really long term. But if I go, so I think this week I'm traveling to a few client sites where they're actually small to medium sized companies where they want actually return of investment much higher. And so it depends on who the end user and the company is. So it's a little bit tricky. And everyone seems to have their own difference of criteria for success or for getting projects approved.
Fine. So one more question. The technology readiness, if you look at the timeline for maturing any technology, it takes almost 7 to 10 years, even in multinational companies.
Yeah.
Okay. So since we being a government, like it takes more time to get it matured. Do you think that it is a good idea to involve a industry partner at the TRL level for itself so that the timeline can be reduced to scale up the technology?
Exactly.
Yes. No, that's a really good question. I think, and you hit it on the head actually. Yeah, the earlier you involve, I think you can shorten the cycle, and also it's less costly. So because to do any changes later on it becomes very difficult. At the moment, like even on our project, some things they've been working on it, and we got involved a little bit later on. And now we're trying to change things, and it's taking a lot of time, a lot of efforts, and it takes and what then happens is if there's other competing technologies coming into the market, then all the hard work which has been done over 7-8 years, 8 to 10 years, that just goes, because there's always the first mover advantage. People who come to the market first, they seem to grab a fair bit of the market share. So I think the earlier people can get involved, the industries and so on. Like even like Animesh mentioned, so when we were talking about the quantum dots as well, Animesh had the idea to involve some of the glass manufacturers earlier on, because then when we are ready, they're also ready. They've already bought into the concept, and therefore it reduces the whole timeline. So it gives it, I personally feel it gives it a much better chance of success, and also people can add values in different ways. I mean, I can go on about it for hours, but because in new ideas, because someone who's so close to the problem, we see certain aspect, but all the other aspects, if you get more people. So I fully agree with you, Ratish. Thank you.
I give you one quick example. I work with the medics in doctors and on medical devices. So first thing I do, go and stay with them in the operating theater. What is the problem? And see their difficulties, make notes, come out, and then discuss how we go about solving it. And then we plan low TRL research so that it accelerates to TRL 4-5 as it gets on the brink of the valley of death. Okay. And during the last phase of this journey, we involve industry. Okay, so what Nandi said, you are looking at from completely different perspective. You're not only looking at an expert, but also somebody who has got an understanding of the market and what other things are coming out. So in your case, Ratishji, I would say one thing. So for example, if you're going for, say, electronic waste, first of all, think about how not to increase the cost of processing the waste and what are the most important things you can get cheaply out, because there's lots of things in there. Okay, that's a mine in itself. So if you take the easiest thing out and you can sell it, then your return on investment cost part is better. Okay, so if you say, for example, if you can take the copper out and sell it or reuse it, that's an already value. Whereas gold, silver, and platinum and other precious metals and difficult metals would come out later on. And I think this is very, very important. In a complex project, you have to look at multiple um, products. And if you are developing technology, don't make it linear, because linear path is disastrous, in my opinion. And then this can also tell you, if you have a if you have something which is like a hand and it spreads out, then you can make lots of very good things from one platform. So this is the platform and this is the application. That's what you have to really think about it.
Thank you, Professor Jha and Dr. Nandish. Over to Chairman.
Thank you.
Dr. Nandish, hello.
Hello.
Can you hear me?
Hello. Yeah, I can hear.
Yeah,
I think there are no questions.
Dr. Rick wants to ask something.
Yeah, just one point. Sorry, the last minute I'm joining. The thing is, thank you for so much for enlightening us on a very important topic, which is of more relevance for CMET, because we are also trying our level best to see how best we can see. Some of the times what happens is we are scientists, we bring technology up to lab level. Sometimes, as Ratish said, we bring up to pilot level, even up to TRL 7. Okay, so we have projects ranging from lower TRL to the highest TRL feasible from our side. Though we have developed these technologies, we don't know the other side, like how best we will be able to productionize it, how successful it will be in really taking it to production stage. So these are all something that we may not know the entire ball game of this. So will you be able to assess that, okay, these are all the technologies where there is, what are the market potentials that we have, and which are all the likely to, where there is a definite promise for us to take it to the higher level, so that it is of sure shot winner in the shorter run. So in those kind of aspects, will you or your company will be able to put your mind and tell us, okay, out of the so many technologies that are available at CMET, these are all the possibilities. Because there are technologies, possibilities where we have it at the as a spin-off technologies, where we are quite sure that it is a low cost and a cheap product and it's easy to market also. But we don't know how to take it up to the next level. So these kind of gap, whether you will be able to, your institution will be able to help us to fill up. Would you like to comment?
Yeah, sure. I think we will definitely try to sort of help and address those. We do have sort of occasion like here in UK. I mean, a lot of experience of ours has been in UK Europe market, and we have sort of many times we have sort of to our office we have high net worth individuals who come in and they've got all these thoughts and ideas of give something back to society. So we will look at it from first principles, but also from the market side of things, and see sort of where it can gain traction. And many times we had to sadly say that this is not something. It's not a nice thing to say or a thing but that's the fact of life. If the numbers don't add up or don't stack up, then you might as well actually try and tweak it and try to see something on that. So a short answer to that question, yes, I think we've done that before for other clients, and we can do. I mean, there may be certain areas where we don't have enough domain knowledge, so to say, but there will be certain areas where, because we have a huge pool of clients, sort of here working here, so we can understand, based on talking to some other people and so on, get an independent assessment and try to put an independent view on things.
Thank you so much.
Thank you, Nandish, for giving a detailed lecture on economic analysis and how it can be applied to assess the projects. So on behalf of organizing committee of MEMP 2021, I'm thankful to you.
Thank you for inviting me.
Thank you, Nandish.
Thank you. All the best. I'll stop sharing now.
Thank you. Bye for now.
So next lecture is Professor Maya Bar Sadan, Associate Professor, Department of Chemistry, Ben Gurion University, Israel. On a place where everyone matters, interfaces in functional nanostructures. Dr. Yogesh is giving the brief introduction of Maya.
Good afternoon, all of you. I, Dr. Yogesh Sethi, welcome you all for the third lecture at this session of MEMP 2021. Let me introduce the speaker, Professor Maya Bar Sadan. Professor Maya Bar Sadan is an associate professor in the chemistry department of Ben Gurion University in Israel. She did her PhD in Weizmann Institute, focusing on inorganic fullerene-like structure, and graduated in 2007. Thereafter, she joined the group of Professor Kun Urban at the Institute of Solid State Research Center, Jülich, Germany. In 2011, she joined the Ben Gurion University. She was awarded Minerva Fellowship and the Sara Lee Postdoctoral Award funded by the Clore Foundation and year donor Sussman. The Weizmann Institute of Science Program for Advancing Women in Science and the Green Prize of the Wolf Foundation for Excellence in Research in 2016. In addition, she is interested in teaching and was awarded few prizes for excellence in teaching, and she is now the head of teaching committee of Chemistry Department of Ben Gurion University, dealing with undergraduate teaching program. With this introduction, I welcome Professor Maya to deliver the talk entitled "A Place Where Everyone Matters: Interface in Functional Nanostructure." Professor Maya, please.
So first, thank you for the invitation. India is one of my most favorite places in the world. I'm just a little bit sad I couldn't visit of late. The first, I want to introduce a little bit where I come from. So I come from Israel, and you have the two big cities, Tel Aviv and Jerusalem, where you can see them here. And Beersheba, where my university is here at the south. It's the fourth biggest city in Israel, which is a small town in India. But we have a big group that focuses on energy-related applications. And we have also a thriving Indian community of postdocs, and we have fun. So what do I want to talk about? So I was just smiling in the previous talk because, of course, just at the end, we started discussing the fact that you need to take the very basic science and connect it with some kind of an applicable thought. And my science is very basic. It's kind of at the other end. So my thought is like this. We know the nanoscale structure. And usually we also know the functionality. We can imagine or assume some kind of an atomic scale structure, but we don't know the real atomic structure. And this is where chemistry actually occurs, right? So if we talk about molecular chemistry, if we talk about proteins, if we talk about molecules, then of course we want to discuss which bonds we break and which bonds we produce. And when we talk about small solid nanostructures, we get into the problem that we don't really know. We don't know what is the real atomic structure, and single atoms, they matter. So if you say this to a chemist, then it's completely clear. So if you have two molecules, and I just tell you, I have two very similar molecules, and they obviously do the same, because the only thing that is different is this one single atom, then as a chemist, you will laugh, because of course, alcohols and carboxylic acids, they are completely different, right? This is the difference between having vodka or vinegar. And what makes us all laugh is something that is a little bit forgotten when we are talking about small nanostructures, where you usually see that people will discuss plus minus 10% of size, and they call it a narrow size distribution. So one atom matters, and we need to know where these atoms are. And if we do know that, we can plan and design better structures. So my favorite tool is doing this by electron microscopy. This is what I basically focus on. And you can see here one image of cadmium selenide in cadmium sulfide quantum dot. And what you can see is that at this way of looking, each of these dots is actually a column of atoms. And what we can see here is directly the structure. I can enlarge it so you can see it here. This is a raw image, by the way. And what you can see here is the chemical bond. So this is 1.4 angstrom, mass to mass, center of mass to center of mass. And this is the chemical bond. And now we can restart asking the same questions that we did before and try to combine this world of molecular chemistry with the world of nanostructures and nanomaterials, which is 2 or 3 orders of magnitude larger. So I did a lot of work on inorganic fullerenes. Of course, these are layered materials where you have the molybdenum atom layer inside here, this plane, and it's sandwiched between 2 layers of sulfur. One can make nanotubes from them, as you can see here, and also fullerenes. And these fullerenes are different than C60, for example. These are much larger structures and it's much harder to bend them. So what we get here is this special nano-octahedron shape. And it has a completely different aspects and signs than you would with carbon structures. One of them is that in order to seam these facets, you need to have all kinds of defects that involve both molybdenum and sulfur. And these defects are the active sites. Usually they are coordinated in such a way that not only they are more active, also their electronic properties are different. And we kind of calculated and worked a lot on analyzing these structures. What's nice about them is that you can actually look at them in electron microscopy and you can get information that you wouldn't get in other methods. So just to put us all on the same page, you have 3 different phases of molybdenum disulfide where the molybdenum atom is coordinated with 6 sulfurs. Now these 3 different configurations differ in their electronic properties. So the 1T is conducting, and these 2, the 2H and the 3R, they are semiconducting. And if you look from the side, you can look here at the atomic scale model, the ball and stick, and you can also see here, just for the benefit of leading the eye, I put here some black lines. So you see that if you look from the side, in a side view, then you can directly see what is conducting and what is semiconducting. So now if you look at one of these fullerenes from the side, and you have here an atomic scale image, and I just overlaid in PowerPoint just these yellow and red dots on top of this structure, and then I put it at the side, I can see that I actually have a very complex junction, electronic junction. I have a semiconducting metal semiconducting junction, which is radial, meaning that I cannot work on this in the regular ways that we can actually measure these junctions, right? Usually you would try to put something like 4 probes and calculate and measure the IV curves. But here, because of these radial junctions, it's much more difficult. And actually with one image, you can immediately understand what is going on in terms of the electronics inside these kind of materials. So this is why I like these structures. So at that point, I kind of diverged and I went into doing catalysis and electrocatalysis with these structures. I was trying to make these nano-octahedral structures in some kind of arc discharge or by laser deposition techniques, but these were too complicated. So I was very happy that a few years ago, one of my students managed to actually make them with a template. You have a template of copper sulfide inside, an nano-octahedron, and on top of that, you have 1 layer of molybdenum disulfide. And he managed to do this in a 1-pot synthesis, which was great. So now we had all these structures, and you can see that you have only 1 layer of molybdenum disulfide around them. So this is one of my favorite projects where I can show you that within 1 image, I'll be able to explain first, why are these good electrocatalysts for the hydrogen evolution reaction? I will be able to tell you something about their electronic properties and the junctions, and I will also be able to predict or to evaluate what was the growth mechanism just from this 1 image. So this is 1 image in atomic resolution. You see here the nano-octahedron, which is copper 2 - X sulfide. You know that the copper sulfide is a very rich system with a lot of different stoichiometries, and the copper is very mobile inside this lattice of sulfurs. You also get the molybdenum disulfide layer, and if you just enlarge it a little bit, you can identify directly this copper sulfide phase, which, by the way, is a metastable phase, a kinetic product. And on top of that, you can see the N-type and the metallic, the 1T phase here in number 3 and number 2. So if you actually look at this structure, you can immediately see that you have here a P-type semiconductor, the copper sulfide. You have the N-type layer, which is here in number 2, and you have a metallic-like structure here. So these are actually very good electrocatalysts for the hydrogen evolution in acidic conditions, and let's discuss a little bit why. So the first thing that we do, we always do that, we try to model this with some friends that do DFT calculations. And we see that the only way to stabilize such kind of structure is by assuming that you have some kind of a stoichiometric phase here. So the copper atoms or ions actually lead to the interface. You see that this is not completely flat. And what they do here in the interface is that they have some very complex interface with the molybdenum disulfide that activates the basal plane. Okay, and we'll show this. So just to make all of us understand what I'm looking at this simple reaction. 2 protons and 2 electrons produce a hydrogen molecule. And in order to get a good electrocatalyst, we need first a good catalytic sites. We need the conductivity of the solid phase. Otherwise, we put electrons into this electrode, but they don't reach the solution and the solid interface. And we need to have this durability and stability that is important for everything that we make. And we measure these diagrams. So we have here the current versus the voltage. And of course, we need to apply some voltage in order to drive the reaction. Platinum is the best. It produces the least overpotential. And we have here the 3 different structures that we made. We have the hybrid, the copper sulfide and the molybdenum disulfide. We have just molybdenum disulfide that we synthesized separately and copper sulfide. And you see that the smallest overpotential, meaning the smallest energy that we need to invest in order to make the hydrogen evolution start, is of the hybrid. We look at the Tafel slope that tells us something about the mechanism, and we see that the Tafel slope is also the smallest for the hybrid. So obviously these are better catalysts. The question is, of course, why? Why are these better catalysts? And what we did is that we did the DFT calculation and we calculated the delta GH. This is the free energy of the binding of the intermediates of the hydrogen. And we want this to be as close to 0 as we can. And if we look at this, we see a lot of different sites here, but the site with the smallest delta GH is actually the sulfur, which is on the basal plane. And this is something important because so far the basal plane of these structures was known to be, we would say, almost inert. It does a little bit of catalysis, but relatively little. And people were making a lot of effort on producing morphologies where you can get more edges because the edges were the active site. So this work is nice because it shows that you can activate the basal plane, and by that you can produce a better catalyst. But why do I say that I also know the growth mechanism? So if we look here at the DFT calculations, we see that this is some maps of electron density. We see here the molybdenum atoms here in red. We see the copper sulfide in blue and yellow. And we see here the 2 sulfur atoms that are connected to the molybdenum. And what we see is that when we have the 2H molybdenum disulfide, we don't have a lot of electron density here on the outermost sulfur, but we have relatively a lot of that here. And this means that the very outermost layer of these structures is actually charged by a negative charge. Now, what we do during the synthesis is that we have these ions, molybdenum S4-2, And we produce molybdenum disulfide by extracting the very active sulfur 2-2. But basically, because of the electrostatic repulsion between the first layer of the molybdenum disulfide and the subsequent ions that want to just lie on top of that, we can arrest the growth and get it only with one layer of molybdenum disulfide, which produces this structure as more active than maybe ones that have a lot of layers of molybdenum disulfide. So I like it because with this one, seeing is believing image, we can actually understand all these important fundamentals and principles on how to produce better structures. So we decided to expand it, and we said, well, we didn't actually use the properties of copper sulfide. We wanted to have another material. We wanted to have, in this case, gold, because gold is, of course, quite inert, and it's also, it can serve as a reservoir of electrons, being a metal, to inject the electrons into the surface of molybdenum disulfide. And what we did, we found a way to cover these structures. We produced once a spherical nanostructure. We used rods, and we also used some irregular structures with a lot of spikes. We call it nanostars. And we checked the catalytic properties that we got. So this is an image of the particles. You can see the gold inside. These are the rods. And you can see here the single layers of molybdenum disulfide. And these are the stars where you can see that you have a few layers at the edge. This is without the molybdenum disulfide, and this is with that. And when we look at the catalytic performance, then of course what we see, if we look, we have here the overpotential in violet. So we want the smallest, these are the nanostars, and we want also the smallest Tafel slope, and we can see that these two goes to these nanostars. And we have the nanostar, we have the rod, we have the sphere, we have the bare rod, we only have here molybdenum disulfide nanoflowers, and we have just the opposite, nanoflowers with these little decorated particles. And what we basically found out that the important part here is not the gold itself. The gold itself just serves as a reservoir. It produces some kind of a surface, a template that can get indeed electrons from a big reservoir. So the biggest structure we have, the more electrons we have, and the layer of molybdenum disulfide is kind of it has more charge that is being injected to that, and this is why these are better. The molybdenum disulfide is more conductive, and these are better structures. Another thing that happens, of course, is the strain. The strain becomes more important as we discuss this. So if we started before with copper sulfide, let me just go slightly back. So my structures here had an overpotential of something like 330, and this is, of course, not the best. When you go to gold, you can already get this to 164 of millivolts. So obviously we improved quite a bit, but still this is not enough, and gold is expensive. So we said, why should we use gold? If we just need a metal, we can use every other kind of metal that will inject electrons into the layer. And what we did is that we did the same with silver and with copper. And with copper, what we see is that the cores that we get sulfidized to copper sulfide a little bit. Some of them don't, and some of them do. And the main thing that we get is the strain and the defective layers. So we can see here that we have edges, we have junctions of the molybdenum disulfide layers. And if we have a lot of layers, the injection of electrons from the core is less important. But still, we could see that if you change the ratio between molybdenum disulfide that you use and copper that you have different coverings. You see here that from very small, we get to a lot of fluffy molybdenum disulfide material around this, and we find the optimal point where the layer of molybdenum disulfide has strain, it has maybe injection of electrons and not too much of fluffy material, so that you get the best activity. And you see here that we can get these values of 220 with a much cheaper copper. So this optimal spot, if we compare all of them, we can have some measure of the strain. We found out that the best one has the best strain, the most strain. We can understand by the Raman what kind of, that we have a single layer or 2 layers, and we see that basically we would like to get only 1 layer, which will produce the best effect. And this delicate interplay between the strain and the electrons can be tuned to produce the best structures. On top of that, we don't need to do only HER. We can also do oxygen evolution. And we did that, and we see that these are actually very good particles, catalysts also for that, with quite nice results. So once you know how to make these structures and you know something about the production of them, the synthesis, what is the intimate relationship between the core and the shell, you can start producing and using them also for other applications. But as I said at the beginning, sometimes this is only one approach to activate the basal plane. Sometimes you want to make structures that, that produce many edges. And for this, we developed this synthesis of what we call nanoflowers. Some of my colleagues that they joke about me and they call these nano cabbages. Okay, I will allow this, but the point is that they are fluffy and cute. You can see here, if we look at different one structure from different orientations, we can see that there are a lot of voids, a lot of edges, and this is a very versatile material. Because once you understand the growth mechanism, you can tune the composition and then you can tune the catalytic properties. So how do we do that? There are 2 basic ways to grow nanostructures. One of them is to do radial growth. Like you see here, this is like a tree grows, right? So you have the stem or the core or the kernel, and from that, the materials just grow. And of course, in this kind of growth, the core is more solid. And as you go outside, it crystallizes. The other way is some kind of a mechanism where you first have an assembly of material which can be amorphous. And then as it comes together, it also crystallizes. And because, of course, the crystal is more dense than the fluffy material, you're left with voids. And when we did it the first time, we took aliquots from the solution, and you can see this fluffy material that crystallizes with time. So this is after 1 minute, this is after 3 minutes, this is after 5 minutes and 10 minutes, where you see the fully developed nanoflower. And this platform is very nice. We do this in colloidal chemistry. We do this with oleolamine. And you can get these materials, and it's extremely important. It's important because it means that whatever you put in this reservoir is going to be left for the mature particle, and I'll talk about this in a second. So first, how did we prove that? We did tomography. So we took the aliquots of the solution. We took the different images from different angles, and then on the computer we restructured the 3D volume. We cut it inside, just like you cut an onion. And what we could see that in no part you can see in the middle, okay, this is the image and this is the reconstructed volume, you don't see a kernel. So we know that what we have is a reservoir of amorphous material that with time, not too much, 10 minutes, it crystallizes. And if you now want to dope this material, this is a kinetic product, you can add into the solution whatever kind of material that you want, and you'll be able to dope it, which is much easier than doing solid state reactions that are much more difficult to produce. So we do this in relatively low temperature, sometimes 200 degrees, and we can dope with whatever you want almost. One good example here is ruthenium. So we started with doping with ruthenium, and what we wanted to do is we wanted to substitute molybdenum for ruthenium, and you can see we have here the SEM and the TM images, and this is the pristine molybdenum diselenide, and this is ruthenium doped, and in this lower level you have substitution of 10% of molybdenum with ruthenium, which is a lot, and they still keep their structure, which is good, because if you want to compare the catalytic activity, you want the morphology to be relatively similar, because you want to take out issues of surface area, of the amount of edges that you have, whatever you put there. So we saw that you have also a difference in the optical properties. We see that you have a change in the excitons of the molybdenum diselenide, and the band gap is slightly higher when you dope with ruthenium. And this is because you add a lot of electrons. It's a donor of electrons, the ruthenium in this system. And what you basically get is that you also get improved conductivity. And this improved conductivity, the ruthenium itself doesn't do anything unlike what you would expect, because ruthenium by itself is a good catalyst. So ruthenium itself doesn't do much in terms of the catalytic performance. It serves as a donor, and it makes the molybdenum diselenide a better conducting material. And this is why we can get the overpotential from something like 225 millivolts go to 143. So this is already nice, and we say that better conductivity is better catalytic properties. But for that, well, ruthenium is quite expensive, right? So we tried also with manganese, and with manganese you get almost the same performance with just a few percent. And of course, manganese is also magnetic, and therefore there's a lot to do with that. And if you look, you see that there is no difference. You put in the manganese, it looks exactly the same, the pristine and the two doped materials, and you get almost the same activity that you would get with the same amount of platinum in this system. So this is quite nice. So if we now go a little bit faster, I want to show a few projects where we use this knowledge in order to produce better catalysts. So if we look at manganese, we see that we have a different mechanism than ruthenium. In manganese itself, although again, it is not the active site itself, it stabilizes inside the material vacancies of selenium. And these are the active sites. So manganese itself is only, when you do the DFT, it is only good for this reaction that I show here, where selenium and protons in the low overpotentials, they already produce this hydrogen 2 selenium gas. This is the desalinization reaction, the DSR. And of course, when the selenium is gone, you are left with these vacancies. So you in situ produce these deficiencies at the very beginning, and then what you get is that you get a very good catalyst. So that's one mechanism. We can also dope with tungsten. Okay, so we now change molybdenum for tungsten, and this system is interesting because what you see is that you have some kind of nonlinear behavior, and there is some specific combination that produces the best catalytic performance in acid and in alkaline, and this is because of the difference in the properties of the molybdenum and the tungsten in terms of attracting or pushing the electrons away from them. So this is one example. Of course, you can also change by the same synthesis procedure. You can also change the chalcogen from sulfur to selenium or vice versa. And again, here what you see is that you can optimize the dissociation energy of the water, which is one of the important steps in doing DHER in alkaline conditions. So you need actually to go to each of these different projects. You need to look at them. You need to do the DFT, but you can produce a whole lot of zoo of materials that look the same. And the only thing that is different is the composition. So this is nice. Another example, and this is example that was prepared by my postdoc, Dr. Sunil Kadam, who's in the crowd today, is when you try to dope, but it's not working that nicely. So Sunil was doing this work where he was trying to dope tungsten diselenide. Tungsten diselenide is interesting. Not a lot has been done on that, but optically it's very interesting. It's a p-type semiconductor, unlike the other materials that I showed now. And he saw that nickel is the most successful in terms of changing the properties of the catalytic properties of tungsten diselenide. But when we actually looked at that, we saw that there is little evidence that we dope. We had calculations done, and what we see is that in this system, the nickel selenide and only certain small patches of nickel selenide are actually responsible for this enhanced catalytic activity. So we have both nickel doped tungsten diselenide. It exists, although in very low percentages, but there is also this hybrid of nickel selenide and tungsten diselenide that you can see here. And only one layer can produce these very, very active sites that change the whole properties of this material. So that was also a nice structure. We tried the same with cobalt. And now we all also understood that we can change the morphology. For example, we can have the pristine molybdenum diselenide. We can dope it homogeneously, or we can add the dopant in later stages of the synthesis where the material already started to crystallize, and we can produce an outer layer, you see here in gray, that actually puts most of the dopants at the edges. And it seems that when you put cobalt at the edges relative to putting it inside the material, you get two different activities completely. So in acid, you see here in green and in blue that, sorry, mainly in green, that the edge doped is kind of impressive. But in alkaline, the homogeneously doped material becomes better. So it depends exactly on where you put your cobalt atoms, and then you can predict their activity, and you can also produce material that is enriched with these active sites that you want to produce. We even worked on other materials that I think they are very nice, and this is tin sulfide and tin disulfide. And we can also produce them. They are not exactly the same nanoflowers as you saw before, because what happens with the molybdenum doping is that you change the tin disulfide to tin sulfide. This is because the dopant atoms, they sometimes also intercalate, and tin sulfide and tin disulfide, they have a very interesting and complex, they are two-layered materials that can produce similar structures. So what we saw is that if you put enough molybdenum inside and you change the phase, you also get, on top of being a better electrocatalyst, also photocatalyst properties, which is nice. Okay, so let me see how much time I have. Yes, I still have enough time to go through this project. If we switch for a second from these layered materials, I want to show again what electron microscopy can do for you when you want to make complex structures and you want to test them for their catalytic properties. So these are seeded rods of cadmium sulfide on top of or around cadmium selenide. This is a very known system. A lot of people worked on that, and they mainly worked on the gold nanoparticle at the end, which is a co-catalyst. So what we did is that we produced a few systems, one that has gold at the end, the other one that has palladium at the end. We produced a core shell, and we also produced core of gold and an alloy shell. And there is a reason to that. The reason to that is that if you look at this, we know that gold is a better trap for electrons that are produced photocatalytically at the interface here. But palladium is a better catalyst. So we first wanted to check each of them separately, but we also wanted to have this core shell structure where we wanted to see if this kind of structure will allow to get the benefit of both metals. And we also tried to do the opposite, but since gold is more noble, it always produces a core, and the gold and the palladium produce here a shell. So the first thing that we saw, and this is something that is overlooked by a lot of people. So we started by making these rods. Well, you can see them here. And then we put on them the gold tip, and on top of this, the palladium shell. And of course, we could produce the core shell structures here, but look what happens to the rod. So the semiconducting rod that is, of course, not always, it's not atomically flat. It's roughly okay here. But as you make more and more modifications, you see these grooves here. And this is because all kinds of processes actually oxidize this cadmium sulfide. So if we look at properties, what we usually do, I also did it before this this project. You measure what you get. You do this in low resolution. You say it's around 5 nanometer, but these grooves, as you will see later, are extremely detrimental to the catalytic properties or the photocatalytic properties of these materials. So when you use it in slurry and you measure the quantum efficiency to produce hydrogen, what you see is something like this. Okay, so we have here the quantum efficiency and we have the time. This is a very long experiment where every time we measure the quantum efficiency by taking aliquots and measuring or injecting aliquots of the vapor to the GC and measuring and calculating the quantum efficiency from the production of the hydrogen. So we decided to compare everything to gold because gold is very stable and also a lot of people worked on that. And we see that palladium is slightly better in general and the gold inside palladium is 2 times better and the gold in the alloy is 8 times better. But this only happens until a certain point in time. And then the activity drops down and gets kind of much lower than we expected. And what we wanted to see is what happens. So we compared here one particle before the synthesis and after the synthesis. And let me show you what we have. So this is a Hadaf-STEM image. This is just an image. And these are elemental maps. We have here the gold as the core and the palladium as the shell. And we see here a map of the gold inside and palladium outside. So this is the starting material. But after you let it work for something like 40 hours, 50 hours, and you take the materials to the microscope, you don't see these semiconducting gold anymore. It is much shorter. And what you also see is that while the gold is still in the middle and kind of stable, then the palladium seems like it leaked or it melted. It doesn't melt, right? Everything is solid. But what happens is that the palladium is much more mobile. It goes on the semiconducting wire and it enhances the oxidation. It is known to produce all kinds of species that are oxidizing. So if you look at this, you see that we end up with material that doesn't have the optical component in order to produce the electrons. And this is why we get this structure roughly is still there, yes. The catalytic properties, of course, they are degraded. And why the gold in alloy is better than the gold in palladium? Because the alloy is very interesting. Gold and palladium, these are materials that actually like this alloying very much. So what they do is that the gold serves to stick the palladium atoms and actually produces something of a glue in order to make this whole process a little bit, I would say, hindered or decreased in general. So we see that this very small modification can change the activity by a lot. And then we were interested exactly in an opposite system. So in this system, I still have the palladium, but I have silver. Now, silver is a very bad catalyst for hydrogen because it doesn't bind protons. And you would expect that if I have a tip of palladium alone and of silver alone, then silver will be completely non-active and palladium will be active. And what happens when we start playing this core shell play with this system, right? So you would assume that if silver is on the outside, and I do this in a 2-step process. So I know that I started with palladium and I put the silver on top. I will expect that no binding of hydrogen will happen and we are not going to get any hydrogen production and vice versa. So let's see what we see. We have here the quantum efficiency and we have here the size because we now know that the tip size is very important. We can see in palladium here is in green, that you have an optimal tip size that takes into account the transfer of electrons into the co-catalyst, into the metal from the semiconductor. And it also says something about the curvature, the size of this thing. So there is a very strong size dependency. And we see that we have here the best at a slightly small catalyst of 2 nanometers. And we have here just in pink, we have the silver. and the silver produces no noticeable production of hydrogen. But when you take the same size of tip, inside you have palladium and outside you have the silver, it still produces some hydrogen. So it means that we have palladium migrating to the surface. If you do this the other way around, we have now here for the same size of 3 nanometers, this is the palladium, the pure palladium. And what we have here inside, we have now the silver, and outside we have palladium. And we see that we have a lot of production of hydrogen, but it's not as good as pure palladium. So obviously, silver goes to the surface. And some of the sites are just being kind of deleted, right? And what we have in gray is that we have a system that we produce to compare, and is a complete, I would say, alloy, but it's actually just putting everything together from the beginning and letting them do what they want. And when we started looking at this system, we understood that although we have these 2 different stages of synthesis, these nanoalloys, and we treat them as solids, actually reconstruct by themselves. And when we started reading about this, you have these DFT calculations that say that the outer shell of these nanoalloy depends on the surrounding. So if you talk about, they did it, of course, in solid gas. So you can have a solid with vacuum, solid with hydrogen, atmosphere, solid with oxygen, but we have a solution. And they say that depending on the conditions, you always get both of them out because of the stabilization of the phases. So you can see here in this small cartoon that it doesn't matter how you start. You can start with the palladium inside. You can start with the silver inside. Eventually, you have some mixed silver palladium on the surface. And we could also show this when we did the microscopy. You see here the rods, and you see here the tips. We made here a large tip. And what you can see here is that in pink and in green, you see the palladium and the silver. And if you compare what we did with 2-stage synthesis and 1-stage synthesis, you hardly see the difference. For sure, you don't see these nice core shell structures that I showed for palladium and gold before. So I call it a man plan. The man plans and God laughs. You know, these things happen. So I want to finish just really in 2 minutes. I'll just say that this is not all that we do. We also work on different phases of phosphides. It's not just sulfides. We are not racist against phosphides, and we even like nitrides. And we work on all of these and do catalysis and photocatalysis with them. So, of course, I want to thank all the people. First, my hardworking students, all of them. Specifically now Sunil, who's in the crowd. I showed two papers of his, and there are a lot more in the kind of in the writing and in the making. And of course, the other people, Andre and Ashwin, are doing the DFT calculations. Lilach and Ronen help with the catalysis and photocatalysis. Lothar is doing the microscopy, and Professor Eshiftene was my PhD advisor, and I still enjoy working on some projects with him because we are good friends. And I thank you for your attention.
Thank you, Professor Maya, for a very nice and informative lecture related to interface in functional nanostructure. Now, session is open for quick 1 or 2 questions.
I have a question.
Mr. Motekar?
Yogesh?
Hello, madam.
Animesh has a question.
Okay.
Yeah. Extremely nice talk. Thank you, Maya. I would like to get in touch with you via email. I have one question which takes me back to my PhD, which was at Imperial College on copper sulfide. The picture you showed, you have a non-stoichiometric copper sulfide, cuprous sulfide. So you have sulfur access. The moment you put molybdenum disulfide, which is very stoichiometric, okay? Because the Gibbs energy difference between molybdenum trisulfide MO2S3 and MOS2 is quite significant. So what I see happening there, because you have sulfur access in cuprous sulfide, that sulfur is donated to the molybdenum layer to make 1T. So this is absolutely fascinating because that's the Gibbs minimization part. Okay, because you cannot convert completely Cu2 minus the non-stoichiometric into Cu2s, which is stoichiometric. That requires much more energy. So that, I think, if I'm right in thinking, that's exactly is happening, and that's why the semiconductor MOS2 becomes 1T MOS2. Is that right?
So what we saw is that you have a lot of things going on. Even if you take copper sulfide, which is stoichiometric, and you want to deposit gold on that, you also get leaching of the copper out, which is something that I could not understand so easily. And we tried doing this in different ways. One time is a one time. Yes, exactly.
I understand why you're saying this, because the Gibbs energy of copper going into gold is lower and helps copper sulfide to become non-stoichiometric. I know the Gibbs energy differences between the alloys because we used to use gold as a reservoir in equilibrium experiments when we used to do thermodynamic measurements. So gold dissolves copper quite a lot, as we know. So you put tiniest amount of gold on a nanoscale, it will suck up a lot of copper. I don't want to take too much time, but the last part where you start showing palladium disappearing, I think what we are seeing there is a classic example. Again, it takes me to 1985 when I was doing my postdoctoral research at Purdue University in School of Chemical and Materials Engineering. I was this brilliant chemical engineering prof who had a physics background. And what he used to do is calculation and then do measurements on few clusters of atoms, going up to maybe 100 clusters, a pure atom, and then measuring the melting point of it. And what he showed, that the melting point of clusters of atoms fall because of the Van 't Hoff relationship by a fraction of a degree. Okay.
I teach it in my classes. I actually teach exactly this in my thermodynamic class.
Okay,
exactly.
Okay, right. So what that has to do with your presentation here? What we are seeing when you make pure alloy on a nanoscale and you put them in a chemically aggressive environment, you are seeing spinodal decomposition of that alloy under that condition, and that's why the phase actually disappears. The palladium disappears, as you saw, showed that it's been swallowed by this phase decomposition process, and that's where your hydrogenation process suffers.
Yeah, and I think one of the main problems as a community is that we tend, also myself, yes, to characterize our structures very well before we do the catalytic measurements. And now I see also with reviewers that they put a lot more emphasis on the before and after in order to understand what actually happens there. This produces a lot of valuable information.
But
yes, absolutely.
I would conclude one thing by saying, without taking any more time for other speakers, other participants to ask questions, what is characteristically missing now in the literature is the link between DFT and traditional thermodynamic measurements. And if we can link that, I think that's a huge knowledge pool, which is missing from the nano and quantum dot structure, in my understanding. Thank you.
Absolutely. Absolutely. And if you want to mail me, I'll be very happy. There is my mail there. And if not, you can just Google my name. There is no problem.
Yeah, these days, nobody can hide, so I know. Right. Thank you.
Thank you so much.
Thank you.
I think no any question. Thank you, Professor Maya.
Professor Maya, whether I have one question here in growth of MOSC and MO2 molybdenum selenide and molybdenum sulfide. See, growth in molybdenum sulfide is different and molybdenum selenide is different. I think I have seen your both the structure, and there we are also depositing nickel, correct? Nickel and cobalt. So in nickel we have deposited only 1%. Whether any other percentage difference is there in the catalytic purpose?
So I'm not sure I really got the question. You think that you ask if the percent is different?
Yeah. Percent in nickel is, I think, only 1% we have done the catalytic properties of hydrogen evolution.
So it's really hard to say. We worked a lot on trying to understand how much is actually substituting and how much is deposited at the edges, because it is you can do ICP measurements and you know something very general, right? And in some cases, like with the nickel, I think that even this 1%, if it goes into this very layer of nickel selenide, it can be very effective. Well, if you want to change electronic properties, you usually need much more, like you need maybe 4 or 5%. And then it becomes a little bit more difficult. So I think the most important thing lies in the characterization. We also had our own issues with this, but then the question is, where is this 1%? Then one can answer these questions a little bit more. And I can also say that our friends that do the DFT calculations, they continuously come with all kinds of very similar structures that for an experimentalist, it's very difficult to know if one exists or the other and what is the fraction of each. So unless you have something which is very specific, like it happened with the nickel selenide, that only some very specific patches were highly active and others were not active almost at all, then I can be sure that at least something specific I have there. But otherwise, I think that it's indeed very difficult what you mentioned. Yeah.
Sometimes what happens? No. Sometimes what happens? We get different kind of growth of nickel itself in the while growing the MOS2 or molybdenum selenide. And like nickel generally gives some nanowire like growth, and that was helping us sometimes. So a very small percent of the nickel was giving very good hydrogen evolution. And
exactly, if it goes to the right places and it makes the right sites, then it's amazing. This is why I said it depends where this 1% go to.
Okay.
Yes.
Okay.
Yes, absolutely. Absolutely. So thank you again for the invitation. It was a delight.
Thank you. Thanks for giving your valuable time to us.
Thank you, Professor Maya. Now, next lecture is Dr. Chanjin Park.
Okay.
Sir, I welcome you all for the first lecture of this session of MEMP 2021. So let me introduce the speaker of this session, Professor Chanjin Park. Dr. Chanjin Park is a professor of material science and engineering at Channam National University, Korea. He received his PhD degree from Korea Advanced Institute of Science and Technology, KAIST, in 2003. From 2003 to 2005, he worked in POSCO Technical Research Lab. He joined the faculty of School of Material Science and Engineering at Channam National University in 2005. In 2015 and 2016, he worked as a visiting scholar in University of Washington, US. Since 2020, he has served as a director of BK21 Center for Energy Convergence Materials, CNE. His research interests focus on the synthesis and electrochemical characterization of electrode and solid electrolyte materials for rechargeable batteries, including lithium-ion, sodium-ion, potassium-ion, lithium-ion, and lithium-sulfur batteries. He was editor of Metals and Materials International from 2010 to 2018. and currently he serves as an associate editor of Journal of Electrochemical Science and Technology. With this introduction, I welcome Professor Park to deliver the talk entitled Insight into Composite Solid Polymer Electrolytes and Their Applications in All Solid State Lithium-ion Batteries. Professor, please.
Okay, thank you, Chairman, for your nice invitation and the nice introduction of me. I prepared the video file for the presentation by asking. So can you share the file?
Yeah, yes.
Okay. Please. Okay, after seeing the video, then we can have the discussion time.
Yes, Professor.
I should share. Okay.
Good afternoon, ladies and gentlemen. This is Johnny Park from
Professor, whether it is visible?
First of all, I appreciate your recovery and that. Good afternoon, ladies and gentlemen. This is Johnny Park from University of Louisville. First of all, I appreciate your recovery and have a long invitation to this excellent conference.
Dr. Ram, can I share the file directly?
Yes.
Okay. Please stop yours.
Yes. Yeah. Professor?
Sorry for your inconvenience. Okay, I will share.
Yes. Yes, it is visible now. Professor, the voice is not coming. Professor, the voice is not coming.
Pardon?
Voice is not coming for the presentation. Only movie, that video is running.
Okay. I understand.
Good afternoon, ladies and gentlemen.
This is the Chanjin Park from Jeondan National University, Korea. Most of all, I appreciate Dr. Kale and Dr. Ram's invitation to this excellent conference. Today, the title of my talk is Insight into Composite Solid Polymer Electrolyte and the application in all solid-state lithium-ion batteries. Here, let me introduce our group's efforts toward the development of all solid-state lithium-ion batteries. In particular, this work was mainly conducted by our PhD student, Mr. Pravin from India. Lithium-ion batteries have been used in many applications such as electric vehicles and other mobilities, ESS, and portable devices. In near future, in 2025, the proportion of lithium-ion batteries in market will increase up to 60%. In particular, the battery market will grow rapidly in Europe and North America, as well as Asia. When comparing the market share of each company, LG Chemical from Korea, Panasonic from Japan, and CATL from China are regarded as big three, and the most big battery companies are from these three countries. We expect that the competition in global EV, electric vehicle, and related battery market will be severe because many of the global IT companies are interested in this EV market. However, lithium-ion batteries have suffered from safety issues related to battery fire. Battery fire happened in various applications such as electric vehicle, electric scooter, public bus, the large energy storage system for renewable energy plant, portable electric devices, and even during the delivering batteries. All these battery fire incidents are related to the intrinsic problem related to flammable liquid electrolyte used in the lithium-ion battery. These figures show the mechanism for the battery fire in lithium-ion battery. Generally, for make a fire, three requisites: fuel, heat, that is triggering, and oxygen are needed. Here, flammable organic liquid electrolyte can act as a fuel. Onset of the overheating is related to the lithium dendrite, separator flows, overcharging, and cell crushing. Finally, the oxygen is released due to the decomposition in cathode material, because cathode material is composed of the many oxide in containing oxygen. To address this safety issue in lithium-ion battery, the battery developed is toward reducing the use of the flammable liquid electrolyte. The hybrid or gel-type polymer electrolyte containing smaller amount of liquid electrolyte has been used to improve the battery safety. Nevertheless, the ultimate object is to develop all solid-state batteries in which all components are made of stable solid. Most of all, key component in battery in solid is a solid electrolyte replacing liquid electrolyte. Due to several advantages such as the easy fabrication and making of the flexible battery interface with the LiFTFSI salt and the major pore silicon nanoparticles, followed by the casting into the composite polymer film. Here, the MSM particles was synthesized using stable method. The prepared film is transparent and highly flexible and bendable. As you can see, this figure shows the physical characteristics my major porous silicon nanoparticles, that is MSNs, prepared by a stable method. The MSN particles show the granular shape with an average particle size of the 27 nanometer. From the XRD pattern, you can see the unforced nature of the MSNs. The particles show the highly porous structure And the high specific surface area corresponds to the 349 square meter per gram, which is very wide surface area. This figure shows the wettability test result of the PPC with a plain glass slide and MSN coated glass slide. The contact angle in the left case was the 43.84 and the right case is the 18.5 degree. This result confirmed the good wettability of the PPC with the MSNs. Generally, the lower angle indicated the better wettability. To investigate the thermal stability of the fabricated composite solid polymer electrolyte, the TG and DSC, the analysis were conducted. And the sample name, the number, the following the sample name, the 0246 indicate the weight percentage of MSN added. From the TG data, all the composite solid polymer electrolytes show the good thermal stability up to 180 degrees Celsius. In the DSC data, the glass transition temperature of the CSPE decreased with increasing the addition of the MSN filler. When estimating the free volumes of the from DSH curves, it was found that the CSP4, which containing the 480% MSN filler, showed the largest free volumes, which is helpful for the ionic migration in solid electrolyte. These figures show the morphology and distribution of MSN fillers inside of the PPC polymer matrix. As you can see that the white colors parsed indicate the MSN particles inside the polymer. Compared with other samples, MSN particles for the CSP4 sample were uniformly distributed. With a higher content of the MSN, which containing the 86%, the agglomeration of particles were found. So you can see that the most uniform distribution of MSN particle was found for the CSP4 sample. To investigate chemical interaction between a PPC and MSNs, XPS analysis were performed. Upper two lines indicated the XPS data in oxygen and fluorine, the core spectra. The CO and CF peaks shifted to higher energies by the addition of MSNs. This result confirmed the MSN interacted chemically with the PPC matrix through the silicon ore oxygen and the silicon fluorine linkage. The lower line shows that the solid state animal data, the lithium peak of the composite solid polymer 4, CSP4, was split and shifted upward compared with that of the pristine polymer. The F peak of CSP was also shifted upward direction. This result confirmed the interaction between MSN and PPC and the coordination lithium-ion with the CSP matrix, which can be the most helpful for the lithium-ion transportation. The electrochemical and mechanical properties of CSPEs were investigated. This figure shows the effect of MSN addition on the ionic conductivity. Ionic conductivity of the CSP was measured to be higher than ionic conductivity of the CSP4 was measured to be higher than others. The obtained value was 8.48. 10 to minus 4 Siemens per centimeter. The temperature dependence of the CSP on ion conductivity source was also measured. The slope of CSP was the lowest for the CSP4 sample, in which the activation energy was estimated up to the 28.19 kilojoule per mole. This figure shows that the linear sweep voltammetry diagrams for the CSP sample. CSP, composite solid polymer electrolyte, was found to be stable up to the 4.8 voltage. The lithium transparent number was estimated using the chronoamperemetry and impedance spectroscopy measurement. The obtained transparent number was 0.87, which very high value compared to the conventional liquid electrolyte case. This figure shows a stress strain curve for the CSP film. With the addition of MSM filler, you can see that the tensile stress was remarkably increased compared with the pristine polymer. The stronger solid electrolyte is very powerful to suppressing the lithium dendrite growth, so that we can easily catch that our composite solid polymer electrolyte can be more stronger, have a stronger resistance to the dendrite penetration compared with the pure polymer sample. To investigate the stability of the CSP with the lithium metal, the lithium symmetric cell was made and tested in various current densities. As you can see, the composite solid polymer electrolyte exhibited our CSP4 exhibited a lower polarization than others. You can see the polarization means that there's some the voltage, the over voltage mean the over voltage. The over potential and the conductivity, over potential decreased and the conductivity increased, which is exactly the matched with each other. So the over potential and the conductivity was optimum for the case of the with the 4 weight percentage MSM fillers. We conducted a cyclic test at 1 milliampere per square centimeters for the 1000 hours. Our CSP4 cells show that the quite stable performance for such a long period of the time. This is mainly due to the maintenance of high ionic conductivity of the electrolyte, as well as the suppressing the lithium dendrite growth. Here we used the lithium symmetric cell, which is composed of lithium composite solid polymer electrolyte and lithium. After the cycling the test on a symmetric cell, the lithium surface was analyzed using XPS. From the peaks, especially many byproducts such as RIF, some RI3 and SN, this kind of the byproducts was formed. Especially that the RIF, lithium RIF was found mostly. In addition, the relative, when comparing with our pure polymer sample and our composite polymer sample, the pure polymer sample, the peak intensity for the byproducts was much larger. This byproduct formation is mainly due to the electrolyte decomposition. So we can get a conclusion that we can estimate that with the addition of the MSM filler, the chemical stability of the polymer electrolyte can be remarkably improved. Now, to check the comparability of our solid polymer electrolyte with the lithium iron phosphate cathode, so we observe the cross-sectional morphologies. It is evident the superior contact, you can see that very good contact between a composite solid polymer electrolyte and cathode material. for the CSP4 case compared with the CSP0. You can see that the several long crevice between SP0 and cathode sample. So accordingly, our all solid state battery composed of lithium CSP4 and LFP cell exhibited a lower impedance, and also it showed that the lower impedance than others. So as a result, you can see that our composite solid polymer electrolyte can show the better compatibility with the cathode material. The all solid-state batteries composed of the lithium metal anode and composite solid polymer solid electrolyte and LFP cathode were charged-discharged tested. This figure shows that the rate capability of the cell with the C rate up to the cell containing the CSP4 exhibits a better rate. The last figure shows the long-term cyclability of the cell measured at 1C. As you can see, the all solid-state cell containing CSP4 exhibits a better cycle. Measured cell voltage was 3.421 volts, which is enough for operating the which can be replaceable by which can replace the conventional lithium-ion battery. And also, the full movie to operate the toy car can be downloaded in the journal as via the website. So, from the result, we can now that we understand that our composite solid polymer electrical, electrochemical, and mechanical properties, distribution of the MSM fillers, and the large free volume. The interaction with the lithium salt anion permitting high lithium ion transportation through the polymer ceramic interface, and better stability and adequate mechanical strength, the excellent electronic performance, and finally also that our fabrication method is a low-cost method, so that it can enable the low-cost solid electrolyte fabrication. This is a conclusion, the summary of this research. The 480% MSN PPC matrix, that is the CSP, was the optimum composition, that is the mixture demonstrated superior electrochemical and mechanical properties. CSP exhibited the high standard conductivity, the 8.4, and a wide electrochemical potential window up to the 4.8 voltage, and a high lithium transparent number of the 0.86 at 60 Celsius. The excellent comparability between a CSP4 and a lithium metal during a lithium streaming plating process was observed by its high stability over the 1000 hour and very small of potential value. The no dendrite formation was observed even after 1000 cycles. And first, it delivered very excellent discharge capacity, and also it showed that the very long-term cyclability. It showed that the capacity retention of the 76% over the 200 cycles. In the previous work, the passive polymer matrix. In this study, the main transport route was through the polymer ceramic interface and in polymer matrix itself. The ceramic filler was inactive actually and was not solid electrolyte itself. In contrast, in this work, we add the LAGP glass ceramic particles, which is a kind of inorganic ceramic inorganic solid electrolyte. Similar to the previous study, we mixed PPC polymer with LiTFS salt and LAGP the powder. LAGP is the well-known non-silicon type of glass ceramic material, solid electrolyte. LAGP has this composition. LAGP powder was synthesized using Jorgen method, followed by further ball milling process. This figure shows that the contact angle measurement, the test regions, we compared the major oxide type solid electrolyte. That is the ferroscrap type LL2, garnet type LL0, and silicon type LLZP. Among all the solid electrolyte with the PPC polymer solution. Accordingly, we selected the LAGP as the main active filler materials in this work. And distribution LAGP in the composite solid polymer electrolyte, LAGP appeared to be uniformly distributed for the LAGP 7 sampled. The number 7 indicated the weight percentage of the LAGP. Also, this figure shows that physical, chemical, thermal analysis of composite solid polymer electrolyte containing LAGP powder 20 degrees Celsius with the increased LAGP indicating the increase in free volume. Similar to the previous work, the PPC NMR. Similarly, the result also showed the interaction of the LAGP and PPC particles come from the coordination of the coordination of lithium ions with the PPC matrix. So frankly, the effect that we expected further things when we use the active solid electrolyte, but main transport mechanism anyway through the phase boundary. So we did up to the 7 weight percentage the LAGP, which showed that the highest conductivity of 5.63 10 to minus 4. We plot Arrhenius plot. The slope indicated activation energy value. The lower the activation energy was found for the LAGP, the 7 samples. The lower activation energy indicated the easier the ion movement inside of the solid electrolyte. So this figure shows the lithium-ion conduction mechanism through a pure PPC polymer and composite solid polymer electrolyte. The main route for the lithium-ion transported for the pure PPC was through a bulk PPC matrix only. In contrast, when the LAGP particles are already in the polymer matrix, the additional route through a PPC and the LAGP interface can be supplied. As a result, improved conductivity could be obtained. The stability of a composite solid polymer electrolyte with a metal was investigated. Also, we use the lithium cell containing the LAGP7 was stable up to 5 voltage compared with the 4 volt for the pure PPC. In addition, the lithium transference number measured was so high as of 0.77 for the LAGP containing sample. The cell containing the LAGP also exhibited a very stable, more stable the cyclability up to 1000. There is no prominent lithium dendrite growth through the cell, through the electrolyte. Also, this figure shows that the interface morphology between a composite solid polymer electrolyte and the lithium iron phosphate cathode material. Here, when the CSP was combined with LFP cathode, it also showed a very good comparability with each other. The solid polymer electrolyte was combined with the LFP cathode. It showed that the lower stability. When comparing the result with the previous MSM filler, the case, frankly speaking, there are some results, so we thought a lot what is the could get a conclusion that anyway, with the addition of the when the amount of the filler is small, then main mechanism is anyway. But when the MSN filler is added, the size of the MSN filler is nano size, comparatively relatively smaller compared with our LAGP filler. So as a result, so the smaller particle size and result in more the uniform distribution of the MSN in PPC matrix can be more helpful to improve this ionic conductivity and other properties. So this is a summary of these results. The optimized electrolyte with. Did I stop the video because I did a mistake question?
Thank you, Professor, for a very interesting and academically enriching lecture related to solid polymer electrolyte. Now session is open for few quick questions.
Dr. Park, good afternoon.
Good afternoon. Hey, how are you?
Good. After a long time, we are at least seeing video.
Yeah. So yeah.
Yes, a good lecture. A lot of things you have done after that. No, many the solid electrolyte. No, that a good thing, good work you have done within this.
Okay. I received the question. Chatting.
Yeah, you can just one question only. You can answer. One.
Okay.
Professor Park, a nice talk and a very interesting talk. Just I would like to ask one question. Of course, I have two questions. One, the charge and discharge curves, over potential difference in EPC. The slide number 18. Yeah, I could not understand how we define this over potential.
Sorry, there's some problem in sound. So
Potential of your two batteries. One is made up of.
Okay. Sorry.
Yeah.
Yes.
See the file?
Yeah.
Okay.
How do
Here, so due to the over potential mean that based on some that the equilibrium potential, the voltage gap between equilibrium potential and the charge or discharge voltage means that over potential. So I defined that the charge and voltage potential gap as a over voltage total over carried that there's some energy loss. So generally if that the solid electrolyte the resistance is high, the battery voltage is measured to be very high. So it indicated that there are sometimes, when we set a cutoff voltage, it can easily reach the cutoff voltage. Also, it means that.
Okay. Just I want to know whether there is any surface reaction we find. There is one more question that your nitrous plot after adding your LAGP. Do you manage to see the grain boundary resistance and bulk resistance before and after adding your LAGP into your polymer?
Do you mean that the volume change inside the polymer in a ceramic LAGP particles?
Yeah.
Okay. So here, frankly speaking, the main transport mechanism through a phase boundary, not the solid electrolyte itself. So also there is the paper showing the transport mechanism through the ceramic particles. In those cases, the ceramic particle, the percentage is very high. If so, we can, but unfortunately that we added a very small amount of the particle.
Okay, thank you.
Okay, it's almost answered already, because I wondered what did you expect to happen from the adding just a few percent of the LAGP? Because even if it's within the polymer, but what is the major effect? The effect on the the LTFSI near the ceramic, or is it the crystallinity of the polymer that is the main effect?
Okay. And the composite solid electrolyte. So it is a ceramic in polymer or polymer in ceramic. But in those cases, anyway, that we think that the polymer can be the main matrix. Also, we have some results having 80%. It is useful. In those cases, we found that the properties, especially that the polymer is very soft and so easily handled. So it is very close, similar to that of the conventional gel polymer type electrolyte. So in my opinion, I will find, but in an intermediate period, I think that the initial
shouldn't make a big difference.
Okay, I understand. So, but yeah, okay, I understand what you
as ceramic material.
Okay.
Session with my group.
Okay, so frankly speaking, also that I continued the work, so that I did not introduce some main mechanism we suggested in detail. But anyway, that frankly speaking, we also discussed with other professors like Professor Jung Sung Lee and others. Then the mechanism for the transportation is ambiguous. So many discussions and many models. Sometimes some suggest some the model, but all the phenomena. But still, yeah, going. Yeah, thank you.
Thank you, and best greetings to Jong Suk. So he's a good friend of mine.
Okay, thank you. I will give a message. Yeah.
Thank you, Professor. If there are no further questions, I would like to thank Professor Park for accepting the invitation and giving this talk. Thank you, Professor.
Okay, thank you again for your invitation. Okay,
thank you, Professor Park. Thanks for your valuable time.
Okay, thank you. Bye-bye.
Now I hand over the digital desk to our convener, Dr. Ranjit.
Thank you, Ram, and I'm back at the conference. So now we have a talk by Dr. Glenn Mather, the research scientist from Institute of Ceramics and Glass. It's very little difficult to spell Spanish, from Madrid, Spain. And Glenn is going to talk on improving stability and proton transfer in barium cerium-based perovskites for high temperature electrochemical applications. Let me give a short introduction of Dr. Glenn. Dr. Glenn Mather is a research scientist at the Institute of Ceramics and Glass at Monsieur Superior de Investigación. Mather graduated with BSc Honours in 1992 and PhD in 1995, both from the University of Aberdeen, Scotland. He has been a research fellow at Prismet Laboratory at the University of Caen, France, at the University of Aveiro, Portugal, a scientist at ECN Holland, and a visiting scientist at State University of Ponta Grossa, Brazil. His principal research field is ionic and electronic transport of ceramic materials for high temperature electrochemical applications, with special interest in proton transport, listed journals, and is a member of the Royal Society of Chemistry and Spanish Ceramic.
Thank you very much. Like the previous speaker, I've pre-recorded something, so I'm going to try and see if I can get it to work. So I'm going to stop my video for the moment. Good afternoon to you all from Madrid. First of all, I'd like to thank the organizers very much for giving me the opportunity to talk to you today. My talk is about improving stability and proton transport in barium cerium-based perovskites for high temperature electrochemical applications. Before we start, I'd like to acknowledge my co-workers, Angel Trevino, Domingo Perez Col, and Hal Ramosa. For those of you unfamiliar with the topic of ceramic proton conductors, I'd just like to give a brief introduction to their applications. We can use ceramic materials which are principally proton conductors as electrolytes in protonic ceramic fuel cells, and these have an operating temperature. We can also employ these cells in reverse mode by applying current to achieve electrolysis of water and produce hydrogen. And both of these applications involve an external circuit. We can also have membranes with high mixed proton electron conductivity, and these can be used for the separation of hydrogen, typically from a high hydrogen partial pressure regime to a low hydrogen partial pressure regime without an external circuit. And they can also be used for useful hydrogenation or dehydrogenation reactions in membrane reactors, such as for the production of benzene from methane, as is shown in the slide. So what are the requirements for proton conduction in an oxide? Here we have a 2D view of a 3D crystal lattice achieved by doping a metal cation with a lower valence cation. The doping partial pressures. Here we have the hydration reaction written in terms of Kroger-Vink notation, so for every in the lattice. And then third, we need a structure which allows the rapid transport of protons. Proton mobility occurs by the Grotthuss mechanism, where protons hop from one lattice oxygen to an adjacent lattice oxygen. So let's look in more detail at the hydration of the lattice with oxygen vacancies and the formation of protonic defects. Absorbs hydroxide ions which replace the oxygen vacancies, and then the oxide acts as a base when the second proton from the water molecule protonates a second oxygen in the lattice. And this base reaction is the dominant reaction in perovskite proton conductors and indicates whether or not an oxide material will absorb water. This really depends on the acidic or basic nature of the oxide. In an acidic oxide such as silica, where we have a small cation of high charge, we essentially have a covalent bond where the electron density, the electron cloud around the oxygen is pulled towards the cation, and so the electron cloud around oxygen doesn't really attract the proton. In a basic oxide where we have large cations of low charge, the electron density is localized around oxygen and is much more attractive to protons. So here we are looking at a perovskite series with a range of A and B cations of different ionic radii. And so for perovskites with large cations, such as the case of barium cerate or barium zirconate, the oxygens are more electropositive and will attract protons. And this is associated with greater enthalpies of hydration, but also greater basicity. So what we tend to find is that perovskites with good proton conductivity tend to have low stability, and perovskites with poor conductivity have high stability. And this is one of the principal issues with ceramic proton conductors. The best conductors have poor stability in acidic gases, such as CO2. One of the best proton conducting series is based on barium cerate. Barium cerate has good conductivity, good sinterability, but rather poor stability. And this instability is related to the large basic cations. The perovskite itself may react with CO2 to form barium carbonate, or we can have residual barium oxide in the grain boundaries which can react with carbon dioxide to form barium carbonate, leading to the mechanical degradation of sintered samples. So a common strategy to improve stability is to partially replace cerium with zirconium, for example, but this generally lowers conductivity and leads to poor sinterability. So recently some groups have looked at alternative strategies such as halogen doping of the oxygen sublattice. So we have halogens introduced into the oxide sublattice, which in theory should reduce the basicity of the anion network by lowering the anion electron density and thereby improving stability in acidic atmospheres. Another strategy we have is to introduce barium deficiency. A-site deficiency in perovskites is quite a common strategy, but is surprisingly underreported in barium cerate. There was, however, a paper in 2018 by Kim. There's a nanoscale amorphous layer which forms at the grain boundaries, and this inhibits proton migration between grains, and this amorphous layer is also reactive with CO2 and water. In contrast, if we have barium deficiency, this enhances stability and enhances grain boundary conductivity. Using these recent results as a basis, in this presentation I'll describe what we've been doing in our laboratory, focusing on improving the stability of barium cerate, either through looking at the effects of bromine addition or an analysis of the effects of barium substoichiometry. And we'll be looking at the effects these have, particularly on the structure, stability, and a detailed look at the partial components of conductivity. So the first system I want to talk about is barium cerate doped with up to 20% bromine on the oxygen site. Synthesis was by a nitrate citrate process based on the Piccini method, with dissolution of the nitrate precursors and barium bromide, followed by addition of citric acid and ethylene glycol. There was then a series of heat treatments to induce polymerization and then pyrolysis, and then the final sintering temperature was 1500 degrees. And as you can see from the scanning electron micrographs of both BCY and the bromine doped material, we could achieve high relative densities of above 92%. So the XRD data of the BCY was refined in space group I2/A in accordance with previous reports of BCY. We could also refine the bromine synthesized material in the same space group, although the monoclinic distortion was greater, as we can see from the greater peak splitting of the bromine doped phase. But we couldn't detect measurable quantities of bromine in the bromine synthesized samples. So then we looked at the samples with total reflection X-ray fluorescence with its higher sensitivity to halogens. And this is a table of the molar content of bromine for the 5% and 20% doped samples at two temperatures, 1100 and 1500. And what we can see is that the bromine is present only in trace amounts. When we increase the sintering temperature, there's even less bromine at 1500 compared to 1100. But despite this, we do observe some effect on the structure, the greater distortion that I described. So, in terms of electrical properties, we first measured the total conductivity of the bromine doped barium cerate series with impedance spectroscopy in different atmospheres. Here are temperature dependence plots of BCY and the 10 and 20% bromine doped phases. And we can see similar conductivity behavior for BCY and the doped phases in dry oxygen and nitrogen. In the high temperature range, conductivity increases for a greater oxidizing atmosphere, and this is characteristic of a high contribution from electron hole. Dry oxygen and nitrogen converge, and this is probably due to a greater contribution of ionic species, due to a lesser contribution from electron holes at low temperatures due to their higher activation energy. If we now compare the conductivity in wet and dry oxygen and nitrogen for BCY and the bromine doped phase, we can see, first of all, there's a higher conductivity in wet in the lower temperature range for both samples. and then the conductivity in wet and dry converges at intermediate temperature. And this merging of conductivity in wet and dry is displaced to lower temperature as the oxide. So here we're comparing the conductivity with bromine content in the reactant mixture, dry nitrogen atmosphere. And we can see that conductivity increases quite remarkably as the nominal bromine content increases in the reactant mixture. And this increase in conductivity occurs in both dry nitrogen and dry oxygen, even though we may expect different transport species to dominate in these different atmospheres. So, conductivities of the series in more detail by studying the effect. This method arises from explicit solutions of the concentration of transport species as functions of oxygen and water vapor partial pressure as developed by Frad, and then the subsequent methodology developed by Beck. When we substitute cerium 4+ with yttrium 3+ on the perovskite B site, we generate oxygen vacancies. In wet atmospheres, these vacancies may then become hydrated in the manner we described earlier to form 2 hydroxyl groups in the lattice. Or in oxidizing atmospheres, the vacancies may be compensated by electron holes. We also have the electroneutrality condition, where the concentrations of positive and negative charges are balanced. So the negative effective charge of the yttrium dopant is balanced by the positive charges of the hydroxyl groups and oxygen vacancies. We can thus derive generic solutions for the defect concentrations based on the equilibrium constants of hydration and oxidation, and the oxygen and water vapor partial pressures and the dopant concentration. So the partial conductivity of the charged species is the product of its charge, its mobility and concentration. We can then arrive at generic formulae for the conductivity defined in terms of a series of constants. And these constants are the alpha, which is the product of, which is 8 times the dopant concentration divided by the equilibrium constant for hydration. A reference partial proton conductivity defined at 1 atmosphere water vapor partial pressure. A reference oxide ion partial conductivity defined at 0 atmospheres water vapor partial pressure. And a reference electron hole partial conductivity defined at 0 atmospheres water vapor partial pressure and 1 atmosphere oxygen partial pressure. So the methodology involves determining the constants, which then allows the partial conductivity to be determined for the imposed conditions of oxygen and water vapor partial pressures. For a fixed condition of water vapor partial pressure under variation of the oxygen partial pressure PO2, the partial proton and oxide ion conductivities are essentially constant, and the electronic conductivity follows a quarter power law dependence. So the total conductivity can be expressed as the sum of the partial conductivities, and this can take the form of a linear equation as a function of PO2 to a quarter. The intercept of this linear equation is the sum of the proton and oxide ion partial conductivities, and its slope is given by this term. So the reference electron hole partial conductivity and alpha can be determined from the experimental values of this slope at 2 different water vapor partial pressures. And once we have alpha, we can then determine the equilibrium constant for hydration, Kw. The reference proton partial conductivity and oxide ion conductivity can then be determined from the intercepts of the slopes at two different water vapor partial pressures. So here we have the PO2 dependencies of conductivity in wet conditions for BCY20 on the left and bromine dope BCY20 in blue here on the right. The flat behavior we see at low PO2 is typical of ionic conductivity, whether that be oxide ion or protons. And the increase in conductivity we see at higher PO2 is typical of an electronic contribution. So we can see that at lower temperature there is a lesser contribution from electron holes and a more contribution from ionic species. Here's the same data expressed as the linear relationship we've just defined at two different water vapor partial pressures. We can see that the slope increases with increasing temperature and lower water vapor partial pressure, and this is due to greater electron hole conductivity. And the different intercepts indicate that we have protons and holes contributing to transport. So what we do is we fit these linear equations, and then according to the methodology just described in the two different humidifications, and we can determine these four constants. Here we have the partial conductivities of bromine synthesized BCY at a PO2 of 1 atmosphere as a function of water vapor partial pressure. The total conductivity is given in black, oxide ion conductivity in red, electron hole or p-type conductivity in blue, and the proton conductivity is given in the open circles. So we can see that in dry conditions the conductivity is mainly governed by electron hole and oxide ion conductivity, and this is due to the high hole and oxide ion vacancy concentration and low proton concentration. As we increase pH2O, the proton conductivity approaches that of the electron hole and oxide ion conductivity, and eventually the proton conductivity becomes the dominant charge carrier. In more reducing conditions, the electron hole conductivity in blue decreases by about an order of magnitude, and in the lower range of pH2O, oxide ion conductivity is the dominant transport mechanism. But again, as we increase the water vapor partial pressure at high pH2O, proton conductivity becomes predominant. Now, if we compare the same results which we've just described at 800 degrees with those at a lower temperature of 600, what we see is that at the lower temperature, the electron hole and oxide ion conductivity decrease due to their lower mobility. However, there's only moderate changes of the proton conductivity due to the higher proton concentration at the lower temperature. So this has the effect that at 600, the proton conductivity is dominant at a lower water vapor partial pressure than at 800. In more reducing conditions, what we see is that the total conductivity is again dominated by oxide ions for water vapor partial pressures below 10 to minus 4 atmospheres. And then there's a crossover, and the total conductivity is then dominated by protons for water vapor partial pressures greater than 10 to minus 2 atmospheres. So here we compare BCY on the left with the bromine synthesized BCY on the right, their profiles in terms of their partial conductivities. And we can see that they both present similar profiles as functions of as a function of water vapor partial pressure. The total conductivity is dominated by protons for water vapor partial pressures above about 10 to minus 2 atmospheres. So here we compare the partial conductivities of BCY and bromine doped BCY on the same plot at 600 degrees with a PO2 of 0.2 atmospheres. The bromine doped sample is indicated with filled symbols and the BCY with open symbols. And although the profiles are similar, there are important differences. The bromine doped phase presents higher values of conductivity for the ionic components, although results are similar to BCY for the electron hole component. So the reason for this enhancement is not readily apparent. What may be occurring is that barium evaporation is occurring along with that of bromine during processing. And this behaviour is consistent with the creation of negative barium vacancies, which are then charge balanced by positive charge carriers, which then increases conductivity. Turning now to the stability of the bromine doped barium cerate series. Here I've shown the conductivity with time as a percentage of the initial conductivity in a CO2 containing atmosphere for BCY and bromine doped BCY. And we can see that the conductivity drops by over 75% in the CO2 containing atmosphere after 8 days at 700. And contrary to what we synthesized composition. And this poor stability was confirmed by thermogravimetry. We can see a significant weight gain here for the bromine synthesized phase. Considering the work of Kim described earlier, we can speculate that we have segregation of barium at the grain boundaries, which favours reaction with CO2 bromine, which may also lower stability. So the second strategy we adopted was to introduce barium in perovskites is generally compensated by A-site vacancy formation, where in this case barium vacancies are compensated by a greater amount of oxygen vacancies. Or the compensation mechanism can be dopant partitioning, in this case of the yttrium dopant over both A and B sites. And this, in fact, leads to a consumption of the barium deficient material was similar to that of BCY and the bromine synthesized phase described earlier. We used a citrate nitrate process based 1500 degrees, where we could achieve a relatively high relative density. We then used neutron powder diffraction for the space group I2 over M, as was the case for BCY and the bromine doped material. And barium deficient cation site occupancies didn't clearly indicate whether A-site vacancy formation. The AO bond length and specific free volume compared with BCY20 indicated that A-site vacancy formation is more likely than a dopant partitioning mechanism. Carbonation of barium cerates is more favourable at low temperatures. So to provide a comparison of stabilities, we exposed barium stoichiometric and barium deficient phase to laboratory air for up to 13 days. A simple visual inspection showed that the degradation of BCY20 occurred after a few days, with whitening of the pellet surface followed by cracking and mechanical breakdown, whereas the barium deficient phase in the corresponding XRD patterns, the formation of barium carbonate is only really detectable after about, it seems to be necessary for the complete degradation of the sample. And consistent with previous reports, barium deficiency prevents carbonation, probably because of less segregation of barium at the green-brown rays. We have the absence of this amorphous nanolayer seen in the work of Kim. So to further check the stability of the barium deficient phase, we measured its electrical conductivity before and after exposure to CO2 at 700 degrees for 7 days. The red dot here corresponds to the initial conductivity in air, and then the blue data here on reintroducing to air after exposure to CO2 for 1 week. So we can see that there's no real loss in conductivity, indicating the high stability of the barium deficient phase. And then the show there was no change before and after. And I should mention also that the mechanical integrity of the pellet was maintained after this procedure. To test the stability in reducing conditions, samples were exposed to wet hydrogen and nitrogen after about 30 hours, but degraded significantly after about 70 hours exposure to hydrogen. And in blue here we have the barium deficient phase, which remained fairly stable, and the pellet integrity was maintained throughout the measuring period. And the XRD diffraction patterns post exposure to hydrogen indicated the presence of an amorphous phase in the case of the BCY sample, which wasn't present in the barium deficient sample. The total conductivity, here we have the temperature dependence of conductivity in dry oxygen and nitrogen. We can see that in the high temperature range, conductivity is greater in oxygen than nitrogen, indicating a significant contribution from electron holes. And then in the low temperature range, the conductivities start to converge, indicating a greater contribution of ionic species. Here we compare the conductivity of the barium deficient phase in blue with that of BCY20 in red, and we can see that barium deficiency increases the total conductivity in both oxygen and nitrogen, even though the contribution from the different charge carriers may be different in these two atmospheres. Here we have the conductivity of the barium deficient phase as a function of PO2 at two different humidifications. Again, as before, there's a PO2 dependence in wet and dry conditions, which shows the presence of then we have increasing electronic contribution at high PO2. If we use the linear representation, we can determine, as before, the partial components of conductivity from the intercepts and slopes of the linear fits. As before, the lower slope at lower temperature indicates a lesser electronic contribution and a higher ionic contribution, and the lower slope in wetter conditions in comparison to drier conditions indicates a lower electronic contribution and a higher ionic contribution. So we can now go on to compare the partial conductivities of the barium deficient phase with BCY. Here we have the total conductivity, proton conductivity, oxide ion conductivity, and electron hole conductivity for the barium deficient phase here with the closed symbols, and BCY with stoichiometric barium in the open symbols. All these plots are at 600 degrees and an oxygen partial pressure of 0.2 atmospheres. So as we can see, all the components of conductivity increase for the barium deficient composition. And as we speculated for the barium synthesized phase earlier, barium deficiency is likely to create barium vacancies, which are electrically balanced by positive charge carriers, whether they be oxide ion vacancies, electron holes in dry conditions, or protons in wet conditions. Finally, I'd just like to show that from the partial conductivities, we can model the transport numbers of the different species as a function of oxygen partial pressure and water vapor partial pressure. And this comes into use for determining the operational ranges of these electrolytes in fuel cells, for example, or as mixed conducting materials for separation membranes and reaction membranes. I'll just wrap up with some conclusions. In the first part of the talk, where we addressed bromine doping in BCY, we saw that bromine addition to BCY produces a considerable distortion of the perovskite lattice. However, only traces of bromine are present after sintering at high temperature. There are greater partial conductivities for the bromine synthesized samples, and this may be associated with the creation of barium vacancies in the bulk during synthesis, as seems to be confirmed by later work we did in barium deficient samples. And there's a greater instability for the bromine synthesized compositions in CO2, which may be attributable to minor contents of barium segregated at the grain boundaries. So in terms of barium deficiency also produces a greater distortion of the perovskite lattice. We see an improvement of total and partial conductivities associated with higher contents of positive charge carriers in the bulk, which compensate the barium vacancies. And stability is considerably improved in both carbon dioxide and hydrogen for barium deficient compositions, probably due to a lower segregation of barium at the grain boundaries. So I'd like to thank the Science, Innovation and University Ministry in Spain for various sources of funding. And we'd also like to thank the Institut Laurent in France for neutron beam time, as well as assistance from Clemens Ritter and Ulysses Amador. The work described in this talk has been published in Acta Materialia, where you can find the bromine synthesized work, and there's another paper in press for the barium deficient series in Journal Power Sources. And I'd be quite happy to send you a copy of these papers if you write to me at the given email address. And finally, thank you very much for your attention. I'll be perfectly happy to answer any of your questions.
Dr. Glenn, thank you very much for your nice talk. We can now take only one question for Glenn. Dr. Narendra Nasani, are you online?
Hello, can you hear me?
Yeah. Hello.
Hello.
Yeah, please.
Can you hear me?
Yeah, go ahead with the question. Glenn, can you unmute?
I can't hear any questions.
Narendra, are you online? Oh, I think.
I hear it.
Seems he is.
Yeah.
Professor Mathur, can I ask one question? I'm curious how the conductivity of bromine along with oxygen here?
We think that there's actually, although there's literature reports of bromine being doped into the barium cerite lattice, but from our work we couldn't actually show that there was bromine in the lattice. We used the TXRF data, and it showed that the amount of bromine that's left in the lattice is really trivial and probably not going to affect the electrical conductivity. What it does do is it changes the stoichiometry of the barium ceriate if you include the bromide in the as a starting reactant. And this change in stoichiometry appears to be related to the creation of barium vacancies, and this is what increases the conductivity in materials that are synthesized with bromine, even though that bromine is not present in the crystal lattice when you've when the high temperature sintering takes place.
Professor Glenn, I think we have 2 questions in the chat, but due to shortage of time, we cannot take them. So it will be good if you can reply to the chat.
Sure.
There are 2 questions. Now, thank you very much for accepting our invitation and delivering the talk. Now, let me hand over the digital dials to our Director General. Thank you very much. Now let me hand the digital dial to our Director General, Dr. B.B. Kale, for the introduction of the next speaker, Padma Bhushan, Dr. Raghunath Mashalkar. Over to you, Kale, sir.
Sir, good evening.
Good evening to you.
Thank you, sir. Thanks for your valuable time today. And our students are actually waiting for your lecture today. And basically, I would like to tell you that we have also connected the students in the rural area where they are watching in one room or something, one hall, maybe 100, 120 students each in lab, the colleges. So yesterday we also told them that this is a good lecture. Then all college principals agreed to for this connectivity and other things. So good things are that you are today talking about some good on good subject, and people are even people from abroad are also there today. They will join very soon now. And they are also going to listen to your lecture, even including Dravid. I talked to Dravid also. He may also join today for your lecture. So today's sir is a national research professor and also has been the Director General of Council of Scientific Industrial Research, CSIR, Chairman of National Innovation Foundation, as also the President of Indian National Science Academy, Global Research Alliance, and Institute of Chemical Engineers, UK. In recognition of his pioneering research contribution in polymer science engineering, he has been honored as a Fellow of Royal Society, Foreign Fellow of US National Academy of Science, as also Engineering, Foreign Associate of American Academy of Arts and Science, and Science and Fellow of US National Academy of Inventors. 44 universities from around the world have honored him with honorary doctorates. The 60+ awards won by him include the prestigious Poisse Lenovo Science Prize, the highest science prize by the World Academy of Science, Business Week USA Award of the Stars of Asia at the hands of the Senior George Bush, and J.R.D. Tata Corporate Leadership Award, the only scientist to win it so far in the 3 decades. That is a very honor for us, sir. Then he was a member of the Scientific Advisory Council to the Prime Minister for over 30 years. Has been honored with Padma Shri, Padma Bhushan, and Padma Vibhushan, 3 of the highest civilian honors. Sir, it's honor for us today to have such a good personality with us. To our students, thanks for your time. So I will now request you to deliver your lecture.
I'm trying to share the screen.
Yes, sir.
I see only the whiteboard.
Just a minute, sir. I'll just find out.
Yeah.
Mashalkar sir,
Yes.
I think you are sharing the whiteboard from the Zoom itself. So you start your presentation and instead of sharing the whiteboard, share the screen. There is a whiteboard feature in Zoom. I think by mistake that you are sharing.
But it says host disabled attendee screen sharing.
No, sir. Well, sir, sir, you are the host now. We have made you the host.
Yeah, but
Yes, sir. Yeah, your whiteboard is coming, sir, now.
yeah, just 1 second. Can you see the presentation?
No, not yet, sir.
We can see the whiteboard. So you're sharing whiteboard from the Zoom, sir. Share desktop. I mean, if your presentation is on the desktop, you have to do share desktop.
Yeah, but that's what I'm trying to do. I had the same problem just now with IOC, and then they asked me to send the presentation, and then they ran it. It was same problem just 1 hour ago.
Sir, can you send me the presentation immediately? I will do that.
So you can send us the presentation. We immediately play it from here, sir.
Yeah, okay, I'll do that. Just one. Sorry about that.
No problem.
Just now I'll send it.
Send on my Gmail, sir. No problem.
Yes. What is? Just 1 second.
bbkale1@gmail.com.
Sorry, BB
Kale1.
Yeah.
@gmail.com.
Okay, I'll send it in. Just 1 second.
Takes some 2 minutes to come now.
Yeah, sorry about that.
No, it's okay. Okay, no problem.
Sir, can you start your video?
No, just 1 second. I've started the video. Just
That's
1
fine.
second. I'm just sending it to you. Just give me.
Sir, file is not big, no?
Yeah, it will come to you on a.
Okay.
Don't worry. Yeah, it says it has been sent. Just see whether you have received it. Hello?
Hello, sir.
Yes. Have you received it?
Yes, sir. In 5 minutes, we'll put it.
Bharat, have you received the file?
Sir, one minute will confirm, sir. 1 minute. Sir, we have received your file. Just give us a moment. We'll be playing it.
Yeah. Okay. Thank you. So if you can give me the control for running the slide.
Yeah, we'll make it host, sir. Hello, sir. Can you see the slides?
No, I can't see.
However, it is not still time. It will take some time, 2 minutes, 1 minute at least.
Yeah.
Can you see the slides, sir?
No, I can't see the slide. I can see the title, CMET Serendipity Public Lecture. Yeah.
Yeah.
Yeah. Go to the first slide. This is way down. Go to the first slide. Go back. Yeah. That's right. I can. Yeah, and give me the share. Give me the control.
Yeah, we are making a host, sir.
Okay. Okay.
Okay, sir.
Okay, right.
Just a moment.
Yes. Thank you very much. I'll start with a deep apology about this last minute challenge.
No, sir.
What I'm going to do is to talk about the importance of science and innovation, serendipity. Now, first of all, one would want to know, the slides are not moving. Slides are not moving. I've not got the control.
Sir, you are the host, sir.
Yeah. So first of all, let us define what is serendipity. I'm seeing the slide, but it's not moving. Yes. Okay. The serendipity, the Oxford Dictionary defines it as the faculty of making happy and unexpected discoveries by accident. And I have difficulty in moving it. I think yes. And the discovery by chance or sagacity of valid results, which were not sought after, is no, I have difficulty in moving. Actually, this doesn't move. There is a lag. Robert Merton talks about it as the discovery by chance or sagacity of valid results, which are not sought after. I think you may take control and run it because there is a lag from my side here. Please take control. Yeah. Now, serendipity has won Nobel Prizes. Next. 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 No, it is not showing up. Next. Next. Yes, go ahead through the whole slide. Yes. Yeah. Yeah. So if you see the names of individuals here, right from Henry Becquerel, 1896, to Carey Muller's PCR, 1993, there have been several Nobel Prize winners because of the happy accidents that took place. Next. Next slide. I'll go through the whole slide. Yeah. And if you can see, there have been 53 major new drugs that are discovered, right from statin to sulfonamide. Serendipity has also led to new businesses. For example, this slide shows that George Mestel was walking his dog and the plant seed sacks were sticking to his dog after a walk. And inspired by this, he went on to invent Velcro. And that rivaled the zipper in its ability to fasten. Next slide. And the serendipity-led Velcro business, as you know, is $500 million, and it is sold in apparel. And Velcro Industries hold actually 160 active patents. So therefore, such breakthroughs, accidental breakthroughs, can lead to big businesses. Next one. If you see here, the serendipity plays funny in terms of leading to businesses. For example, here is an example of adhesive that did not stick. The post-it pad, for example, was one where, because it did not stick, the office secretary used to just stick them around on the notes or the files and send it away. And then they suddenly realized that this is a big business. So here was a failure in terms of adhesive not sticking. No, don't change till I say, go back. Go back. Yeah, I will say change and then you change. And then there was a case of adhesive that stuck too well to an extent they could not find the refractive index because the prisms were sticking to each other. It was given up. And after several years, people found this as a super glow, cyanoacrylates, and that became a big business. I think the point I'm trying to make is that accidents play in a funny way, and you can create big businesses through these failures. Next slide. And serendipity has been continuing. This will be a subject of interest to all of you. For example, there is a breakthrough on crystalline graphite, and they unexpectedly discovered a new way to make crystalline graphite, which is an essential material used in making of lithium-ion batteries. Next slide. And if you see the breakthrough, the way it occurred, as they say, unexpectedly, 90% of the samples got transformed into highly ordered structures. And this, of course, is a breakthrough. No need of metal catalysts or special raw materials to turn carbon into crystalline graphite. So right in your own field, such breakthroughs actually take place. Next. Now, if you see, there is this issue about chasing anomalies. A fairly common experience of observing an unanticipated anomalous and static datum, which become the occasion of developing a new theory or for extending an existing theory. So in my own research, which is in the area of polymer science and engineering, I'll take you through some of the anomalies that I was chasing. Next slide. If you see, complete the slide. If you see, early in the days, we found some anomalous separation in viscoelastic fluid flows. Later on, there was some anomalous transport phenomena in rapid external flows of viscoelastic fluids. Later, we saw some anomalous convective diffusion in films of polymeric solutions. And then there was a discovery of some unusual retardation and enhancement in polymer dissolution. Now, they were all anomalous results, but each one of them led to some profound theories or new insights or models. Next slide. And I have, as a matter of fact, written an article on this, Fun and Joy of Science, Learning from Anomalies and Discontinuities in Current Science. The reference here you can see. Next slide. Let's look through the normal, what anomalous observations you had and what you got out of that in terms of new theory. For example, in convective heat transfer, the heat flux increases with increasing velocity all the time. If you are sitting under a fan and you increase the velocity of the fan, rotation of the fan, you feel cooler, right? But the anomaly was that in rapid viscoelastic flows of dilute polymer solutions, the heat flux remained constant despite increasing velocity after a critical velocity was reached. That was very funny. Next. And that resolution, we wrote a paper, myself and Professor G. Marucci is an Italian professor, on anomalous transport phenomena. And the new insight that we got was that we had to give away the old Prandtl boundary layer theory, which had existed from 1937. And we had to create the concept of elastic boundary layer, where the inertial forces and the elastic forces at the leading edge actually balance out. Next slide. If you see the norm, if you take a solid particle and start dissolving it, the dissolution time will reduce as the particle size reduces. For example, if you take a clump of sugar and put it in water, it will take a long time. But if you take very fine granules of sugar and put them, they will dissolve very fast. But what did we observe? When a solid polymer particle dissolves, the dissolution time remains constant below critical particle size. That means whether you take a lump or a fine sugar, as far as polymer particles are concerned, the time for dissolution remains constant after a critical particle size. Next. And the resolution of anomaly, we wrote a paper where the first time we did the elucidation of the critical role of reptation dynamics, the dissolution time becoming equal to reptation time before below critical size. As you know, the polymer, the Nobel laureate D. James, for example, had talked about the reptation theory, where he looks at the polymer melt molecules as snakes. Bundle of snakes, and they have to reptate out, and that reptation time actually dictates when the polymer is sort of dissolving and not the diffusional flux. Next. Then we found certain anomalous phenomenon. Actually, there was a paper in Nature where Ferguson showed that there were certain associating polymers which were just pulling out from a burette, just open it up, and you will find that the solution will actually phase separate. Similarly, Mesner in Delaware actually found that exactly the same phenomenon takes place. In fact, he had taken polyacrylamide solutions which were being forced to these spinnerets. And the funny thing was, when the solid polymer actually precipitated out, you would normally expect it to dissolve in water because it was a water-soluble polymer which came out. So it should dissolve in water. It would not. No matter what you do, high temperature heating or urea, etc., nothing will actually work. Next. And I and Ashish Lele actually looked at it. We looked at the sort of a conceptual model that we developed with regard to the free energy change because of entropy of mixing, ease of hydrogen bonding upon staging, and deformation-induced hydrophobicity in such polymers. And you can see the hydrogen bonding taking place when the polymer chains are staged and CS2CONH2, CS2CONH3, the internal hydrogen bonding, leaving the hydrophobic part out. So this is like hydrodynamically induced hydrophobicity. Next. And we did actually computations by developing this conceptual model. I would not have time to go into it, excepting to say that we looked at the free energy of mixing, free energy of formation, and free energy of hydrogen bonding. Next. And there were model predictions. We could create these phase diagrams, for example, and how by stretching, actually you can enhance the rate of solidification of these. Next. And very importantly, a paper appeared in Nature, Jean Kaplan in 2003. They cited our paper and suggested that the elongational stress-induced association of fibrin molecules is the most likely reason for formation of silk fibers. You can imagine the sort of hydrogen bonding taking place in the straight chains, leaving the hydrophobic part out. Next. Then we have benefited, by the way, in my laboratory in terms of the breakthrough that we had because of serendipity. In fact, there is this the World Academy of Science Linnaeus Science Prize, which I was lucky to get in 2019. It's the highest prize that the Academy gives. And the title of my talk there was Discovery of Trapeze Artistry in Biomimetic Smart Gels in my group in NCL that we had basically found. Next slide. This shows the photograph of my receiving the prize. Next slide. And here I must talk about the smart gels. So these gels actually show sensitivity, shape memory, as well as mobility. And these phenomena were discovered outside. But what we discovered at NCL was self-organization, which was completely serendipitous observation. Self-healing, which was completely NCL serendipity. And then there was an enzyme-like activity, and this was, of course, sort of a planned activity. Next. And if you look at the breakthrough that had taken place, in early 80s, Tanaka from MIT had shown that these swellable polymers, for example, they imbibe water to an extent where they can increase their size by 100-fold, all right? And by a switch of temperature or pH, you can do a reversible volume transition. Then in mid-90s in Japan, they showed that these gel cylinders could be, for example, you can create mobility in them by bending and rebending, bending and rebending, and you can create a soft robot. And it was in NCL in 2001 that we showed how there is a macroscopic self-organization that takes place to create coconut-like structures. And amazingly, this is completely reversible. Next. For example, these copolymer hydrogels that we had created, polyacrylamide along with polyacrylamide polymethyl sulfonate. You can see in the middle, for example, there is a two-phase gel, which by just lowering temperature by 1 degree centigrade swells, and by raising the temperature by 1 degree centigrade, it collapses completely. So there is a volume phase transition, so as to say. Next. And you complete the slide, yeah. And as a matter of fact, we were the first ones to give a theory on this by creating sort of a balance of both the hydrogen bonding as well as the hydrophobic interactions. Next. And we could see here the prediction of the N-isopropyl acrylamide gel with the experiment and theory working very well indeed. Next. And these gels, for example, the role of hydrogen bonding and hydrophobicity, there's something extremely interesting we saw, because you can do anything with the model to get results. And you can see there were terms which were on temperature dependent hydrophobicity. Supposing you drop them completely, there will be no transition, as you can see from the yellow line. Whereas if you drop the hydrogen bonding terms, again, you will not see any transition at all. So it's a subtle balance of hydrogen bonding and hydrophobicity that our model was showing is important. Next. So if you look at the science is an exploration, you can't always predict. For example, lattice fluid hydrogen bonding models, we provided the first scientific quantitation. The first elucidation of subtle role of hydrophilic hydrophobic balance in volume transition also we showed. But if you look at the third part, and the fourth part, they were completely serendipitous observations, by the way. The metal complexation induced volume transition, as well as the solid gel cylinder turning spontaneously to a coconut-like structure and reversibly. Next slide. And this is what I talk about the serendipity. In fact, can you just believe it? See, we had to create the gels and dry them overnight. And as you know, there is a lot of poverty in national labs those days. I'm talking about 30 years ago. And I remember my student Shaini Varghese, she's a very eminent professor in Duck University now. She was trying to dry it in a new oven, and she would find that the gel will be fine. But when she put it in an old oven, she would find that they turned blue. And she couldn't realize what was happening. And then she one day just did not sleep overnight and just watched what was happening. And she found that they were turning blue or greenish because there was a rust in that old oven, and the rust particles were fine. Can you just believe it? Next slide. Actually, therefore, we actually accidentally discovered this metal ion complexation can also lead to volume phase transitions. We have papers in macromolecules on this, and you can quite clearly see the cupric ion, binding with both the carboxyls, leaving the hydrophobic part out. Next. Then this was the funny part that we found. The funny part was that if you take a cylinder-like gel, basically it will start evolving 12 hours, 24 hours, 72 hours, and 96 hours. And as you can see, there's a rearrangement via complexation that was taking place, creating hollow structures. Next. And you can see here the self-organized hollow objects. If you look at on your left, the siderophores, nature has created them, these hollow objects. If you look at on the right, like coconut, nature has created them. But if you look at the middle, these were structures that were created by us, and they were created by a particular gel, acrylyl 6-amino-cupric acid, and I will talk more about it. But this, I would say, man-made serendipity. They all look similar structures, but this macromolecular scopic organization came up entirely because of an accidental breakthrough. Next. And another serendipity, complete the slide, yeah. You can see what happened was that you didn't have 24 hours, for looking at the gels and so on and so forth. So we had to sort of do something very fast. So as an engineer, I said, my goodness, it's very simple. You reduce the size and then the swelling will take place fast. So the work is actually did that. And we said, all right, the swelling will take place very fast, and we wanted to take a scanning electron microscope. And what we found was very funny. You can see the slide, and if you just look at in detail, you will find that the two gel particles had fused together. Now that is impossible because a gel is a single macromolecule, complex macromolecule, by the way, completely chained to each other. All the chains are completely chained to each other. So at the interface, there cannot be any sort of diffusion, just like you have, if you take a soft polymer, another polymer, and hit them over the glass transition temperature, put them together, then there will be reptation, like snake-like reptation at the interface, and you will create a weld line. Okay? But here, that is absolutely impossible. So this failed experiment turned out to be a breakthrough. Next slide. And we wrote a paper on rapid self-healing hydrogels in PNAS, Proceedings of National Academy of Science. In fact, this paper was highlighted. Next one. Yeah, next slide. Yeah. There is a film there. Can you show the film? If you can't show the film, then move forward. I'll tell you what the film shows. You please move forward. Take the next slide. Yeah. Yeah. Yeah, go down. Go down, go down, yeah. Yeah, that film is missing. Forget about the film, I'll tell you. You go to the trapeze next, yeah. Can you show the film? If you expand it, it is embedded. If it is not there, then you can go to the next one. Then you go to the trapeze picture. Bharat, you go to the picture.
It is hanged somewhere.
Oh.
Sir, can you see the slide?
I can't see the slide, no. Yeah.
Can you see the slide, sir?
Yeah, all right. Okay, I can see the slide.
Yeah.
Yeah, yeah. So therefore, actually, what you would have seen if you had seen the film is that there are two pieces of gel which are just brought together in a fraction of a second. They heal, and this is the rapidest healing that has been shown in gel so far. It's a pity that it's a spectacular film. Really, I would have liked you to see that. Doesn't matter. But I think the point I'm trying to make is that this hydrophilic hydrophobic balance. Next slide, please. Next slide. Now again, it is hanging.
Sir, can you see the slides?
No, I can't see the slides.
Can you see it now, sir?
I can see the slide. I can see the slide.
Yeah.
So therefore, yeah. So therefore, it is all about tailoring of the gels, and we were trying to balance out the hydrophilicity and hydrophobicity. Created several structures. Next slide. Next slide. Yeah. And if you see the tightrope trapeze artistry, if you see in detail, for example, we are trying to balance out, and if you see that as far as the Michelin groups are concerned, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. If you start looking at the balancing part of it, you'll find if it is just one, there was no healing at all, like of the that you saw. If it was 3, it was no healing at all. 5, there was a strong rapid healing. 7, weak healing, and 10, no healing. So there is some magic about the number 5, which is what gives you the acrylyl 6-amino-caproic acid, by the way. That is the point I'm trying to make. So this balance that acrylyl 6-amino-caproic acid gives is the only one which leads to healing. Next slide. And this is the part of the trapeze artistry with regard to acrylyl 6-aminocaproic acid. If you see the next slide, that actually created quite a stir and across the laboratories. For example, these are results done in San Diego, where they have used it in stem cell adhesion and migration. And they found that the cell adhere and spread best on A6-SEA compared to matrices that are containing fewer or higher methylene groups on the side chains. Somehow or the other, A6-SEA does the magic. Next. Yeah, and the matrix hydrophobicity assists stem cells in adhesion, migration, and differentiation. As you can see, the movement, the stem cells move much more slowly on surface containing C5 side chain than the other ones. That means assisting the adhesion, migration, and differentiation becomes possible with A6-SEA more than any other. Next. Similarly, these stem cells adhesion, migration, and differentiation, also the osteogenic differentiation of stem cells, if you start seeing the most training was observed on C5 surfaces. That means A6-SEA. Next. Then this is biomineralization, actually the hydrophobic balance that actually assists biomineralization, as you can quite clearly see here. Next. And these are biomineralized matrices for osteogenic commitment of stem cells. Somehow the A6-SEA did actually the magic, but none other. Next. Then the A6-SEA is creating breakthrough in elastic enteric implants in MIT. You know, Bob Langer's the group actually used this and co-polymerized it with polymethyl methacrylate supramolecular gels. And he said that in 40 years' time that they have been working, they could not find sort of elastic entering implants which were as good as that. So there was some magic with A6-SEA that worked there. Next. Then amazingly, I would have never imagined that. You know, there is a lost circulation of fluids in drilling wells. And many materials such as inorganic polymeric suspensions are used to divert fluid or plugging fluid loss. And this invention that they proposed was to introduce the suspension of A6-SEA hydrogel and change the pH. And by lowering the pH, you create agglomeration. So as soon as you create agglomeration, you have the pores plugged, and that is completely reversible. So any pore that you want to plug, you can actually do this. There are US patents that have been taken. If somebody had told me after we had that crazy breakthrough because of that rusted oven, that this will be the kind of implication, I would have never believed. Next. And then, of course, people looked at graphene oxide and they created superior composite gels with far better properties in terms of tensile strength, etc. Next. And the research continued with carbon nanotubes, for example. And again, with A6-SEA, they found the magic. Unfortunately, I won't have time to sort of go through this. I know that I have just 5 minutes left, so I'm rushing. Next. I think, therefore, what I have shown to you in summary is that we are lucky to get some breakthroughs. But I want to emphasize something, that you may get those breakthroughs, but you can completely miss them. And the basic point is that eyes do not see what the mind does not know. And therefore, it requires a prepared mind. That is the most important. How do we train our students to see this and not miss out? I think is the biggest challenge. So next few, just 5-6 minutes, I'll take you through revisiting serendipity and what are the lessons that we learn. So I would say serendipity is not just an event. It's a capability of identifying a matching pair of events that are meaningful but not necessarily causally related. So can we develop such capacity in our organized research is the basically question, all right? So it is not in education, we are connecting the dots, collecting the dots, like information, pieces of information. Can we start connecting? And if we connect the completely unrelated, then it makes a big difference. Next one. Actually, Nobel laureate Paul Flory had said, the significant inventions are not mere accidents. Many a man floated in water before Archimedes. Apples fell from trees. As long as Garden of Eden, chance discovery involves both the phenomenon to be observed and the appropriate intelligent observer. That's the point I was trying to basically make. Next. In fact, Heraclitus has said the unexpected connection is more powerful than the one that is obvious. And it is by doing that, actually some of the Nobel Prizes have come because these unexpected connections were done. Next. Connecting the dots, mathematician Poincare had said, the useful or interesting combinations are those who reveal to us unsuspected kinship between other facts, long known but wrongly believed to be strangers to one another. Accordingly, so among chosen combinations, the most fertile will often be those formed from elements drawn from domains which are far apart. So in our education system, while we are training our research students, etc., the narrow single lens wouldn't do. How do you do the lateral thinking and connecting the unconnected becomes the most important part. Next. Even social discovery engines can be inspiration engines which are going beyond the nearest neighbor screening. So if you go upon, go and look upon, stumble upon, or banana slug, or delicious US, you will find how these sorts of connections are done. Next. So want to emphasize that chance is an event, serendipity is a capability. There is a big difference between the two. Chance has no bite for creativity in brokering random events meaningfully with other events, but the unplanned or random element retains a role in serendipitous invention. It is more peripheral than central, as has been assumed. Next. Research on serendipity has shown that it has been often spot on by degree of sloppiness, inefficiency, dissent, failure, and tenacity. So don't be too organized. I think that's the point that one is talking about. In fact, Ferguson has said that lofting and savoring the moment of wandering and loitering and directionless activity of all sorts sort of matters. We have to ask ourselves, are we allowing enough time for us to do that? But these are precisely the things that planned and organized research seeks to minimize in its quest for extreme efficiency. So I think sometimes we should not ask for extreme efficiency. Next. Steve Jobs has actually, he's a big believer in serendipitous innovation. And if a building doesn't encourage that, you will lose a lot of innovation and the magic that is sparked by serendipity. So he's talking about building the buildings where researchers work, innovators work in such a way. He wanted the engineers and the designers to be in constant contact to enable serendipitous possibilities that could emerge from constantly bumping elbows, so as to say, rather than sitting in the sort of cabins. I think it talks to us about the environment that we have to create to promote serendipity. Next. Organization and serendipity, if we see, if chance favors the prepared mind, how do we create a prepared mind in an organization? That's the big question. Can there be such a thing as organizational serendipity? And is there an optimal degree of inefficiency or wastefulness to be tolerated or even planned for in innovative organizations? I know that these are very provocative questions, but we have to ask ourselves this. Next. Next. Yeah. So I would say that we need to move from the current best practices to next practices, because the current information management systems are suited for only structured innovation processes. How can they be made to facilitate serendipity? That's the big question. Second, the current funding, project selection, referee systems, they all play safe. They are intolerant to failure. All right. And the not invented here syndrome promotes isolation and not co-creation with collective intellectual power of wild diversity of ideas. And how do you create such an ecosystem, I think, is the big challenge. Next. And need to move from current best practices to next practices. Go back, yeah. In fact, scientific research papers today rationalize a posteriori the theoretical and experimental research, making no reference to serendipitous results, involving elements of failure, chance, accident, surprise, unsought answers. For example, both our observations actually that I talked about, the rapid healing, that paper that appeared in Journal of American Chemical Society, or the self-organization, which actually Nature had commented that it's a Indian rope trick. In both these, we did not tell them about the kind of failures that we had, the process that we talked about. So I think maybe when we are writing the research papers, the process part of it, how do we arrive that rather than just giving tables and flushing graphs? Maybe that is what we need to do, because that the process of innovation is very, very important. Next. Actually, the Global Research Council meeting in Tokyo had said that researchers need freedom and flexibility that leads to serendipity, and they should be encouraged to take risks even if it leads to failures. Next. And this was my sort of experience. And Bharat, you will recollect that, that in NCL in 1989, I created Kite Flying Fund.
Yes, sir.
You remember?
Yes, sir.
There was a chance of success, maybe 1 in 100, 1 in 1,000. I would fund it. Only 1% budget I kept.
Yeah.
Then when I moved to CSIR, I created a new India fund. I did not want to call it Kite Flying Fund because Parliament was just 1 kilometer away, and they would say public money invested on kite flying. And the breakthroughs came up. I remember Chandra Kumar creating 2 US patents on spin computing ahead of the rest of, because he had some crazy ideas, which he actually used.
Yes.
And then I created the NIMITLI program, New Millennium Indian Technology Leadership Initiative, where we gave some grand challenges. And finally, the Daring to Try Prize Tatas was also based on the discussion that Ratan Tata and I had, because I remember he had invited me for meeting of some senior people, leaders, and I talked about a discussion that I had with somebody from the US, and he said, we don't hang people who make mistakes, but we do hang people who don't take risks. And then he asked me, what do you do in India? I said, we don't take risks. And what do you do with the people who take risks? We hang them. And there was a big laughter. But then Ratan Tata talked to me and said, then how do we change that in Tata's, for example? And I said, celebrate those who dared to try but failed. So can you believe it? In Tata, there is a prize for the biggest failure of the year, where they tried sort of big problems. So that is the kind of environment we actually need to take. This is at least my personal experience, not the books that you see behind me, but books of my life. Next. So I think this leapfrogging to pole vaulting, I think, is the critical part of the story, not just jump few feet because you are afraid, but have an aspiration. Next one. Next one, yes, this pole vault to new ideas. And I'm not publicizing my book, but I am publicizing my book. This is the leapfrogging to pole vaulting.
Yes, sir.
This won the 2019 Best Business Book of the Year award in the Literary Festival. And as Ratan Tata says there, that this captivating book, through impressive assured innovation framework, showed the way forward for achieving this daunting task. So this book is actually all about how can we not, Jalapan Marathi manto bedu pudi nave Hanuman udi. How can we actually do that? The book is all about that. And that was the essence of my talk, serendipity and accidental breakthroughs. Next. Yeah, this got the Business Book of the Year award. Next. So I think we have to have a paradigm shift in innovation strategy. We have been following and taking pride that we are fast followers. We have to start leading. We have to start leapfrogging. But most importantly, in my judgment, we have to pole vault, because the size of the pole will be the size of our aspiration. Next. And therefore, we have to create these beyonders, scientists who are able to think beyond the realms of possibilities, bringing science, serendipity, and innovation together, which is the title of my talk. Next. Thank you. Thank you very much. And my deepest apologies for these technical glitches. I'm really sorry about it, but I thought you would get the glimpse of what I'm trying to say. This is all about daring to try, taking risks, having a prepared mind, so that when a breakthrough occurs, you sort of get it. And particularly because young people are listening to this, I have also shown to you how such the accidental breakthroughs have led to Nobel Prizes. I hope one of you will get these one of these days, provided you are able to spot. Thank you.
Yes, sir. This kind of experience is helpful to us. Maybe that those days we have this hydrogel for particular application, but same hydrogel now used in so many other applications. Like recently, people have started using it with for the solid state supercapacitor, as electrolyte. because these hydrogel are very easy to prepare, and we can have ionic movement in the hydrogel.
Correct.
So these are the new concept, new things has come up now, because supercapacitor never been an solid state supercapacitor. Now people are talking about solid state supercapacitor for variety of applications. Means some we can get the good voltage window. So this kind of hydrogel will be useful, and you can see many references now for this hydrogel. That time when you invented that application for the agriculture purpose, that time it was new, but now it is the hydrogels are everywhere, even cosmetics and all this. So people are talking to, and as incidental, we also experience once in our silicon tetrachloride when we started. At that time, the chlorination is the exothermic reaction all the time, and once we in one experiment, what happened? We have the more carbon has gone into the mix, and the temperature was that time less. That means the carbon and silica, as we increase the content of carbon at 500 degrees centigrade, the heat dissipation was occurred, and we control the reactor temperature. So it is incidentally happened that time, and we have made a patent out of it. So that was a great experience in 1993-94. So this is good. Actually, these are the good experiences, and we should. And thank you for sharing with us. Thank you, sir, and thanks for your valuable time for for the students. Thank you very much.
Thank you. Thank you for
that.
On behalf of the organizers and as a convener of this conference, I apologize to one and all for some technical glitches. It was really nice, thrilling, and very charging up lecture by Marcel Gersel. He has touched upon many, not only scientific points like trade with artistry and how that trade with artistry eventually was used all over the world by many researchers to find out novel things. But he has made some very good quotes which all young people and policymakers have to take with them. One quote is that eyes don't see what the mind doesn't think, and chance is even serendipity is a capability, and we have to have prepared mind. By listening to him, I recapitulated one event I want to share with Masika is that in the discovery of graphene was in 2005. But from 1981 onwards, when Gerard Benning discovered the scanning tunneling microscope, everyone in the world knew you have to use the Scotch tape to exfoliate mica and graphite to get a new fresh layer for deposition. But it was only the group of Costa Novoselo and other guys that they observed that okay, we can make some new material by using this technique. And he has given a lot of good suggestions to the policymakers that failures have to be taken very positively. Failures are a part of research, and failures are indeed a major part of the research because they guide to one novel discovery. And his some initiatives like Kite Flying Fund, New Idea Fund, the Tata Failure Prize. I think all policymakers, all directors, director generals, principals, etc., who are listening to this talk, they should take up such kind of initiatives to encourage young people and encourage young minds and tell them that okay, if you fail, still we'll fund you, and that is a very major change that is needed in all kinds of research. And all funding agencies also have to accept that all projects that are given, maybe 99.99% can fail. So I think if this change comes to this, if this change comes to this this country, I think then we'll also have many. Will not be followers, we'll be leaders, and we also will have many more Nobel Prize winners. Thank you, sir. Thank you so much for an enthralling and very charged up lecture. Thank you very much, sir.
Thank you. Thank you very much. Thank you.
Thank you, sir. Thanks. Thank you.
To all all participants, I would like to make a small announcement that tomorrow's session will start at 9 a.m. in the morning. I declare that today's session is over. Okay, see you. Good night. Goodbye.